Section 1 of the Insomnia Collection, Volume 6. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Verla Viera. Excerpts from Scaffolding, a treatise on the design and erection of scaffolds, gantries, and stagings, with an account of the appliances used in connection therewith, for the use of contractors, builders, clerks of works, etc., with a chapter on the legal aspect of the question, by A.G.H. Thatcher, Building Surveyor, 2nd edition revised, with 146 diagrams and 6 full-page plates. London, B.T. Batsford, 94 High Holborn, 1907. Preface. Scaffolding, up to quite recent years, has been considered by builders and others concerned, with the exception of the actual workmen, to be a matter of small importance and consequently unworthy of study. Recent legislation, however, the Workmen's Compensation Act, 1897, and the Factory and Workshop Act, 1901, and preceding dates, has brought it into greater prominence, with the result that more attention has lately been given to it. Special study of the subject has, however, remained very difficult owing to the lack of accessible information. The author, in the course of considerable experience in the building trade, has had opportunities of examining a large number of scaffolds throughout the country, affording him exceptional facilities for thoroughly studying the subject, and he has been led to prepare this treatise in the hope that it may prove useful to those engaged both in the design and erection of scaffolds for building purposes. While special attention has been given to practical details, the theory has not been neglected, but has been dealt with by the use of terms well understood in the building trade. The various formulae given have been simplified as far as possible, and it is hoped that in these days of technical education they will not be beyond the scope of the reader. The illustrations have generally been drawn to scale, but for the sake of clearness, details are given to a larger scale where necessary. The practice of allowing workmen to erect scaffolds without the aid of expert supervision, as is generally the case, is to be strongly deprecated. The architect, builder, or clerk of works should in all cases be responsible for their erection, the risk of defective or unsafe work being thereby minimized, and an economy often effected in both labor and material. The author desires to acknowledge his indebtedness to Mr. G. Thatcher of His Majesty's Office of Works and Hampton Court Palace for valuable information contributed by him, and to Mr. J. Clark of the Factory Department of the Home Office for his very careful reading of the proofs, while his best thanks are due to the following manufacturers: Mr. C. Batchelor, Messrs. Bullivant and Company, Limited, Messrs. Butters Brothers, Mr. J. Fishburne, Messrs. Frost and Company, and Mr. E. Palmer, who have furnished him with particulars of their various specialities. A.G.H.T. London, February 1904. Note to the 2nd edition. Recent alterations in and additions to the legal enactments affecting scaffolding and the persons employed in its erection have rendered necessary a 2nd edition of this work. The author has accordingly revised the information relating to the law of the subject, and has embodied the important series of suggestions for the guidance of those engaged in building operations, published in the annual report of the Chief Inspector of Factories, which, if followed out, will undoubtedly be the means of reducing the number of fatal and other accidents occurring at such works. AGHT, October 1907. Chapter 1. Scaffolding. Scaffolding is the art of arranging and combining pieces of timber in order to enable workmen to proceed with their work, and from which, if required, to lift and carry the material necessary for their purpose. Many definitions of a scaffold have been given by authorities on building construction. Some of the best known are as follows. Mitchell, C.F. Temporary erections constructed to support a number of platforms at different heights, raised for the convenience of workmen to enable them to get at their work and to raise the necessary material for the same. Treadgold, Hurst. A scaffold, as used in building, is a temporary structure supporting a platform by means of which the workmen and their materials are brought within reach of their work. Rivington. Scaffolds are temporary erections of timber supporting platforms close to the work on which the workmen stand and deposit their materials. Bannister F. Fletcher, in Carpentry and Joinery. A scaffold is a temporary structure placed alongside a building to facilitate its erection by supporting workmen and raising materials during the construction or for the repair of buildings. Recent cases tried under the Workmen's Compensation Act have given a wider meaning to the word, and the following definition is perhaps the most comprehensive at the present time. A scaffold, as used in building, is a temporary arrangement of timbers combined and supported in various ways to enable the workmen to proceed with their work, and where required, to afford facilities for the lifting and carrying of the materials. The two principal methods of scaffolding are known respectively as the North and South country systems. The Northern, as indicated by the name, was at one time in use only in Scotland and the north of England, but its many advantages, more especially for the transport of material, have now caused it to become general throughout the country. The second method is essentially the South country system, and is of greater use when power is not necessary for the construction of the building. A combination of both methods is commonly seen and found useful in practice. In scaffolding, the vertical timbers are known as standards or uprights. The horizontal timbers between the standards are known as ledgers when of cylindrical section, but as transoms and runners when of rectangular section. Braces, shores, struts, and ties of any section are pieces used to stiffen the structure. The put-logs, or joists, as they are called when of greater length, carry the boards which form the working platform. The Northern System. This scaffolding can be divided into two parts. First, the derrick staging from which the transporting power acts, and second, the platforms which bring the workmen within reach of their work. Derrick stagings. These stagings, also known as Scotch derricks and Scotchmen, are erected to carry the power required, usually a steam crane. They consist of 3 or 4 timber towers or legs supporting a platform upon which the crane stands. The number of legs depends upon the area over which the power is required to act. When one crane is to be erected, 3 legs are sufficient to carry the platform. If the building is a large one, several such stagings may be constructed, but in some cases 2 cranes are required where the size of the building will not allow of 2 stagings. In these cases, the platform is square and supported at each angle by a leg. The cranes are then fixed diametrically opposite each other. In determining the position of the legs, they must be placed where the effective range of the crane is most required, and also where they will cause the least possible obstruction to the progress of the building. The position of the tower that carries the crane, and which is known as the principal or king leg, is first fixed. The secondary or queen legs are set out from it in the form of an isosceles triangle. The distance between the king and queen legs depends upon the length of the sleepers. These run from below the engine to the lower ends of the guys and average from 25 to 30 feet in length. The legs, especially the king legs, if intended to rise from the earth, must have a foundation of 2 thicknesses of 3-inch timbering laid crosswise. This is unnecessary if there is a concrete or other solid foundation. Apart from the necessity for any foundation, the standard should rise from a framework of bulk timbers of about 12 inches by 12 inches, laid on the ground and halved at their intersection. Figure 1. In the case of the queen legs, an extra bulk is placed under the framework, as shown in Figure 1. The legs are from 6 to 10 feet square on plan, the king legs being the larger. Each leg comprises 4 standards, either of whole timbers or battens bolted together. The standards for the king legs should measure not less than 9 inches by 9 inches. If of battens, then 3 pieces, 9 inches by 3 inches, should be used. For the queen legs, balks 7 inches by 7 inches, or 3 pieces 7 inches by 2.5 inches, are sufficient sectional area. Where battens are used, they are given a lap equal to 1/3 of their full length, and are bolted together by 3/4 inch wrought iron bolts. Whole timbers are used when they can be obtained in one piece of sufficient length. As the standards rise, they are divided into bays by transoms. These are made out of about 9 inches by 3 inches deals, placed from about 6 to 10 feet apart. The bays are triangulated by cross braces, 7 inches by 2.5 inches. Both of these are usually placed on the outside of the bay, but one or both may be placed on the inside. The first method is the better, as these braces, by butting against the transoms, give an increased resistance to movement. The king leg, having to carry the weight of the engine, requires greater strength. This is gained by running an extra standard up the center of the leg. If it is whole timber, bulks about 14 inches by 14 inches are required. If built up, 4 deals 16 inches by 4 inches are used. It should stand upon an extra bulk laid with the horizontal framing at the bottom of the leg, and should rest on a solid foundation. To prevent any tendency to flexure, this extra standard should be strutted from all 4 of the outer standards behind each transom. See Figure 2. Another method is to shore the central standard from the foundation, as in Figure 3. The legs in this manner can be made to support a platform up to 120 feet in height. The required height having been reached, the legs are connected by trussed beams in the following manner. 2 bulk timbers of about 12 inches by 8 inches are laid immediately above each other, between the king leg and each queen leg, resting on the 2 top transoms, as shown in Figure 1. They are from 6 to 9 feet apart, the top bay being sometimes made slightly lower than the others. The lower bulks are connected to the center standard of the king leg by wrought iron straps. The top bulks project from 6 to 10 feet beyond the king leg and are halved at their point of intersection. The projecting ends are connected to each other by pieces 8 inches by 6 inches, and again to the return bulk by similar pieces. See Figure 4. They are also supported by struts from the central standard, as shown in Figure 1. The upper and lower balks are connected by iron bolts about 10 feet apart, and each bay thus formed is cross-braced in the same manner as the legs. The iron bolts are covered by pieces of the same scantling as the braces. In the single derricks, the queen legs can be connected by a trussed beam similarly formed, or by a single balk carried across and laid on the top transom. If the span is considerable, struts can be carried from the queen legs towards the center of the underside of the balk to prevent sagging. On the trussed beams thus formed, joists of 9 inches by 3 inches or ordinary poles are laid about 3 feet apart. They are laid parallel to one another and in a direction at right angles to the truss or single beam forming the back support of the platform. The center joists are continued to the ends of the balks, which project beyond the king leg. The advantage of having continued the top balks can now be seen, as it gives greater area to the platform immediately round the engine. The boards 9 inches by 1.5 inches are laid at right angles to the joists. Another way of forming the platform is to cover only partially the surface between the legs. In this case, 2 additional joists, 6 inches by 6 inches, are thrown across the king leg. See Figure 4. The boards not extending beyond their length. When this is done, the workmen reach the platform from the communicating ladder, which usually passes up a queen leg, by means of a run 2 boards wide. It is better to lay the larger platform, as, apart from the question of safety to the men, it serves as a storage for coal for the engine, the weight of which tends to keep the erection steady. Double boards should be laid under coals or other heavy stores. To reach the platform, ladders are fixed in different ways. They can run up inside or be fixed to the outside of the queen legs. In either case, they are nearly or entirely upright. A better method is shown in Figure 5 and should be carried out wherever possible. The derrick sleepers, 2 in number, are of balk timber and lie across the platform from beneath the engine bed, to which they are connected, to the center of the queen legs. The guys or stays, also of balk timbers, besides being connected to the mast, are attached to the sleepers over the queen legs. See Figure 1. To counteract the overturning force exerted by the jib and the material lifted, the guys are chained down to the timber balk at the bottom of the queen legs. Figure 1. This balk supports a platform which is loaded with bricks or stones more than equal to double the weight that will be lifted. The chain, which works loose with the vibration of the scaffold, is tightened by means of a screw coupler fixed in its length. The arrangement is as follows. 2 lengths of heavy chain with large links at each end are required. 1 length is carried round the sleeper and then taken down the center of the leg. The other length is taken round the balk, which is placed underneath the staging, and carried up through the load, when the tightening screw can be applied and the correct tension brought up. To prevent lateral motion, the legs are cross-braced by poles or deals between each leg, as shown on frontispiece. The poles are tied to the legs just beneath the platform and connected at their meeting point. When crossing, they should be at right angles to each other. Deals 9 inches by 3 inches can take the place of the poles if required, bolts in this case being used instead of tyings. At the building of the new post office, Leeds, 1893, a different method of raising the platform for the crane was adopted. The legs, instead of being framed, consisted of a single balk of timber strutted on each side from the ground level, the sleepers and guys being firmly attached to the standards themselves. When erecting long ranges of buildings, it may be more convenient to have the derrick mounted upon a traveling bogie than to dismantle the structure in order to re-erect at another point. Figure 6 illustrates the system, the traveling power being usually manual. The arrangement is suitable for small derricks and is employed where the crane is erected outside the building. Another method of using traveling cranes is to erect a platform as shown in Figure 7. The standards, which may be of bulk timber or built up as previously shown, are about 10 feet apart longitudinally and 20 to 30 feet transversely. They stand upon sills of the same section where the foundation is not solid. On the head of the standards, the runners are laid connecting all the standards in the same row. Headpieces may be fitted between the standards and runners. This serves to distribute pressure. All the connections are securely made by dog irons, bolts, and straps. The stability depends entirely upon the bracing, and this, it is important to note, should be between each bay longitudinally and at least every second bay transversely. Timbers placed as A in Figure 7 give rigidity to the standards by preventing flexure, and are necessary when the lengths of the uprights exceed 30 times their least diameter. The deals used for braces are bolted to the standards. For poles, tying is resorted to. Working platforms. The working platforms used in conjunction with overhead or overhand work depend upon the requirements of the building. By overhead or hand work is meant that the material upon which the mechanic is to be employed reaches him from overhead or hand. When no outside scaffolding is needed, the platforms are laid upon the floor joints in the interior of the building, being raised upon trestles as the work proceeds and until the next floor is reached. Light forms of scaffolds, as the ordinary masons' and bricklayers' pole scaffolds, are now frequently used as working platforms in connection with the Scotch system, the South Country system. This system is divided into two classes according to the strength required. For the first, square timbers are used. For the second, poles are employed. The scaffolds built of square timbers are known as gantries and stagings, and the pole erections are termed bricklayers and masons or independent scaffolds. Gantries. The term gantry was originally given to erections constructed with a view to the easy carriage of heavy material, but of late it has also come to mean a structure arranged to support lighter forms of scaffolding over footpaths which have to be kept open for public use. First, gantries for transport of material, commonly called travelers. Figures 8 and 8a show the general construction. The distance between the outer rows of standards and the wall depends upon circumstances. If possible, the space should be allowed for a cartway, as the material can thus be brought quite close to the work before being lifted. If, owing to adjacent footpaths or any other reason, this cannot be done, the upright should be placed close to the wall on either side, the material being lifted at the end of the gantry or other convenient spot, over which the lifting gear can be brought. The standards of square timber for the gantry are from 6 inches to 12 inches square and are erected upon sleepers, or, as they are sometimes termed, sills laid in the same direction as the run of the scaffold. 1 row of standards is placed on each side of the wall. The standards are placed 8 to 10 feet apart. On the top of the standards, runners are fixed, connecting each standard in the same row. Sills, standards, and runners should be of the same sectional area. The runners are strutted on their underside from the standards by pieces of, at least, half the sectional area of the supported timbers. If the struts are of equal size to the runners, double the weight can be carried. The cleats from which the struts rise are simply spiked to the standards, but if designed to carry excessive weights, they are slightly housed in. As the space between each row of standards has to be kept open for the building, no cross-bracing can be allowed except at the ends. Strutting is therefore resorted to in order to give stability. The struts, 1 to each standard, are bolted to the upright near the top and again to a foot block driven into the ground. Other methods of fastening down the bottom ends of the struts are shown in Figure 9. The use of each depends upon the nature of the soil. Struts are also fixed at the ends to prevent lateral movement. Headpieces, or corbels, as they are sometimes termed, are occasionally inserted between the standards and runners and serve to distribute pressure. Straining pieces spiked on the underside of the runners for the struts to pitch against are used when the standards are considerably apart. Rails upon which the traveling engine or traveler can move are laid on top of the runners and are turned up at the ends of the platform to serve as buffers to the engine platform. The engine platform consists of 2 trussed beams of timber about 3 feet apart, connected at their ends with short pieces of the same scantling, and fitted with grooved wheels to move upon the rails. Rails are also laid upon each beam and serve for the traversing motion of the crab. Movement of the traveler is obtained from the crab, which is worked either by manual or steam power, and acts through a system of shafting and geared wheels. Movement in 3 directions is necessary from the crab: vertically for lifting, and horizontally in 2 directions, transversely and longitudinally. Travelers are made up to 50 feet wide and any required length. Another method of building travelers is shown in Figure 10. In this case, the rails upon which the traveler moves in a longitudinal direction are fixed on sleepers on the ground level, and the standards and runners of the first example are not required. In their place is constructed a triangulated system of bulk timber framing. The platform is fixed to the headpieces and is braced as shown. Less timber is used in their construction, but owing to the greater weight, a steam winch is required to impart motion. Gantries which serve as a base for lighter forms of scaffolding. These erections are in reality elevated platforms and allow of a clear way for a footpath where required. They are constructed of 2 frames, placed apart according to the width of the path over which the platform stands. Figure 11. The method of erection, so far as the side frames are concerned, is the same as for the first example of traveling gantries. Stability is, however, gained by cross-bracing, as shown in figure, thus making strutting unnecessary. The platform can be laid by placing short boards 9 inches by 3 inches across the runners when the platform is narrow. It is more usual, however, to place joists 10 inches by 2 inches across, and on these to lay the boards longitudinally. The joists average 2 to 3 feet apart. The braces are about 2 inches by 7 inches. On the outside of the scaffold, parallel to the sills, bulk timbers are placed, forming a fender to prevent the vehicular traffic from injuring or disturbing the erection. Stagings. Stagings are erected in a manner similar to traveling gantries, but are carried more than 1 story high. Figure 12. It is a form of scaffolding rarely seen, more especially since the introduction of the Scotch derrick system. The timbers are erected to the height of the first runner in the same manner as the frames in Figure 11. In order to carry the scaffold higher, horizontal pieces are laid across the scaffold over the standards and are made to project 9 or 10 feet on each side of the runners. On these beams, uprights, as in the first tier, are raised, being connected in like manner longitudinally by transoms. The rising tiers of standards are strutted by timbers AA, rising from the projecting portion of the beam called the footing piece, which serves in the same manner as a footing block. The footing piece is supported by struts BB, rising from the lower standards. The struts BB are in 2 pieces, being bolted to the sides of the footing pieces and uprights. This allows the shores AA to pass between them. Strutting within the bays formed by the standards is carried out on each tier with the exception of the top, where braces are fixed, as shown at C. On the top runners, rails are laid for a traveler. In constructing the foregoing square timber erection, note should be taken of the following points: that the uprights of the upper tiers should stand immediately over those of the lower tiers in order to prevent cross strains on the runners; that the timber should fit as evenly as possible, as thereby the whole erection is rendered more stable; that joints between the runners should occur immediately over the standards. The several parts of the structure, if for temporary purposes, can be connected by dog irons, if for a more permanent use, by bolts and straps. Pole scaffolds. Bricklayer scaffolds. A bricklayer scaffold consists of a series of upright poles or standards, to which are lashed horizontal poles termed ledgers. The ledgers and the wall of the building carry the put logs, on which boards are laid to support the workman, his material, and tools. Figure 13. The standards are first erected and may stand singly or in pairs. In a repairing job, unless of great height, and where there is no great weight of material, single poles are sufficient. Where double poles are required, the first pair are erected of different lengths. The short pole is termed a puncheon. The difference of length allows of a lap in connecting the succeeding poles. The lap should equal half of the full-length pole. The standards are placed 6 to 8 feet apart and from 4 to 6 feet away from the building. The butt ends are embedded about 2 feet in the ground, which affords some resistance to overturning. If they cannot be embedded, They should be placed on end in barrels filled with earth, tightly rammed. As the building rises, additional poles are added, being lashed to the standards already erected. If the standard is a single pole, the second pole, having a lap of 10 or 15 feet, stands upon a put log placed close to the first pole for that purpose. Figure 14. The inner end of the put log is securely fastened down to the scaffold or inserted into the building. If the standard is double, the rising pole is placed upon the top end of the puncheon, and afterwards others are placed on end upon the lowest free end of the standards already fixed. As the standards rise, they are spliced or married together with band ties. At a height of 5 feet, this distance being the greatest at which a man can work with ease, a ledger is tied across the standards to form a support for the working platform. Where a single pole is insufficient in length to form a continuous ledger, two are joined in one of 3 ways. In the first, they are lapped over each other as figure 15. This method gives a strong connection, but prevents the put logs being laid evenly. The second way provides that the ledgers shall lap horizontally side by side. This allows of evenness of line for the put logs, but is not so strong. Figure 16. In both of these methods, the lap should cover 2 standards, and not as shown in figure 17. The third manner of connection, figure 18, is the best. The ledgers butt end to end. Underneath, a short pole is placed crossing 2 standards. The tying at the standard embraces the double ledger. A band tie is run round the supporting pole and the ends of the ledgers where they butt. Great strength is obtained in this way, and the put logs can be evenly laid. Additional ledgers are fixed as the work proceeds. On the ledgers, and at right angles to them, put logs are laid, resting outwardly on the ledgers and inwardly on the wall, where header bricks have been left out for their reception. The put logs, which are placed about 3 or 4 feet apart, should be tied to the ledgers and fastened by wedges into the wall. This is not often done, but at least 1 put log to every tying between standard and ledger should be so treated. Where the put logs cannot be carried by the wall, owing to an aperture in the building, such as a window, they are supported by bearers fixed as shown in figures 19 and 20. By wedging the inner end of the put log into the wall, some stability is given to the scaffold, but the connection cannot be considered satisfactory, as the put log would draw under very little strain. Greater stability can be gained if the outer frame of the scaffold is supported by one of the 3 methods given, as follows. A shore or tie can be fixed between the erection and the ground, as shown in figure 21. Or, if there are openings in the wall, supports can be fixed as ties, shown in the same diagram. The ties or struts should be placed to every 3rd or 4th standard at about 25 feet from the ground, and their fastenings made good. Additional ties should be carried within the building at a greater height where possible. The stability of the scaffold under loads and crosswind pressure depends greatly upon the ties or shores, and their fastening should be well made and kept in good order. The historical instance of the mechanic who, to escape a shower of rain, stood upon the inner board of the platform, and by leaning against the building, pushed the scaffold over, should have no opportunity of recurrence. To stiffen the scaffold longitudinally, braces are tied on the outside of the scaffold in the form of a St. Andrew's cross. See Figure 13. They start from the lower end of one standard and rise obliquely across the scaffold to near the top, or some distance up a standard in the same run. Tied at their crossing point, connections are made to all the main timbers of the scaffold with which they come in contact. Braces are fixed in all exposed situations, and generally where the scaffold is more than one pole, 30 feet in height. The only exception to effective bracing being carried out is where the building, being of irregular form, creates many breaks and returns in the scaffolding. It is obvious that where a scaffold butts against or breaks with a return wall, the tendency to lateral motion is lessened. The boards, which are placed longitudinally across the put logs, can be laid to lap or butt at their ends. When lapping, one put log only is required to carry the ends of two series of boards, Figure 22. When butting, 2 put logs are required, placed about 4 inches apart, Figure 23. The second method is the better, as the boards are not so likely to lose their place or to trip the workmen. If heavy work is in progress, the boards are laid double. As the building rises, the boards are carried up to each successive platform, but each tied put log is left in its place. Mason scaffolds. Masons, or independent scaffolds, differ from the bricklayers in that they have to be self-contained. Owing to the different material of which the building is erected, the put logs cannot rest upon the wall. If openings were left for them, as in brickwork, the wall would be permanently disfigured, more especially when ashlar fronted. In order to gain the necessary support, 2 parallel frames of standards and ledgers are erected along the line of wall to be built, Figure 24. They are from 4 to 5 feet apart, the inner frame being as close to the wall as possible. As a heavier material has to be dealt with, the standards are placed closer together, say from 4 to 5 feet. The ledgers and braces are placed as before, the put logs now resting on ledgers at each end, and not on the wall at the innermost end, as in the bricklayer's scaffold. To prevent cross-movement of the scaffold, an additional method of bracing is available in this system. An inner and outer standard are connected by short braces across each bay, as shown in Figure 24. This method of cross-bracing can be continued to the top of the scaffold, and the braces should be put in longitudinally, about 20 feet apart. The platforms laid on all pole scaffolds are from 4 to 5 feet wide. It is usually necessary, on anything but the smallest jobs, to keep this width free for the workman and his material. In order, therefore, to provide a platform on which the material can be landed, it is convenient to erect, on the outside of the scaffold, an additional platform from 5 to 10 feet square, Figure 25. It is constructed of standards, ledgers, and braces, in like manner as the scaffold to which it is attached. The face boards, as shown in this figure, should be fixed wherever material is being hoisted to prevent any projection of the load catching under a ledger and upsetting. Connections. The members of pole scaffolds are connected by cordage. The names of the various knots are given in Chapter 5. The arranging of the various timbers used in erecting scaffolds is a dangerous occupation, and one requiring skill and considerable nerve on the part of the workman. In the majority of cases, the timbers on the ground level are placed in position by manual labor only, sheer legs being used to facilitate matters. When the scaffold rises, advantage is taken of any rigid member on which pulley wheels can be hung, and by this means the succeeding poles, etc., are raised, manual dexterity and strength being responsible for their final position. Chapter 2. Scaffolds for Special Purposes. When applying the given methods for scaffolding, difficulties arise owing to the varying designs of the buildings under construction or repair. It is impossible to deal with these cases in detail. They must be left to the scaffolder who, while holding closely to the principles, by the exercise of ingenuity, will make combinations and variations of the various systems to suit the special requirements demanded in each case. There are, however, certain types of scaffolding which occur with some regularity, and these will now be dealt with. Needle scaffolding. Needle scaffolding is necessary where it is impossible or too expensive to carry the scaffold from the ground level or other solid base. It is used both for repairing and new erections. The needles from which the scaffold takes its name are timbers, usually poles or balks, placed horizontally through and at right angles, or nearly so, to the wall of the building. The projections support a platform upon which an ordinary pole scaffold is erected. Figure 26. Windows or other openings in the wall are utilized, where possible, for the poles to pass through. In other cases, holes have to be made in the walls, cut as nearly as can be to the size of the needles in use. The needles must be of sufficient scantling to carry the weight of the scaffold and attendant loads. The stability of the structure depends upon the means taken to fasten down the inner end of the needle. The usual plan is to tie it down to a convenient joist or other rigid member of the building itself, but the method shown on the diagram is better, as resistance to movement is gained both from above and below. Struts from the building below the needles to their outer end give greater strength to the beam. When erecting needle scaffolding around buildings of small area, say of a tower or chimney shaft, the needles can be laid across the building in one length, piercing the wall on opposite sides. In these cases, if the needles are wedged in, the weight of the building and the scaffold itself on the opposite ends of the needles is sufficient to maintain equilibrium. The platform is formed of 9 inches by 3 inches deals, and on this is erected whatever scaffolding may be necessary. Scaffolds for chimney shafts, towers, and steeples. The erection of chimney shafts can be carried on entirely by the aid of internal scaffolding. As the work rises, put logs are laid across the shaft, the ends being well built into the wall. On the put logs, the platform is laid, being carried up as the work proceeds. The put logs may be left in for the time and struck on completion. The platform is fitted in its center with a hinged flap door through which the material is hoisted as required. There is some objection to this method of scaffolding where the wall is more than 1 foot 10.5 inches thick, which is the greatest depth of brickwork over which a man can reach and do finished work, for the mechanics, in order to reach the outside joints, have to kneel on the freshly laid material, which is detrimental to good workmanship. For this reason, the system of carrying up an ordinary pole scaffold externally until the height is reached where the wall is reduced to 1 foot 10.5 inches in thickness is to be preferred. The walls of a chimney shaft decrease in thickness 4.5 inches at a time, forming an internal setback of that width at every 20 feet in height. This setback is of advantage to internal scaffolding when the full height of the brickwork is reached and the cap has to be fixed. The cap, or coping, when of stone or iron, does not admit of the insertion of put logs. To overcome the difficulty, 4 or more standards are erected at equal distances and standing upon the top setback. Figure 27. The standards project sufficiently to carry the pulley wheel well above the total height of the chimney in order to give headroom and to assist the workman in fixing the coping. To stiffen the standards, short ledgers are tied across as shown in Figure 27. End of Section 1. Section 2 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Electricity for the Farm. Light, Heat, and Power by Inexpensive Methods from the Water Wheel or Farm Engine. By Frederick Irving Anderson, author of The Farmer of Tomorrow, etc., etc. New York, The Macmillan Company, 1915. All rights reserved. Copyright 1915 by the Curtis Publishing Company, The Country Gentleman. Copyright 1915 by the Macmillan Company. Set up and electrotyped. Published April 1915. Preface. This book is designed primarily to give the farmer a practical working knowledge of electricity for use as light, heat, and power on the farm. The electric generator, the dynamo, is explained in detail, and there are chapters on electric transmission and house wiring by which the farm mechanic is enabled to install his own plant without the aid and expense of an expert. With modern appliances, within the means of the average farmer, the generation of electricity, with its unique conveniences, becomes automatic, provided some dependable source of power is to be had, such as a water wheel, gasoline, or other form of internal combustion engine, or the ordinary windmill. The water wheel is the ideal prime mover for the dynamo in isolated plants. Since water power is running to waste on tens of thousands of our farms throughout the country, several chapters are devoted to this phase of the subject. These include descriptions and working diagrams of weirs and other simple devices for measuring the flow of streams. There are tables and formulas by which anyone with a knowledge of simple arithmetic may determine the power to be had from falling water under given conditions. And in addition, there are diagrams showing in general the method of construction of dams, bulkheads, races, flumes, etc., from materials usually to be found on a farm. The tiny unconsidered brook that waters the farm pasture frequently possesses power enough to supply the farmstead with cool, clean, safe light in place of the dangerous, inconvenient oil lamp. A small stream capable of developing from 25 to 50 horsepower will supply a farmer, at practically no expense beyond the original cost of installation, not only with light, but with power for even the heavier farm operations as threshing, and in addition will do the washing, ironing, and cooking, and at the same time keep the house warm in the coldest weather. Less than 1 horsepower of energy will light the farmstead. Less than 5 horsepower of energy will provide light and small power and take the drudgery out of the kitchen. For those not fortunate enough to possess water power which can be developed, there are chapters on the use of the farm gasoline engine and windmill in connection with the modern storage battery as sources of electric current. It is desired to make acknowledgement for illustrations and assistance in gathering material for the book to the editors of the Country Gentleman, Philadelphia, Pennsylvania, the Crocker Wheeler Company, Ampere, New Jersey, the General Electric Company, Schenectady, New York, the Weston Electrical Instrument Company of Newark, New Jersey, the Chase Turbine Manufacturing Company, Orange, Massachusetts, the C.P. Bradway Machine Works, West Stafford, Connecticut, the Pelton Water Wheel Company, San Francisco and New York, the Ward Leonard Manufacturing Company, Bronxville, New York, the Fairbanks Morse Company, Chicago, and the Fitz Water Wheel Company, Hanover, Pennsylvania. Introduction. The sight of a dozen or so fat young horses and mares feeding and frolicking on the wild range of the Southwest would probably inspire the average farmer as an awful example of horsepower running to waste. If, by some miracle, he came on such a sight in his own pastures, he would probably consume much time practicing the impossible art of creasing the wild creatures with a rifle bullet, after the style of Kit Carson and other free rovers of the old prairies when they were in need of a new mount. He would probably spend uncounted hours behind the barn learning to throw a lariat, and one fine day he would sally forth to capture a horsepower or two, and once captured, he would use strength and strategy, breaking the wild beast to harness. A single horsepower animal will do the work of lifting 23,000 pounds 1 foot in 1 minute, providing the animal is young and sound and is fed 12 quarts of oats and 10 or 15 pounds of hay a day, and is given a chance to rest 16 hours out of 24, providing also it has a dentist to take care of its teeth occasionally, and a blacksmith chiropodist to keep it in shoes. On the hoof, this horsepower is worth about $200, unless the farmer is looking for something fancy in the way of drafters, when he will have to go as high as $400 for a big fellow. And after 10 or 15 years, the farmer would look around for another horse because an animal grows old. This animal horsepower isn't a very efficient horsepower. In fact, it is less than 3/4 of an actual horsepower, as engineers use the term. A real horsepower will do the work of lifting 33,000 pounds 1 foot in 1 minute, or 550 pounds 1 foot in 1 second. Burn a pint of gasoline with 14 pounds of air in a gasoline engine, and the engine will supply 1 33,000-pound horsepower for an hour. The gasoline will cost about 2 cents, and the air is supplied free. If it was the air that cost 2 cents a pound instead of the gasoline, the automobile industry would undoubtedly stop where it began some 15 years ago. It is human nature, however, to grumble over this 2 cents. Yet the average farmer, who would get excited if sound young chunks and drafters were running wild across his pastures, is not inspired by any similar desire of possession and mastery by the side of a brook or a rivulet that waters his meadows. This brook or river is flowing downhill to the sea. Every 4,000 gallons that falls 1 foot in 1 minute, every 400 gallons that falls 10 feet in 1 minute, or every 40 gallons that falls 100 feet in 1 minute, means the power of 1 horse going to waste. Not the $200 flesh and blood kind that can lift only 23,000 pounds a foot a minute, but the 33,000 foot-pound kind. Thousands of farms have small streams in their very dooryard, capable of developing 5, 10, 20, 50 horsepower 24 hours a day for the greater part of the year. Within a quarter of a mile of the great majority of farms outside of the dry lands themselves, there are such streams. Only a small fraction of 1% of them have been put to work, made to pay their passage from the hills to the sea. The United States Government Geological Survey engineers recently made an estimate of the waterfalls capable of developing 1,000 horsepower and over that are running to waste, unused in this country. They estimated that there is available, every second of the day and night, some 30 million horsepower in dry weather, and twice this during the 8 wet months of the year. The waterfall capable of giving up 1,000 horsepower in energy is not the subject of these chapters. It is the small streams, the brooks, the creeks, the rivulets, which feed the 1,000 horsepower torrents, make them possible, that are of interest to the farmer. These small streams thread every township, every county, seeking the easiest way to the main valleys where they come together in great rivers. What profitable crop on your farm removes the least plant food? A bee farmer enters his honey for the prize in this contest. Another farmer maintains that his ice crop is the winner. But electricity generated from falling water of a brook meandering across one's acres comes nearer to the correct answer of how to make something out of nothing. It merely utilizes the wasted energy of water rolling downhill. The weight of water, the pulling power of gravity. Water is still water after it has run through a turbine wheel to turn an electric generator. It is still wet. It is there for watering the stock, and a few rods further downstream, where it drops 5 or 10 feet again, it can be made to do the same work over again, and over again, as long as it continues to fall on its journey to the sea. The city of Los Angeles has a municipal water plant generating 200,000 horsepower of electricity, in which the water is used 3 times in its fall of 6,000 feet. And in the end, where it runs out of the race in the valley, it is sold for irrigation. 1 water horsepower will furnish light for the average farm. 5 water horsepower will furnish light and power and do the ironing and baking. The cost of installing a plant of 5 water horsepower should not exceed the cost of 1 sound young horse, the $200 kind, under conditions which are to be found on thousands of farms and farm communities in the East, the Central West, and the Pacific States. This electrical horsepower will work 24 hours a day, winter and summer, and the farmer would not have to grow oats and hay for it on land that might better be used in growing food for human beings. It would not become aged at the end of 10 or 15 years, and the expense of maintenance would be practically nothing after the first cost of installation. It would require only water as food, wastewater. 250 cubic feet of water a minute, falling 10 feet, will supply the average farm with all the conveniences of electricity. This is a very modest creek, the kind of brook or creek that is ignored by the man who would think time well spent in putting in a week capturing a wild horse, if a miracle should send such a beast within reach. And the task of harnessing and breaking this water horsepower is much more simple and less dangerous than the task of breaking a colt to harness. Part 1. Water Power. Chapter 1. A Working Plant. The dynamo, a direct current machine, 110 volts pressure, and what is known in the trade as compound, that is, a machine that maintains a constant pressure automatically and does not require an attendant, was picked up second-hand through a newspaper ad and cost $90. The switchboard, a makeshift affair, not very handsome, but just as serviceable as if it were made of marble, cost less than $25 all told. The transmission wire cost $19 a 100 pounds. It is of copper and covered with weatherproofed tape. Perkins bought a 50-cent book on house wiring and did the wiring himself, the way the book told him to, a simple operation. For fixtures, as we have said, his wife devised fancy shades out of Mexican baskets, tissue paper, and silk, in which are hidden electric globes that glow like fireflies at the pressing of a button. The lamps themselves are mostly old-style carbon lamps, which can be bought at 16 cents each, retail. In his living room and dining room, he used the new-style tungsten lamps instead of old-style carbon. These cost 30 cents each. Incandescent lamps are rated for 1,000 hours useful life. The advantage of tungsten lights is that they give 3 times as much light for the same expenditure of current as carbon lights. This is a big advantage in the city, where current is costly, but it is not so much of an advantage in the country, where a farmer has plenty of water power, because his current costs him practically nothing, and he can afford to be wasteful of it to save money in lamps. Another advantage he has over his city cousin. In town, an incandescent lamp is thrown away after it has been used 1,000 hours, because after that it gives only 80% of the light it did when new. Quite an item when one is paying for current. The experience of Perkins and his neighbor in their cooperative plant has been that they have excess light anyway, and if a few bulbs fall off a fifth in efficiency, it is not noticeable. As a matter of fact, most of their bulbs have been in use without replacing for the 2 years the plant has been in operation. The lamps are on the wall or on the ceiling, out of the way, not liable to be broken. So the actual expense in replacing lamps is less than for lamp chimneys in the old days. Insurance companies recognize that a large percentage of farm fires comes from the use of kerosene. For this reason, they are willing to make special rates for farm homes lighted by electricity. They prescribe certain rules for wiring a house, and they insist that their agent inspect and pass such wiring before current is turned on. Once the wiring is passed, the advantage is all in favor of the farmer with electricity over the farmer with kerosene. The National Board of Fire Underwriters is sufficiently logical in its demands and powerful enough so that manufacturers who turn out the necessary fittings find no sale for devices that do not conform to insurance standards. Therefore, it is difficult to go wrong in wiring a house. Finally, As to the added value a water power electric plant adds to the selling price of a farm, let the farmer answer this question for himself. If he can advertise his farm for sale with the paragraph running, "Hydroelectric plant on the premises, furnishing electricity for light, heat, and power," what do you suppose a wide-awake purchaser would be willing to pay for that? Perkins and his neighbor believe that $1,000 is a very modest estimate added by their electric plant to both places, and they talk of doing still more. They use only a quarter of the power of the water that is running to waste through the wheel. They are figuring on installing a larger dynamo of, say, 30 electrical horsepower, which will provide clean, dry, safe heat for their houses, even on the coldest days in winter. When they have done this, they will consider that they are really putting their small river to work. Chapter 2. A little prospecting. The average farmer makes the mistake of considering that one must have a river of some size to develop power of any practical use. On your next free day, do a little prospecting. We have already said that 250 cubic feet of water, falling 10 feet a minute, will provide light, heat, and small motor power for the average farm. A single water horsepower will generate enough electricity to provide light for the house and barn. But let us take 5 horsepower as a desirable minimum in this instance. In your neighborhood, there is a creek 3 or 4 feet wide, toiling along day by day at its task of watering your fields. Find a wide board a little longer than the width of this creek you have scorned. Set it upright across the stream between the banks so that no water flows around the ends or under it. It should be high enough to set the water back to a dead level for a few feet upstream before it overflows. Cut a gate in this board, say 3 feet wide and 10 inches deep, or according to the size of a stream. Cut this gate from the top so that all the water of the stream will flow through the opening and still maintain a level for several feet back of the board. This is what engineers call a weir, a handy contrivance for measuring the flow of small streams. Experts have figured out an elaborate system of tables as to weirs. All we need to do now, in this rough survey, is to figure out the number of square inches of water flowing through this opening and falling on the other side. With a rule, measure the depth of the overflowing water from the bottom of the opening to the top of the dead level of the water behind the board. Multiply this depth by the width of the opening, which will give the square inches of water escaping. For every square inch of this water escaping, engineers tell us that stream is capable of delivering roughly 1 cubic foot of water a minute. Thus, if the water is 8 inches deep in an opening 32 inches wide, then the number of cubic feet this stream is delivering each minute is 8 times 32, or 256 cubic feet a minute. So, a stream 32 inches wide, with a uniform depth of 8 inches running through our weir, is capable of supplying the demands of the average farm in terms of electricity. Providing, of course, that the lay of the land is such that this water can be made to fall 10 feet into a water wheel. Go upstream and make a rough survey of the fall. In the majority of instances, unless this is some sluggish stream in a flat prairie, it will be found feasible to divert the stream from its main channel by means of a race, an artificial channel, and to convey it to a not far distant spot where the necessary fall can be had at an angle of about 30 degrees from horizontal. If you find there is twice as much water as you need for the amount of power you require, a 5-foot fall will give the same result. Or, if there is only 1/2 as much water as the 250 cubic feet specified, you can still obtain your theoretical 5 horsepower if the means are at hand for providing a fall of 20 feet instead of 10. Do not make the very common mistake of figuring that a stream is delivering a cubic foot a minute to each square inch of weir opening simply because it fills a certain opening. It is the excess water falling over the opening after the stream is set back to a permanent dead level that is to be measured. This farmer who spends an idle day measuring the flow of his brook with a notched board may say here, "This is all very well. This is the spring of the year, when my brook is flowing at high water mark. What am I going to do in the dry months of summer, when there are not 250 cubic feet of water escaping every minute?" There are several answers to this question, which will be taken up in detail in subsequent chapters. Here, let us say, even if this brook does flow in sufficient volume only 8 months in a year, the dark months, by the way, is not electricity, and the many benefits it provides worth having 8 months in the year. My garden provides fresh vegetables 4 months a year. Because it withers and dies and lies covered with snow during the winter, is that any reason why I should not plow and manure and plant my garden when spring comes again? A water wheel, the modern turbine, is a circular fan with curved iron blades revolving in an iron case. Water, forced through the blades of this fan by its own weight, causes the wheel to revolve on its axis, and the fan in turn causes a shaft fitted with pulleys to revolve. The water, by giving the iron-bladed fan a turning movement as it rushes through, imparts to it mechanical power. The shaft set in motion by means of this mechanical power is, in turn, belted to the pulley of a dynamo. This dynamo consists, first, of a shaft on which is placed a spool, wound in a curious way, with many turns of insulated copper wire. This spool revolves freely in an air space surrounded by electric magnets. The spool does not touch these magnets. It is so nicely balanced that the weight of a finger will turn it. Yet, when it is revolved by water power at a predetermined speed, say 1,500 revolutions a minute, it generates electricity, transforms the mechanical power of the water wheel into another form of energy, a form of energy which can be carried for long distances on copper wires, which can, by touching a button, be itself converted into light or heat or back into mechanical energy again. If 2 wires be led from opposite sides of this revolving spool, and an electric lamp be connected from one to the other wire, the lamp will be lighted, will grow white hot, hence incandescent light. The instant this lamp is turned on, the revolving spool feels a stress. The magnets by which it is surrounded begin to pull back on it. The power of the water wheel, however, overcomes this pull. If 100 lights be turned on, the backward pull of the magnets surrounding a spool will be 100 times as strong as for 1 light. For every ounce of electrical energy used in light or heat or power, the dynamo will require a like ounce of mechanical power from the water wheel which drives it. The story is told of a canny Scotch engineer who, in the first days of dynamos, not so very long ago, scoffed at the suggestion that such a spool, spinning in free air, in well-lubricating bearings, could bring his big coreless steam engine to a stop. Yet he saw it done simply by belting this spool, a dynamo, to his engine and asking the dynamo for more power in terms of light than his steam could deliver in terms of mechanical power to overcome the pull of the magnets. Electricity must be consumed the instant it is generated, except in rare instances where small amounts are accumulated in storage batteries by a chemical process. The pressure of a button or the throw of a switch causes the dynamo instantly to respond with just enough energy to do the work asked of it, always in proportion to the amount required. Having this in mind, it is rather curious to think of electricity as being an article of export, an item in international trade. Yet in 1913, hydroelectric companies in Canada exported, by means of wires, to this country over 772 million kilowatt hours, over 1 billion horsepower hours of electricity for use in factories near the boundary line. This 250 cubic feet of water per minute then, which the farmer has measured by means of his notched board, will transform by means of its falling weight mechanical power into a like amount of electrical power, less friction losses, which may amount to as much as 60% in very small machines, and 15% in larger plants. That is, the brook which has been draining your pastures for uncounted ages contains the potential power of 3 and 4 young horses, with this difference, that it works 24 hours a day, runs on forever, and requires no oats or hay, and the cost of such an electric plant, which is ample for the needs of the average farm, is in most cases less than the price of a good farm horse, the $200 kind, not counting labor of installation. It is the purpose of these chapters to awaken the farmer to the possibilities of such small water power as he or his community may possess, to show that the generating of electricity is a very simple operation, and that the maintenance and care of such a plant is within the mechanical ability of any American farmer or farm boy, and to show that electricity itself is far from being the dangerous, death-dealing fluid of popular imagination. Electricity must be studied, and then it becomes an obedient, tireless servant. During the past decade or two, mathematical wizards have studied electricity, explored its atoms, reduced it to simple arithmetic, and although they cannot yet tell us why it is generated, they tell us how. It is with this simple arithmetic and the necessary manual operations that we have to do here. Chapter 3. How to Measure Water Power. If a man were off in the woods and needed a horsepower of energy to work for him, he could generate it by lifting 550 pounds of stone or wood, or what not, 1 foot off the ground, and letting it fall back in the space of 1 second. As a man possesses capacity for work equal to 1/5 horsepower, it would take him 5 seconds to do the work of lifting the weight up that the weight itself accomplished in falling down. All that goes up must come down, and by a nice balance of physical laws, a falling body hits the ground with precisely the same force as is required to lift it to the height from which it falls. The Carthaginians and other ancients, who were deep in the woods as regards mechanical knowledge, had their slaves carry huge stones to the top of the city wall, and the stones were placed in convenient positions to be tipped over on the heads of any besieging army that happened along. Thus, by concentrating the energy of many slaves in one batch of stones, the warriors of that day were enabled to deliver horsepower in one mass where it would do the most good. The farmer who makes use of the energy of falling water to generate electricity for light, heat, and power does the same thing. He makes use of the capacity for work stored in water in being lifted to a certain height. As in the case of the gasoline engine, which burns 14 pounds of air for every pound of gasoline, the engineer of the water power plant does not have to concern himself with the question of how this natural source of energy happened to be in a handy place for him to make use of it. The sun, shining on the ocean and turning water into vapor by its heat, has already lifted it up for him. This vapor, floating in the air and blown about by winds, becomes chilled from one cause or another, gives up its heat, turns back into water, and falls as rain. This rain, falling on land 5, 10, 100, 1,000, or 10,000 feet above the sea level, begins to run back to the sea, picking out the easiest road and cutting a channel that we call a brook, a stream, or a river. Our farmlands are covered to an average depth of about 3 feet a year with water, every gallon of which has stored in it the energy expended by the heat of the sun in lifting it to the height where it is found. The farmer, prospecting on his land for water power, locates a spot on a stream which he calls supply, and another spot a few feet downhill near the same stream which he calls power. Every gallon of water that falls between these 2 points and is made to escape through the revolving blades of a water wheel is capable of work in terms of foot-pounds, an amount of work that is directly proportional to the quantity of water and to the distance in feet which it falls to reach the wheel, pounds and feet, the efficient water wheel. And it is a very efficient form of work, too. In fact, it is one of the most efficient forms of mechanical energy known, and one of the easiest controlled. A modern water wheel uses 85% of the total capacity for work imparted to falling water by gravity, and delivers it as rotary motion. Compare this water wheel efficiency with other forms of mechanical power in common use. Whereas a water wheel uses 85% of the energy of its water supply and wastes only 15%, a gasoline engine reverses the table and delivers only 15% of the energy in gasoline and wastes 85%. And it is rather a high-class gasoline engine that can deliver even 15%. A steam engine, on the other hand, uses about 17% of the energy in the coal under its boilers and passes the rest up the chimney as waste heat and smoke. There is still another advantage possessed by water power over its 2 rivals, steam and gas. It gives the most even flow of power. A gas engine kicks a wheel round in a circle by means of successive explosions in its cylinders. A reciprocating steam engine kicks a wheel round in a circle by means of steam expanding first in one direction, then in another. A water wheel, on the other hand, is made to revolve by means of the pressure of water, by the constant force of gravity itself, weight. Weight is something that does not vary from minute to minute, or from one fraction of a second to another. It is always the same. A square inch of water pressing on the blades of a water wheel weights 10, 20, 100 pounds, according to the height of the pipe conveying that water from the source of supply to the wheel. So long as this column of water is maintained at a fixed height, the power it delivers to the wheel does not vary by so much as the weight of a feather. This property of falling water makes it the ideal power for generating electricity. Electricity generated from mechanical power depends on constant speed for steady pressure, since the electric current when analyzed, is merely a succession of pulsations through a wire, like waves beating against a seawall. Water power delivers these waves at a constant speed, so that electric lights made from water power do not flicker and jump like the flame of a lantern in a gusty wind. On the other hand, to accomplish the same thing with steam or gasoline requires an especially constructed engine, the simple weir. Since a steady flow of water and a constant head bring about this ideal condition in the water wheel, the first problem that faces the farmer prospector is to determine the amount of water which his stream is capable of delivering. This is always measured, for convenience, in cubic feet per minute. A cubic foot of water weighs 62.5 pounds and contains 7.5 gallons. This measurement is obtained in several ways, among which probably the use of a weir is the simplest and most accurate for small streams. A weir is, in effect, merely a temporary dam set across the stream in such a manner as to form a small pond, and to enable one to measure the water escaping from this pond. It may be likened to the overflow pipe of a horse trough which is being fed from a spring. To measure the flow of water from such a spring, all that is necessary is to measure the water escaping through the overflow when the water in the trough has attained a permanent level. The diagrams show the cross-section and detail of a typical weir, which can be put together in a few minutes with the aid of a saw and hammer. The cross-section shows that the lower edge of the slot through which the water of the temporary pond is made to escape is cut on a bevel, with its sharp edge upstream. The wing on each side of the opening is for the purpose of preventing the stream from narrowing as it flows through the opening and thus upsetting the calculations. This weir should be set directly across the flow of the stream, perfectly level and upright. It should be so embedded in the banks and in the bottom of the stream that no water can escape except through the opening cut for that purpose. It will require a little experimenting with a rough model to determine just how wide and how deep this opening should be. It should be large enough to prevent water flowing over the top of the board, and it should be small enough to cause a still water pond to form for several feet behind the weir. Keep in mind the idea of the overflowing water trough when building your weir. The stream, running down from a higher level behind, should be emptying into a still water pond, which in turn should be emptying itself through the aperture in the board at the same rate as the stream is keeping the pond full. Your weir should be fashioned with the idea of some permanency, so that a number of measurements may be taken, extending over a period of time, thus enabling the prospector to make a reliable estimate not only of the amount of water flowing at any one time, but of its fluctuations. Under expert supervision, this simple weir is an exact contrivance, exact enough, in fact, for the finest calculations required in engineering work. To find out how many cubic feet of water the stream is delivering at any moment, all that is necessary is to measure its depth where it flows through the opening. There are instruments, like the hook gauge, which are designed to measure this depth with accuracy up to 1/1000th of an inch. An ordinary foot rule, or a folding rule, will give results sufficiently accurate for the water prospector in this instance. The depth should be measured not at the opening itself, but a short distance back of the opening, where the water is setting at a dead level and is moving very slowly. With this weir, Every square inch of water flowing through the opening indicates roughly 1 cubic foot of water a minute. Thus, if the opening is 10 inches wide and the water flowing through it is 5 inches deep, the number of cubic feet a minute the stream is delivering is 10 times 5 equals 50 square inches equals 50 cubic feet a minute. This is a very small stream, yet if it could be made to fall through a water wheel 10 feet below a pond or reservoir, it would exert a continuous pressure of 30,000 pounds per minute on the blades of the wheel, nearly 1 theoretical horsepower. Another method of measuring a stream. Weirs are for use in small streams. For larger streams, where the construction of a weir would be difficult, the U.S. Geological Survey engineers recommend the following simple method. Choose a place where the channel is straight for 100 or 200 feet and has a nearly constant depth and width. Lay off on the bank a line 50 or 100 feet in length. Throw small chips into the stream and measure the time in seconds they take to travel the distance laid off on the bank. This gives the surface velocity of the water. Multiply the average of several such tests by 0.80, which will give very nearly the mean velocity. Then it is necessary to find the cross-section of the flowing water, its average depth multiplied by width, and this number, in square feet, multiplied by the velocity in feet per second, will give the number of cubic feet the stream is delivering each second. Multiplied by 60 gives cubic feet a minute. Figuring a stream's horsepower. By one of the above simple methods, the problem of quantity can easily be determined. The next problem is to determine what head can be obtained. Head is the distance in feet the water may be made to fall from the source of supply to the water wheel itself. The power of water is directly proportional to head, just as it is directly proportional to quantity. Thus, the typical weir measured above was 30 inches wide and 6 1/4 deep, giving 189 cubic feet of water a minute. Quantity. Since such a stream is of common occurrence on thousands of farms, let us analyze briefly its possibilities for power. 189 cubic feet of water weighs 189 times 62.5 pounds equals 11,812.5 pounds. Drop this weight 1 foot, and we have 11,812.5 foot-pounds. Drop it 3 feet, and we have 11,812 times 3 equals 35,437.5 foot-pounds. Since 33,000 foot-pounds exerted in 1 minute is 1 horsepower, we have here a little more than 1 horsepower. For simplicity, let us call it a horsepower. Now, since the work to be had from this water varies directly with quantity and head, it is obvious that a stream 1/2 as big, falling twice as far, would still give 1 horsepower at the wheel, or a stream of 189 cubic feet a minute, falling 10 times as far, 30 feet, would give 10 times the power, or 10 horsepower. A stream falling 100 times as far would give 100 horsepower. Thus small quantities of water falling great distances, or large quantities of water falling small distances, may accomplish the same results. The size of the wheel. Water wheels are not rated by horsepower by manufacturers, because the same wheel might develop 1 horsepower or 100 horsepower, or even 1,000 horsepower, according to the conditions under which it is used. With a given supply of water, the head, in feet, determines the size of wheel necessary. The farther a stream of water falls, the smaller the pipe necessary to carry a given number of gallons past a given point in a given time. A small wheel, under 10 times 13.5 foot head, would give the same power with the above 376 cubic feet of water a minute as a large wheel would with 10 times 376 cubic feet under a 13.5 foot head. This is due to the acceleration of gravity on falling bodies. A rifle bullet shot into the air with a muzzle velocity of 3,000 feet a second begins to diminish its speed instantly on leaving the muzzle, and continues to diminish in speed at the fixed rate of 32.16 feet a second until it finally comes to a stop and starts to descend. Then again, its speed accelerates at the rate of 32.16 feet a second until on striking the earth it has attained the velocity at which it left the muzzle of the rifle, less loss due to friction. The acceleration of gravity affects falling water in the same manner as it affects a falling bullet. At any 1 second, during its course of fall, it is traveling at a rate 32.16 feet a second in excess of its speed the previous second. In figuring the size wheel necessary under given conditions, or to determine the power of water with a given nozzle opening, it is necessary to take this into account. The table on page 51 gives velocity per second of falling water, ignoring the friction of the pipe in heads from 5 to 1,000 feet. Chapter 4. The Water Wheel and How to Install It. In general, there are 2 types of water wheels, the impulse wheel and the reaction wheel. Both are called turbines, although the name belongs more properly to the reaction wheel alone. Impulse wheels derive their power from the momentum of falling water. Reaction wheels derive their power from the momentum and pressure of falling water. The old-fashioned undershot, overshot, and breast wheels are familiar to all as examples of impulse wheels. Water wheels of this class revolve in the air, with the energy of the water exerted on one face of their buckets. On the other hand, reaction wheels are enclosed in watertight cases, either of metal or of wood, and the buckets are entirely surrounded by water. The old-fashioned undershot, overshot, and breast wheels were not very efficient. They wasted about 75% of the power applied to them. A modern impulse wheel, on the other hand, operates at an efficiency of 80% and over. The loss is mainly through friction and leakage and cannot be eliminated altogether. The modern reaction wheel, called the turbine, attains an equal efficiency. Individual conditions govern the type of wheel to be selected. The impulse or tangential water wheel. The modern impulse or tangential wheel, so called because the driving stream of water strikes the wheel at a tangent, is best adapted to situations where the amount of water is limited and the head is large. Thus, a mountain brook supplying only 7 cubic feet of water a minute, a stream less than 2.5 inches deep flowing over a weir with an opening 3 inches wide, would develop 2 actual horsepower under a head of 200 feet. Not an unusual head to be found in the hill country. Under a head of 1,000 feet, a stream furnishing 352.6 cubic feet of water a minute would develop 534.01 horsepower at the nozzle. Ordinarily, these wheels are not used under heads of less than 20 feet. A wheel of this type, 6 feet in diameter, would develop 6 horsepower with 188 cubic feet of water a minute and 20-foot head. The great majority of impulse wheels are used under heads of 100 feet and over. In this country, the greatest head in use is slightly over 2,100 feet, although in Switzerland there is one plant utilizing a head of over 5,000 feet. The old-fashioned impulse wheels were inefficient because of the fact that their buckets were not constructed scientifically, and much of the force of the water was lost at the moment of impact. The impulse wheel of today, however, has buckets which so completely absorb the momentum of water issuing from a nozzle that the water falls into the tail race with practically no velocity. When it is remembered that the nozzle pressure under a 2,250-foot head is nearly 1,000 pounds to the square inch, and that water issues from this nozzle with the velocity of 23,000 feet a minute, the scientific precision of this type of bucket can be appreciated. A typical bucket for such a wheel is shaped like an open clamshell, the central line which cuts the stream of water into halves being ground to a sharp edge. The curves which absorb the momentum of the water are figured mathematically and in practice become polished like mirrors. So great is the eroding action of water under great heads, especially when it contains sand or silt, that it is occasionally necessary to replace these buckets. For this reason, the larger wheels consist merely of a spider of iron or steel, with each bucket bolted separately to its circumference so that it can be removed and replaced easily. Usually, only one nozzle is provided, but in order to use this wheel under low heads, down to 10 feet, a number of nozzles are used, sometimes 5, where the water supply is plentiful. The wheel is keyed to a horizontal shaft running in babbited bearings, and this same shaft is used for driving the generator, either by direct connection or by means of pulleys and a belt. The wheel may be mounted on a homemade timber base or on an iron frame. It takes up very little room, especially when it is so set that the nozzle can be mounted under the flooring. The wheel itself is enclosed, above the floor, in a wooden box, or a casing made of cast or sheet iron, which should be watertight. Since these wheels are usually operated under great heads, the problem of regulating their water supply requires special consideration. A gate is always provided at the upper or intake end, where the water pipe leaves the flume. Since the pressure reaches 1,000 pounds the square inch and more, there would be danger of bursting the pipe if the water were suddenly shut off at the nozzle itself. For this reason, it is necessary to use a needle valve, similar to that in an ordinary garden hose nozzle, and by such a valve, the amount of water may be regulated to a nicety. Where the head is so great that even such a valve could not be used safely, provision is made to deflect the nozzle. These wheels have a speed variation amounting to as much as 25% from no load to full load in generating electricity, and since the speed of the prime mover, the water wheel, is reflected directly in the voltage or pressure of electricity delivered, the wheel must be provided with some form of automatic governor. This consists usually of 2 centrifugal balls, similar to those used in governing steam engines. These are connected by means of gears to the needle valve or the deflector. As the demand for farm water powers in our hill sections becomes more general, the tangential type of water wheel will come into common use for small plants. At present, it is most familiar in the great commercial installations of the Far West, working under enormous heads. These wheels are to be had in the market, ranging in size from 6 inches to 6 feet and over. Wheels ranging in size from 6 inches to 24 inches are called water motors and are to be had in the market, new, for $30 for the smallest size and $275 for the largest. Above 3 feet in diameter, the list prices will run from $200 for a 3-foot wheel to $800 for a 6-foot wheel. Where one has a surplus of water, it is possible to install a multiple nozzle wheel under heads of from 10 to 100 feet. The cost for 18-inch wheels of this pattern running from $150 to $180 list, and for 24-inch wheels from $200 to $250. A 24-inch wheel with a 10-foot head would give 1.19 horsepower, enough for lighting the home and using an electric iron. Under a 100-foot head, the same wheel would provide 25.9 horsepower to meet the requirements of a bigger than average farm plant. End of Section 2. Section 3 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from the Mechanical Properties of Wood, including a discussion of the factors affecting the mechanical properties and methods of timber testing, by Samuel J. Record, M.A., M.F., Assistant Professor of Forest Products, Yale University. First edition, First Thousand, 1914. To the staff of the Forest Products Laboratory at Madison, Wisconsin, in appreciation of the many opportunities afforded and courtesies extended, the author. Preface. This book was written primarily for students of forestry to whom a knowledge of the technical properties of wood is essential. The mechanics involved is reduced to the simplest terms and without reference to higher mathematics, with which the students rarely are familiar. The intention throughout has been to avoid all unnecessarily technical language and descriptions, thereby making the subject matter readily available to everyone interested in wood. The writer is indebted to the U.S. Forest Service for nearly all of his tables and photographs, as well as many of the data upon which the book is based, since only the government is able to conduct the extensive investigations essential to a thorough understanding of the subject. More than 80,000 tests have been made at the Madison Laboratory alone, and the work is far from completion. The writer also acknowledges his indebtedness to Mr. Emanuel Fritz, M.E., M.F., for many helpful suggestions in the preparation of Part 1, and especially to Mr. Harry Donald Tiemann, M.E., M.F., engineer in charge of timber physics at the Government Forest Products Laboratory, Madison, Wisconsin, for careful revision of the entire manuscript. Samuel J. Record, Yale Forest School, July 1st, 1914. Part 1. The Mechanical Properties of Wood. Introduction. The mechanical properties of wood are its fitness and ability to resist applied or external forces. By external force is meant any force outside of a given piece of material which tends to deform it in any manner. It is largely such properties that determine the use of wood for structural and building purposes, and innumerable other uses, of which furniture, vehicles, implements, and tool handles are a few common examples. Knowledge of these properties is obtained through experimentation, either in the employment of the wood in practice or by means of special testing apparatus in the laboratory. Owing to the wide range of variation in wood, it is necessary that a great number of tests be made, and that so far as possible, all disturbing factors be eliminated. For comparison of different kinds or sizes, a standard method of testing is necessary, and the values must be expressed in some defined units. For these reasons, laboratory experiments, if properly conducted, have many advantages over any other method. One object of such investigation is to find unit values for strength and stiffness, etc. These, because of the complex structure of wood, cannot have a constant value which will be exactly repeated in each test, even though no error be made. The most that can be accomplished is to find average values, the amount of variation above and below, and the laws which govern the variation. On account of the great variability in strength of different specimens of wood, even from the same stick and appearing to be alike, it is important to eliminate as far as possible all extraneous factors liable to influence the results of the tests. The mechanical properties of wood considered in this book are 1. Stiffness and elasticity, 2. Tensile strength, 3. Compressive or crushing strength, 4. Shearing strength, 5. Transverse or bending strength, 6. Toughness, 7. Hardness, 8. Cleavability, 9. Resilience. In connection with these, associated properties of importance are briefly treated. In making use of figures indicating the strength or other mechanical properties of wood for the purpose of comparing the relative merits of different species, the fact should be borne in mind that there is a considerable range in variability of each individual material, and that small differences, such as a few hundred pounds in values of 10,000 pounds, cannot be considered as a criterion of the quality of the timber. In testing material of the same kind and grade, differences of 25% between individual specimens may be expected in conifers, and 50% or even more in hardwoods. The figures given in the tables should be taken as indications rather than fixed values, and as applicable to a large number collectively, and not to individual pieces. Fundamental considerations and definitions. Study of the mechanical properties of a material is concerned mostly with its behavior in relation to stresses and strains, and the factors affecting this behavior. A stress is a distributed force and may be defined as the mutual action, 1. Of one body upon another, or 2. Of one part of a body upon another part. In the first case, the stress is external, in the other, internal. The same stress may be internal from one point of view and external from another. An external force is always balanced by the internal stresses when the body is in equilibrium. If no external forces act upon a body, its particles assume certain relative positions, and it has what is called its natural shape and size. If sufficient external force is applied, the natural shape and size will be changed. This distortion or deformation of the material is known as the strain. Every stress produces a corresponding strain, and within a certain limit, see elastic limit, page 5, The strain is directly proportional to the stress producing it. The same intensity of stress, however, does not produce the same strain in different materials or in different qualities of the same material. No strain would be produced in a perfectly rigid body, but such is not known to exist. Stress is measured in pounds or other unit of weight or force. A unit stress is the stress on a unit of the sectional area. Unit stress equals P divided by A. For instance, if a load, P, of 100 pounds is uniformly supported by a vertical post with a cross-sectional area, A, of 10 square inches, the unit compressive stress is 10 pounds per square inch. Strain is measured in inches or other linear unit. A unit strain is the strain per unit of length. Thus, if a post 10 inches long before compression is 9.9 inches long under the compressive stress, the total strain is 0.1 inch, and the unit strain is lowercase l divided by uppercase L equals 0.1 divided by 10 equals 0.01 inch per inch of length. As the stress increases, there is a corresponding increase in the strain. This ratio may be graphically shown by means of a diagram or curve, plotted with the increments of load or stress as ordinates and the increments of strain as abscissae. This is known as the stress-strain diagram. Within the limit mentioned above, the diagram is a straight line. See Figure 1. If the results of similar experiments on different specimens are plotted to the same scales, the diagrams furnish a ready means for comparison. The greater the resistance a material offers to deformation, the steeper or nearer the vertical axis will be the line. There are 3 kinds of internal stresses, namely 1, tensile, 2, compressive, and 3, shearing. When external forces act upon a bar in a direction away from its ends or a direct pull, the stress is a tensile stress. When toward the ends or a direct push, compressive stress. In the first instance, the strain is an elongation. In the second, a shortening. Whenever the forces tend to cause one portion of the material to slide upon another adjacent to it, the action is called a shear. The action is that of an ordinary pair of shears. When riveted plates slide on each other, the rivets are sheared off. These 3 simple stresses may act together, producing compound stresses as in flexure. When a bow is bent, there is a compression of the fibers on the inner or concave side, and an elongation of the fibers on the outer or convex side. There is also a tendency of the various fibers to slide past one another in a longitudinal direction. If the bow were made of 2 or more separate pieces of equal length, it would be noted on bending that slipping occurred along the surfaces of contact, and that the ends would no longer be even. If these pieces were securely glued together, they would no longer slip, but the tendency to do so would exist just the same. Moreover, it would be found in the latter case that the bow would be much harder to bend than where the pieces were not glued together. In other words, the stiffness of the bow would be materially increased. Stiffness is the property by means of which a body acted upon by external forces tends to retain its natural size and shape, or resists deformation. Thus, a material that is difficult to bend or otherwise deform is stiff. One that is easily bent or otherwise deformed is flexible. Flexibility is not the exact counterpart of stiffness, as it also involves toughness and pliability. If successively larger loads are applied to a body and then removed, it will be found that at first the body completely regains its original form upon release from the stress. In other words, the body is elastic. No substance known is perfectly elastic, though many are practically so under small loads. Eventually, a point will be reached where the recovery of the specimen is incomplete. This point is known as the elastic limit, which may be defined as the limit beyond which it is impossible to carry the distortion of a body without producing a permanent alteration in shape. After this limit has been exceeded, the size and shape of the specimen, after removal of the load, will not be the same as before, and the difference or amount of change is known as the permanent set. Elastic limit, as measured in tests and used in design, may be defined as that unit stress at which the deformation begins to increase in a faster ratio than the applied load. In practice, the elastic limit of a material under test is determined from the stress-strain diagram. It is that point in the line where the diagram begins perceptibly to curve. See Figure 1. Resilience is the amount of work done upon a body in deforming it. Within the elastic limit, it is also a measure of the potential energy stored in the material and represents the amount of work the material would do upon being released from a state of stress. This may be graphically represented by a diagram in which the abscissae represent the amount of deflection and the ordinates, the force acting. The area included between the stress-strain curve and the initial line, which is 0, represents the work done. See Figure 1. If the unit of space is in inches and the unit of force is in pounds, the result is inch-pounds. If the elastic limit is taken as the apex of the triangle, the area of the triangle will represent the elastic resilience of the specimen. This amount of work can be applied repeatedly and is perhaps the best measure of the toughness of the wood as a working quality, though it is not synonymous with toughness. Permanent set is due to the plasticity of the material. A perfectly plastic substance would have no elasticity, and the smallest forces would cause a set. Lead and moist clay are nearly plastic, and wood possesses this property to a greater or less extent. The plasticity of wood is increased by wetting, heating, and especially by steaming and boiling. Were it not for this property, it would be impossible to dry wood without destroying completely its cohesion due to the irregularity of shrinkage. A substance that can undergo little change in shape without breaking or rupturing is brittle. Chalk and glass are common examples of brittle materials. Sometimes the word brash is used to describe this condition in wood. A brittle wood breaks suddenly with a clean instead of a splintery fracture and without warning. Such woods are unfitted to resist shock or sudden application of load. The measure of the stiffness of wood is termed the modulus of elasticity, or coefficient of elasticity. It is the ratio of stress per unit of area to the deformation per unit of length. E equals unit stress divided by unit strain. It is a number indicative of stiffness, not of strength, and only applies to conditions within the elastic limit. It is nearly the same whether derived from compression tests or from tension tests. A large modulus indicates a stiff material. Thus, in green wood, tested in static bending, it varies from 643,000 pounds per square inch for arbor vitae to 1,662,000 pounds for longleaf pine and 1,769,000 pounds for pignut hickory. See Table 9. The values derived from tests of small beams of dry material are much greater, approaching 3 million for some of our woods. These values are small when compared with steel, which has a modulus of elasticity of about 30 million pounds per square inch. See Table 1. Table 1. Comparative strength of iron, steel, and wood. Column 1. Material. Column 2. Specific gravity, dry. Column 3. Modulus of elasticity and bending, pounds per square inch. Column 4. Tensile strength, pounds per square inch. Column 5. Crushing strength, pounds per square inch. Column 6. Modulus of rupture, pounds per square inch. Cast iron, cold blast, Hodgkinson, 7.1, 17,270,000, 16,700, 106,000, 38,500. Bessinger steel, high grade, Fairbairn, 7.8, 29,215,000, 88,400, 225,600. Blank. Longleaf pine, 3.5% moisture, U.S. 0.63, 2,800,000. Blank. 13,000, 21,000. Red spruce, 3.5% moisture, U.S. 0.41, 1,800,000. Blank. 8,800. 14,500. Pignut hickory, 3.5% moisture, U.S. 0.86, 2,370,000. Blank. 11,130. 24,000. Note: great variation may be found in different samples of metals as well as of wood. The examples given represent reasonable values. Tensile strength. Tension results when a pulling force is applied to opposite ends of a body. This external pull is communicated to the interior, so that any portion of the material exerts a pull or tensile force upon the remainder, the ability to do so depending upon the property of cohesion. The result is an elongation or stretching of the material in the direction of the applied force. The action is the opposite of compression. Wood exhibits its greatest strength and tension parallel to the grain, and it is very uncommon in practice for a specimen to be pulled in two lengthwise. This is due to the difficulty of making the end fastenings secure enough for the full tensile strength to be brought into play before the fastenings shear off longitudinally. This is not the case with metals, and as a result, they are used in almost all places where tensile strength is particularly needed, even though the remainder of the structure, such as sills, beams, joists, posts, and flooring, may be of wood. Thus, in a wooden truss bridge, the tension members are steel rods. The tensile strength of wood, parallel to the grain, depends upon the strength of the fibers, and is affected not only by the nature and dimensions of the wood elements, but also by their arrangement. It is greatest in straight-grained specimens with thick-walled fibers. Cross grain of any kind materially reduces the tensile strength of wood, since the tensile strength at right angles to the grain is only a small fraction of that parallel to the grain. Table 2. Ratio of strength of wood in tension and in compression. Bulletin 10, U.S. Division of Forestry, page 44. Column 1, kind of wood. Column 2, ratio R equals tensile strength divided by compressive strength. Column 3, a stick 1 square inch in cross section, weight required to pull apart. Column 4, a stick 1 square inch in cross section, weight required to crush endwise. Hickory, 3.7, 32,000, 8,500. Elm, 3.8, 29,000, 7,500. Larch, 2.3, 19,400, 8,600. Longleaf pine, 2.2, 17,300, 7,400. Note: moisture condition not given. Failure of wood in tension parallel to the grain occurs sometimes in flexure, especially with dry material. The tension portion of the fracture is nearly the same as though the piece were pulled in two lengthwise. The fiber walls are torn across obliquely and usually in a spiral direction. There is practically no pulling apart of the fibers, that is, no separation of the fibers along their walls, regardless of their thickness. The nature of tension failure is apparently not affected by the moisture condition of the specimen, at least not so much so as the other strength values. Tension at right angles to the grain is closely related to cleavability. When wood fails in this manner, the thin fiber walls are torn in two lengthwise, while the thick-walled fibers are usually pulled apart along the primary wall. Table 3. Tensile strength at right angles to the grain of small clear pieces of 25 woods in green condition. Forest Service Circular 213. Column 1. Common name of species. Column 2. When surface of failure is radial, pounds per square inch. Column 3. When surface of failure is tangential, pounds per square inch. Hardwoods. Ash, white, 645, 671. Basswood, 226, 303. Beech, 633, 969. Birch, yellow, 446, 526. Elm, slippery, 765, 832. Hackberry, 661, 786. Locust, honey, 1,133, 1,445. Maple, sugar, 610, 864. Oak, post, 714, 924. Oak, red, 639, 874. Oak, swamp, 757, 909. Oak, white, 622, 749. Oak, yellow, 728, 929. Sycamore, 540, 781. Tupelo, 472, 796. Conifers, arbor vitae, 241, 235. Cypress, bald, 242, 251. Fir, white, 213, 304. Hemlock, 271, 323. Pine, longleaf, 240, 298. Pine, red, 179, 205. Pine, sugar, 239, 304. Pine, western yellow, 230, 252. Pine, white, 225, 285. Tamarack, 236, 274. Compressive or crushing strength. Compression across the grain is very closely related to hardness and transverse shear. There are two ways in which wood is subjected to stress of this kind, namely, 1. With the load acting over the entire area of the specimen, and 2. With the load concentrated over a portion of the area. See Figure 2. The latter is the condition more commonly met with in practice, as, for example, where a post rests on a horizontal sill or a rail rests on a cross tie. The former condition, however, gives the true resistance of the grain to simple crushing. The first effect of compression across the grain is to compact the fibers, the load gradually but irregularly increasing as the density of the material is increased. If the specimen lies on a flat surface and the load is applied to only a portion of the upper area, the bearing plate indents the wood, crushing the upper fibers without affecting the lower part. See Figure 3. As the load increases, the projecting ends sometimes split horizontally. See Figure 4. The irregularities in the load are due to the fact that the fibers collapse a few at a time, beginning with those with the thinnest walls. The projection of the ends increases the strength of the material directly beneath the compressing weight by introducing a beam action which helps support the load. This influence is exerted for a short distance only. Table 4. Results of compression tests across the grain on 51 woods in green condition and comparison with white oak. U.S. Forest Service. Column 1. Common name of species. Column 2. Fiber stress at elastic limit perpendicular to grain, pounds per square inch. Column 3. Fiber stress in percent of white oak, or 853 pounds per square inch. Percent. Osage orange, 2,260, 265. Honey locust, 1,684, 197.5. Black locust, 1,426, 167.2. Post oak, 1,148, 134.6. Pignut hickory, 1,142, 133.9. Water hickory, 1,088, 127.5. Shagbark hickory, 1,070, 125.5. Mockernut hickory, 1,012, 118.6. Big shellbark hickory, 997, 116.9. Bitternut hickory, 986, 115.7. Nutmeg hickory, 938, 110. Yellow oak, 857, 100.5. White oak, 853, 100. Bur oak, 836, 98. White ash, 828, 97.1. Red oak, 778, 91.2. Sugar maple, 742, 87. Rock elm, 696, 81.6. Beech, 607, 71.2. Slippery elm, 599, 70.2. Redwood, 578, 67.8. Bald cypress, 548, 64.3. Red maple, 531, 62.3. Hackberry, 525, 61.6. Incense cedar, 518, 60.8. Hemlock, 497, 58.3. Longleaf pine, 491, 57.6. Tamarack, 480, 56.3. Silver maple, 456, 53.5. Yellow birch, 454, 53.2. Tupelo, 451, 52.9. Black cherry, 444, 52.1. Sycamore, 433, 50.8. Douglas fir, 427, 50.1. Cucumber tree, 408, 47.8. Shortleaf pine, 400, 46.9. Red pine, 358, 42. Sugar pine, 353, 41.1. White elm, 351, 41.2. Western yellow pine, 348, 40.8. Lodgepole pine, 348, 40.8. Red spruce, 345, 40.5. White pine, 314, 36.8. Engelmann spruce, 290, 34. Arbor vitae, 288, 33.8. Large tooth aspen, 269, 31.5. White spruce, 262, 30.7. Butternut, 258, 30.3. Buckeye, yellow, 210, 24.6. Basswood, 209, 24.5. Black willow, 193, 22.6. When wood is used for columns, props, posts, and spokes, the weight of the load tends to shorten the material endwise. This is endwise compression, or compression parallel to the grain. In the case of long columns, that is, pieces in which the length is very great compared with their diameter, the failure is by sidewise bending or flexure, instead of by crushing or splitting. See Figure 5. A familiar instance of this action is afforded by a flexible walking stick. If downward pressure is exerted with the hand on the upper end of the stick placed vertically on the floor, it will be noted that a definite amount of force must be applied in each instance before a decided flexure takes place. After this point is reached, a very slight increase of pressure very largely increases the deflection, thus obtaining so great a leverage about the middle section as to cause rupture. The lateral bending of a column produces a combination of bending with compressive stress over the section, the compressive stress being maximum at the section of greatest deflection on the concave side. The convex surface is under tension, as in an ordinary beam test. See Figure 6. If the same stick is braced in such a way that flexure is prevented, its supporting strength is increased enormously, since the compressive stress acts uniformly over the section, and failure is by crushing or splitting as in small blocks. In all columns free to bend in any direction, the deflection will be seen in the direction in which the column is least stiff. This sidewise bending can be overcome by making pillars and columns thicker in the middle than at the ends, and by bracing studding, props, and compression members of trusses. The strength of a column also depends to a considerable extent upon whether the ends are free to turn or are fixed. The complexity of the computations depends upon the way in which the stress is applied and the manner in which the stick bends. Ordinarily, where the length of the test specimen is not greater than 4 diameters and the ends are squarely faced, see Figure 7. The force acts uniformly over each square inch of area, and the crushing strength is equal to the maximum load, P, divided by the area of the cross-section, A. C equals P divided by A. It has been demonstrated that the ultimate strength and compression parallel to the grain is very nearly the same as the extreme fiber stress at the elastic limit in bending. See Table 5. In other words, the transverse strength of beams at elastic limit is practically equal to the compressive strength of the same material in short columns. It is accordingly possible to calculate the approximate breaking strength of beams from the compressive strength of short columns, except when the wood is brittle. Since tests on endwise compression are simpler, easier to make, and less expensive than transverse bending tests, the importance of this relation is obvious, though it does not do away with the necessity of making beam tests. Table 5. Relation of fiber stress at elastic limit, R, in bending to the crushing strength, C, of blocks cut therefrom, in pounds per square inch. Forest Service Bulletin 70, page 90. Longleaf pine. Row 1. Moisture condition. Soaked 50%. Green 23%. 14%. 11.5%. 9.5%. Kiln dry 6.2%. Row 2. Number of tests averaged 5, 5, 5, 5, 4, 5. Row 3. R in bending 4,920, 5,944, 6,924, 7,852, 9,280, 11,550. Row 4. C in compression 4,668, 5,100, 6,466, 7,466, 8,985, 10,000, 910. Row 5. Percent R is in excess of C. 5.5, 16.5, 7.1, 5.2, 3.3, 5.9. Spruce. Row 1. Moisture condition. Soaked 30%. Green 30%. 10%. 8.1%. Kiln dry 3.9%. Row 2. Number of tests averaged. 5, 4, 5, 3, 4. Row 3. R in bending. 3002, 3362, 6458, 8400, 10170. Row 4. C in compression. 2680, 3025, 6120, 7610, 9335. Row 5. Percent R is in excess of C. 12, 11.1, 5.5, 10.4, 9. When a short column is compressed until it breaks, the manner of failure depends partly upon the anatomical structure and partly upon the degree of humidity of the wood. The fibers, tracheids and conifers, act as hollow tubes bound closely together, and in giving way they either 1, buckle, or 2, bend. The first is typical of any dry, thin-walled cells, as is usually the case in seasoned white pine and spruce, and in the early wood of hard pines, hemlock, and other species with decided contrast between the two portions of the growth ring. As a rule, buckling of a tracheid begins at the bordered pits, which form places of least resistance in the walls. In hardwoods such as oak, chestnut, ash, etc., buckling occurs only in the thinnest walled elements, such as the vessels, and not in the true fibers. According to Jacquard, the folding of the cells is accompanied by characteristic alterations of their walls, which seem to split them into extremely thin layers. When greatly magnified, these layers appear in longitudinal sections as delicate threads without any definite arrangements, while on cross-section they appear as numerous concentric strata. This may be explained on the ground that the growth of a fiber is by successive layers which, under the influence of compression, are sheared apart. This is particularly the case with thick-walled cells, such as are found in late wood. Table 6. Results of endwise compression tests on small clear pieces of 40 woods in green condition. Forest Service Circular 213. Column 1. Common name of species. Column 2. Fiber stress at elastic limit, pounds per square inch. Column 3. Crushing strength, pounds per square inch. Column 4. Modulus of elasticity, pounds per square inch. Hardwoods. Ash, white, 3,510, 4,220, 1,531,000. Basswood, 780, 1,820, 1,016,000. Beech, 2,770, 3,480, 1,412,000. Birch, yellow, 2,570, 3,400. 1,915,000. Elm, slippery, 3,410. 3,990. 1,453,000. Hackberry, 2,730. 3,310. 1,068,000. Hickory, big shell bark, 3,570. 4,520. 1,658,000. Hickory, bitternut, 4,330. 4,570. 1,616,000. Hickory, mockernut, 3,990. 4,320. 1,359,000. Hickory, nutmeg, 3,620. 3,980. 1,411,000. Hickory, pignut, 3,520. 4,820. 1,980,000. Hickory, shagbark, 3,730. 4,600. 1,943,000. Hickory, water, 3,240. 4,660. 1,926,000. Locust, honey, 4,300. 4,970. 1,536,000. Maple, sugar, 3,040. 3,670. 1,463,000. Oak, post, 2,780. 3,330. 1,062,000. Oak, red, 2,290. 3,210. 1,295,000. Oak, swamp white, 3,470. 4,360. 1,489,000. Oak, white, 2,400. 3,520. 946,000. Oak, yellow, 2,870. 3,700. 1,465,000. Osage orange, 3,980. 5,810. 1,331,000. Sycamore, 2,320. 2,790. 1,073,000. Tupelo, 2,280. 3,550. 1,280,000. Conifers, arbor vitae, 1,420. 1,990. 754,000. Cedar, incense, 2,710. 3,030. 868,000. Cypress, bald, 3,560. 3,960. 738,000. Fir, alpine, 1,660. 2,060. 882,000. Fir, amabilis, 2,763. 3,040. 1,579,000. Fir, Douglas, 2,390. 2,920. 1,444,000. Fir, white, 2,610. 2,800. 1,332,000. Hemlock, 2,110. 2,750. 1,054,000. Pine, lodgepole, 2,290. 2,530. 1,219,000. Pine, longleaf, 3,420. 4,280. 1,890,000. Pine, red, 2,470. 3,080. 1,646,000. Pine, sugar, 2,340. 2,600. 1,029,000. Pine, western yellow, 2,100. 2,420. 1,271,000. Pine, white, 2,370. 2,720. 1,318,000. Redwood, 3,420. 3,820. 1,175,000. Spruce, Engelmann, 1,880. 2,170. 1,021,000. Tamarack, 3,010. 3,480. 1,596,000. The second case, where the fibers bend with more or less regular curves instead of buckling, is characteristic of any green or wet wood, and in dry woods where the fibers are thick-walled. In woods in which the fiber walls show all gradations of thickness, in other words, where the transition from the thin-walled cells of the early wood to the thick-walled cells of the late wood is gradual, the two kinds of failure, namely, buckling and bending, grade into each other. In woods with very decided contrast between early and late wood, the two forms are usually distinct. Except in the case of complete failure, the cavity of the deformed cells remains open, and in hardwoods this is true not only of the wood fibers, but also of the tube-like vessels. In many cases, longitudinal splits occur, which isolate bundles of elements by greater or less intervals. The splitting occurs by a tearing of the fibers or rays, and not by the separation of the rays from the adjacent elements. Moisture in wood decreases the stiffness of the fiber walls and enlarges the region of failure. The curve which the fiber walls make in the region of failure is more gradual and also more irregular than in dry wood, and the fibers are more likely to be separated. In examining the lines of rupture and compression parallel to the grain, it appears that there does not exist any specific type, that is, one that is characteristic of all woods. Test blocks taken from different parts of the same log may show very decided differences in the manner of failure, while blocks that are much alike in the size, number, and distribution of the elements of unequal resistance may behave very similarly. The direction of rupture is, according to Jacquard, not influenced by the distribution of the medullary rays. These are curved with the bundles of fibers to which they are attached. In any case, the failure starts at the weakest points and follows the lines of least resistance. The plane of failure, as visible on radial surfaces, is horizontal, and on the tangential surface it is diagonal. End of Section 3. Section 4 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Handbook of Railroad Construction for the use of American engineers, containing the necessary rules, tables, and formulae for the location, construction, equipment, and management of railroads as built in the United States, with 158 illustrations, by George L. Vose, civil engineer. Quote, "Rules themselves oblige us to reflect, that we may see whether we have not departed from them." End quote. Napoleon. Boston and Cambridge, James Monroe and Company, 1857. Entered according to Act of Congress in the year 1857 by James Monroe and Company in the Clerk's Office of the District Court of the District of Massachusetts, Cambridge. Allen and Farnham, Printers. Preface. The object of this work is to give in the plainest possible manner all instructions, rules, and tables necessary for the location, construction, equipment, and management of railroads. As a general thing, American engineers are not educated for their business, and when they do possess a knowledge of pure science, they are at a loss how to apply it. The reader is presumed acquainted with the elements of arithmetic, geometry, algebra, and mechanics. Being thus provided, he will, by a perusal of what follows, be enabled to correctly proportion bridges of wood, stone, and iron, abutments, piers, retaining walls, superstructure, and locomotive engines, and to plan and lay out, execute, and estimate any description of work occurring upon railroads. As the object has been more to be useful than original, the best engineering writers and experimenters have been consulted, among whom are Gothi, Navier, Viat, Treadgold, Barlow, Totten, Fairbairn, Hodgkinson, Clark, and Lardner. Also a great number of reports by American civil engineers upon railroad matters. If assumptions take the place of demonstration, it will be on good authority. Readers will bear in mind that the work is a handbook and not a treatise. It is intended more as an office companion than as a textbook for students. It will give in all cases the actual numerical result needed, whether it be the scantling of a bridge cord, the thickness of a wall, or the dimensions of a locomotive boiler. In connection, it will be found convenient to use the works of Trautwein and Henck on field work, of Lieutenant Smith on topography, Davies on surveying, and Gurley on the use of instruments. Anyone wishing a complete treatise on the principles of bridge construction is referred to the excellent work of Hermann Haupt. I take this opportunity of heartily thanking the engineers who in many ways have aided in making the work, as it is believed, of some worth. G.L.V. Introduction. Quote, "They build not merely roads of earth and stone, as of old, but they build iron roads, and not content with horses of flesh, they are building horses of iron, such as never faint nor lose their breath." End quote. Dr. Bushnell, Rise and Progress of Railroads. 1. In 1825, the Stockton and Darlington Railroad, England, was opened. In 1827, the Quincy of Massachusetts and Mauch-Chunk, Pennsylvania, were completed. In 1829, the Liverpool and Manchester Road, England, was finished. In 1833, a road was opened from Charleston, South Carolina, to Augusta, Georgia. In 1840, Belgium opened 190 miles of railroad. In 1843, the railroad from Paris to Rouen, France, was completed. In 1844, Belgium finished her system of 347 miles. In 1846, Russia opened a railroad from the Volga to the Don. In 1847, Germany had in operation 2,828 miles. In 1852, the Moscow and St. Petersburg Road was finished. 2. In 1856, the United States of America had in operation 23,000 miles, and in progress 17,000 miles, employing 6,000 locomotive engines, 10,000 passenger and 70,000 freight cars, costing in all about $750 million, running annually 114 million miles, and transporting 123.5 million of passengers and 30 million of tons of freight per annum, performing a passenger mileage of 4,750,000,000 and a freight mileage of 3 billion. 3. By mileage is meant the product of miles run, by tons or by passengers carried. Thus, 500 persons carried 100 miles, and 750 persons carried 75 miles, give a passenger mileage of 500 times 100 plus 750 times 75 equals 106,250. 4. The rate of progress in the United States has been as follows. In 1828, there were 3 miles. In 1830, 41 miles. In 1840, 2,167 miles. In 1850, 7,355 miles. In 1856, 23,242 miles. At the present time, January 1st, 1857, there is probably, in round numbers, 25,000 miles of completed road, or enough to extend entirely around the world. As regards the ratio of completed road to population, and as regards the actual length of railroad in operation, the United States stand before any other country. Influence of railroads. 5. The effect of a judicious system of railroads upon any community is to increase consumption and to stimulate the production of agricultural products, to distribute more generally the population, to cause a balance between supply and demand, and to increase both the amount and safety of traveling. It is stated that within 2 years after the opening of the New York and Erie Railroad, It was carrying more agricultural produce than the entire quantity which had been raised throughout the tributary country before the road was built. 6. The following table, cut from a Chicago paper, shows the effect of railroad transport upon the cost of grain in that market. Wheat, Column 1, by railroad. Column 2, by wagon. At market, $49.50. $49.50. 10 miles, $49.25. $48. 50 miles, $48.75. $42. 100 miles, $48. $34.50. 150 miles, $47.25. $27. 200 miles, $46.50. $19.50. 250 miles, $45.75. $12. 300 miles, $45. $4.50. 330 miles, $44.55. $0. Corn, Column 1, by railroad. Column 2, by wagon. At market, $25.60. $25.60. 10 miles, $24.25. $23.26. 50 miles, $24. $17.25. 100 miles, $23.25. $9.75. 150 miles, $22.50. $2.25. 200 miles, $21.75. $0. 250 miles, $21. $0. 300 miles, $20.25. $0. 330 miles, $19.80. $0. Thus, a ton of corn carried 200 miles costs per wagon transport more than it brings at market. While moved by railroad, it is worth $21.75 per ton. Also, wheat will not bear wagon transport of 330 miles. While moved that distance by railroad, it is worth $44.55 per ton. 7. By railroads, large cities are supplied with fresh meats and vegetables, butter, eggs, and milk. An unhealthy increase of density of population is prevented by enabling businessmen to live 5, 10, or 15 miles away from the city and yet do business therein. The amount of this diffusion is as the square of the speed of transport. If a person walks 4 miles per hour, and supposing 1 hour allowed for passing from the house to the place of business, he cannot live at a greater distance than 4 miles from his work. The area, therefore, which may be lived in is the circle of which the radius is 4, the diameter 8, and the area 50 1/4 square miles. If by horse one can go 8 miles per hour, the diameter becomes 16 miles and area 201 square miles. And if by railroad he moves 30 miles per hour, the diameter becomes 60 miles and the area 2,827 square miles. The effect of such diffusion is plainly seen about Boston, Massachusetts. People who in 1830 were mostly confined to the city now live in Dorchester, Milton, Dedham, Roxbury, Brookline, Brighton, Cambridge, Charlestown, Somerville, Chelsea, Lynn, and Salem, places distant from 2 to 13 miles. 8. In railroads, as in other labor-saving and labor-producing machines, the innovation has been loudly decried. But though it does render some classes of labor useless and throw out of employment some persons, it creates new labor far more than the old, and gives much more than it takes away. 20 years of experience shows that the diminished cost of transport by railroad invariably augments the amount of commerce transacted, and in a much larger ratio than the reduction of cost. It is estimated by Dr. Lardner that 300,000 horses working daily in stages would be required to perform the passenger traffic alone, which took place in England during the year 1848. It is concluded also, from reliable returns, that could the whole number of passengers carried by railroad have been transported by stage, the excess of cost by that method above that by railroad would have been $40 million. Safety of railroad traveling. 9. If we know that in a given time the whole distance traveled by passengers was 500,000 miles, and that in such time there occurred one fatal accident, it follows that when a person travels 1 mile, the chances are 499,999 against 1 of losing life. If he travels 10 miles, the chances are 49,999 against 1, or 10 times as many of meeting with loss of life, and generally the chances of accident are as the distance traveled. In 1855, the whole number of miles run by passengers in the United States was, in round numbers, 4,750,000,000, while there were killed 116, or 1 in every 41 million, very nearly. The ratio in England is 1 in every 65 million. Now if for each 400,000 miles traveled by stage passengers, a distance equal to 16 times round the world, 1 passenger was killed, and if the whole railroad mileage could be worked by stages, there would be annually 11,875 lives lost, or 100 times the number annually lost by railroad. Thus it would be 100 times safer to travel by railroad than by stage. The danger of steamboat traveling is far greater than by stage. Preliminary operations. 10. The first step to be taken in starting a railroad enterprise is the choice of a board of directors, provisional, whose duty is to find all that can be known of the commercial, financial, and agricultural nature of the country to be traversed, to determine as near as possible its ability to build and support a road, and to obtain the necessary legislative enactments. 11. The determination of the increase of traffic which the road may be expected to excite is a difficult matter. There can be few rules given for proceeding in such an inquiry. It seems very easy to prove by what roads have done that any project will be profitable. An abstract of a report lately published tries to prove that a road will pay 45.5% net, the working expenses being assumed at only 13.5% of the gross receipts. The error here lies in assuming the working expenses too low, as few roads in the country have been worked for less than 40%, a more common ratio being 50/100ths of the gross receipts. Not 1/2 of railroads are built for the original estimate. In few cases has sufficient allowance been made for the sacrifice undergone in negotiating the company's securities. All general instructions that can be given relating to the determination of prospective profits are to keep the estimate of constructing and working expenses high, and that of the assumed traffic low. Not so low, however, as to require a too lightly built road. Mechanical principles of locomotion. 12. The superiority which the modern railroad possesses over the common macadam, plank, or turnpike road consists, first, in the reduction of the resistance to motion, and second, in the application of the locomotive steam engine. 13. The effect of grades of a given incline upon a railroad is relatively more than upon common roads, for as the absolute resistance on a level decreases, the relative resistance of grades augments. Whence to obtain the full benefit of the system, we must reduce much more the grades and curvature upon a railroad than on a common road. For example, if the resistance to moving 1 ton upon a level upon a railroad was 10 pounds, and upon a common road 40 pounds, where a 23 feet grade would be admissible upon the former, we might use an incline of 93 feet per mile upon the latter. 14. The resistance to the motion of railroad trains increases rapidly with the speed, whence the grades of a passenger road, where a high average speed is used, may be steeper than those of a road doing a freight business chiefly. Determination of character of road. 15. Upon a correct idea of what the road ought to be, depends in a great degree its success. The amount of capital expended upon the reduction of the natural surface depends upon the expected amount of traffic. The traffic remaining the same, the greater the capital expended in reducing grades and curvature, the less will be the working expense, and the less the construction capital, the greater that for maintenance. The limit of expenditure must be such as to render the sum of construction and maintaining capital a minimum. The bad effect of grades upon the cost of maintaining and of working railroads is not so great as many suppose. Of the whole cost of working, only about 40% can be charged to locomotive power, and of this, not more than 62% is effected by grades. 16. The degree of curvature to be admitted upon any road depends somewhat upon the speeds at which trains are to be run. The larger the radius of curvature, the greater may be the speed. At the same time, the elevation of the exterior rail upon curves may be less, and therefore more adapted to freight trains. High rates of speed are considered upon some competing roads necessary, but are, even in such cases, necessary evils. The wear of cars and of engines, of permanent way and of bridges, increase in a rapid ratio with the velocity. The maximum speed for freight trains should never exceed 15 miles per hour, or for passenger trains from 20 to 25 miles per hour. 17. The agricultural nature of the country and its commercial position will determine the nature of the traffic, whether passenger or freight, and also the amount. The amount and nature of the traffic will limit the curvature and will partially determine the arrangement of grades. Gauge. 18. The question of broad and narrow gauge has led to much discussion, and both plans claim among their advocates some of the best engineers. The narrow gauge, American and English, is 4 feet 8 1/2 inches from inside to inside of rail. The maximum adopted is the Great Western of England, 7 feet. The American maximum, New York and Erie, and Ohio and Mississippi, is 6 feet. There is also in America 4 feet 10 inches, 5 feet, and 5 feet 6 inches. The advantage of the broad gauge for a road doing an extensive business is the increased stowage room in freight cars, thus rendering admissible shorter trains, by which the locomotive power is more directly applied on curves. More comfortable passenger cars. The same length of car, of course, accommodates the same number of passengers. The disadvantages of a wide gauge are increased expense of cutting, embanking, bridging, and masonry, increased expense of engines, cars, rails, sleepers, and all machinery, more wear and tear upon curves by reason of greater difference between the lengths of inner and outer rails, and increased atmospheric resistance to fast trains from increased bulk. 19. The general conclusion arrived at by a commission appointed by the Great Western Railway Company, England, consisting of Messrs. Nicholas Wood, J.K. Brunel, and John Hawkshaw, was that 4 feet 8 1/2 inches was rather narrow, but still enough for a certain class of roads, that 2 or 3 inches made no material difference, that 7 feet was too wide for any road, that the weight of the broad gauge engine, compared with the small increase of power, was a serious evil, that engines could be run with perfect safety upon the narrow gauge at any speed from 30 to 60 miles per hour, and that no more had been attained upon the broad, that rolling friction was less upon the broad owing to the increased diameter of wheels, but that friction from curves and atmospheric resistance was greater. 20. D. K. Clark, in Railway Machinery, page 300, 301, makes the resistance as deduced from experiments made upon both the 4 feet 8 1/2 inches and the 7 feet gauge, considerably greater upon the former than on the latter. But as the narrow gauge trials were made upon a curved road with rails in a bad state in average weather, while those upon the broad were made in good weather upon a good and straight line, he leaves the gauge question open and uses the same formula for all widths. 21. Want of increased power can be an apology for increased gauge, until the capacity of the narrow gauge has been filled. The strongest engines in the world are upon the 4 feet 8 1/2 inch gauge. No engines in America surpass or compare for absolute strength with those upon the Baltimore and Ohio Railroad. The most powerful passenger engine ever built for high speeds is Crampton's engine, Liverpool, London and Northwestern Railroad, England, gauge 4 feet 8 1/2 inches. General establishment of route. 22. The straight and level line connecting any 2 points is of course the best for the completed road, but this is seldom practicable. Waytowns must be accommodated to a certain extent, but the main line should not be lengthened on that account, unless the traffic and capital furnished by such town is not only sufficient to pay for the construction and maintenance of the extra length, but also to carry the entire through traffic over such increased distance. If the town is unable to support such a burden, it may be able to build and maintain a branch. 23. Routes placed upon the immediate bank of a large stream are generally crossed by a great number of deep gorges, which serve to drain the side lands. 24. Routes placed upon sloping land, when the axis of the road and the natural descent are at right angles to each other, are more subject to slides than when placed upon plateaus or bottoms. 25. Lines crossing the dividing ridges of separate waters rise and fall a great deal, thus rendering necessary a strong motive power to work the road. Such roads are the western of Massachusetts, passing from the valley of the Connecticut at Springfield to the Hudson River Valley at Greenbush. Also those roads crossing the Alleghenies. And such will be the Pacific Road, crossing first the Rocky Mountains to the Great Basin, and second, the Sierra Nevada into the Sacramento Valley. Chapter 1. Reconnaissance. 26. The object of the reconnoiter is to find approximately the place for the road, i.e., within half of a mile, to find the general form of the country, and to choose that part which, with reference to the expected traffic, shall give the best gradients, to determine the elevations of summits upon competing routes, and, in fine, to prepare the way for the survey. General topography. 27. The general topography of a country may be ascertained by reference to state maps where such exist, and when not, by riding over the district. The direction and size of watercourses will show at once the position of summits. 28. Water flowing as in Figure 1 indicates a fall from B to E, and also traverse slopes from AA and CC to DD. 29. Figure 2 shows a broken ridge, AAA, from which the water flows in both directions, and in general, the sources of streams point towards the higher lands. 30. If it be required to join the points A and D by railroad, Figure 3, it may be better to pass at once from A through B and C than to go by the streams FE, F'E'. By the latter route, the road would ascend all of the way from A to E and descend from E' to D. By the first, if it requires steep gradients to rise from A to B and to fall from C to D, still if the section BC is a plateau, and if the rise between A and B and A and E is the same, by grouping the grades at B and C, we may so adapt the motive power as to take the same train from A to D without breaking. The general arrangement of grades by the line ABCD is then as Figure 4, and AFE, E'F'D as in Figure 5. The saving in this case is by length, as the same amount of power is required to overcome a given ascent. 31. Valleys generally rise much faster near their source than at any point lower down. Also, the width increases as we approach the debauch. Figure 6 shows the cross-sections of a valley from its source to the mouth. 32. In the case of parallel valleys running in the same direction, the form will be as in Figure 7. Let 1, 2, 1, 2, etc. represent a datum level or a horizontal plane passing through the lowest point. The line AB shows the height of the bottom at capital B, CD that at capital D, EF that at capital E, and GH that at capital C. The broken lines I, K, L, M, N show the general form of the land. Now by the route M, 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 from capital A to capital F, we have the profile M, 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 Figure 8, by N, 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 the profile N, 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 and by O, 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 the profile O, O, O. 33. In the case of parallel valleys running in opposite directions, as in Figure 9, we have the form there shown, and the profiles corresponding to the several lines are shown in Figure 10. As we should always adopt the line giving the least rise and fall, other things being equal, it is plain which line on the plan we must follow. 34. In passing from capital A to capital B, Figures 11 and 12, by the several lines C, D, E, F, we have the profile shown at C, D, E, F, from which it appears that the nearer we cross to the heads of streams, the less is the difference of heights. 35. If we wish to go from capital A to capital B, Figure 12, A, we should of course take first the straight line, but being obliged to avoid the hill capital C on arriving at D, we should not try to recover that line at E, but proceed at once to capital B. Also, as we are obliged to pass through D, we ought to go directly to D and not by the way of C, and the same idea is repeated between capital A and D, the last line being capital A, B, D, capital B. Few rules can be given in the choice of routes. Practice only will enable the engineer to find the best location for a railroad. Barometrical leveling. 36. The relative height of summits, the rate of fall of streams, and absolute elevation, within a few feet, may be easily, rapidly, and cheaply found by the barometer. This also affords an excellent check upon subsequent leveling operations. The results thus obtained depend upon the physical property that the density of the air decreases as the square of the height. 37. The barometer is a glass tube, partly filled with mercury, having a vacuum in the upper part. By it, the exact density of the air at any point is determined. Accompanying are two thermometers, one attached, showing the temperature of the barometer, the other detached, showing the atmospheric temperature. 38. Knowing now the manner of finding the density of the air at any 2 points, and also the relation between density and height, the operation of leveling by the barometer is very simple. Chapter 2. Survey. Topographical sketching. 39. Topographical drawing includes everything relating to an accurate representation upon paper of any piece of ground. The state of cultivation, roads, town, county, and state boundaries, and all else that occurs in nature. The sketching necessary in railroad surveying, however, does not embrace all of this, but only the delineation of streams and the undulations of ground within that limit which affects the road, perhaps 500 feet on each side of the line. The making of such sketches consists in tracing the irregular lines formed by the intersection of the natural surface by a system of horizontal planes at a vertical distance of 5, 10, 15, or 20 feet, according to the accuracy required. 40. Suppose that we wish to represent upon a horizontal surface a right cone. The base MM, Figure 13, is shown by the circle of which the diameter is mm. If the elevation is cut by the horizontal planes AA, BB, CC, The intersection of these planes with the conical surface is shown by the circles A, B, C in plan. The less we make the horizontal distances on plan between the circles, the less also will be the vertical distance between the planes. Wishing to find the elevation of any line which exists on plan as 1, 2, 3, 3, 2, 1, we have only to find the intersection of the verticals drawn through the points 1, 2, 3, 3, 2, 1, and the elevation lines AA, BB, CC. This gives us the curve 4, 5, 6, 7, 6, 5, 4. 41. Again, in figure 14, the cone is oblique, which causes the circles on plan to become eccentric and elliptic. Having given the line 1, 2, 3 as before, we find it upon the elevation in the same manner. 42. In the section of regular and full-lined figures, the horizontal and vertical projections are also regular and full-lined, but in a broken surface like the ground, the lines become quite irregular. Suppose we wish to show on plan the hill of which we have the plan, figure 15, and the sections, figures 16, 17, and 18. Let AD be the profile, made with the level, of the line AD on plan, figure 15. BE, that of BE, and CF, that of CF. To form the plan from the profiles, proceed as follows. Intersect each of the profiles by the horizontal planes AA, BB, CC, DD, equidistant vertically. In the profile capital A, capital D, figure 18, drop a vertical onto the baseline from each of the intersections A, B, C, D, D, C, B, A. Make now capital A 1, 1, 2, 2, 3, 3, 4, etc. on the plan equal to the same on the profile. Next draw on the plan the line capital B, capital E at the right place and at the proper angle with capital A, capital D. And having found the distances capital B, 1, 1, 2, 2, 3, etc., as before, transfer them to the line capital B, capital E on plan. Proceed in the same manner with the line capital C, capital F. The points AAA, BBB, CCC are evidently at the same height above the base upon the profiles, whence the intersections of these lines with the surface line, or 1, 1, 1, 2, 2, 2, 3, 3, 3, etc., on the plan, are also at the same height above the base, and an irregular line traced through the points 1, 1, 1, or 2, 2, 2, will show the intersection of a horizontal plane with the natural surface. When, as at capital A, we observe the contour lines near to each other, we conclude that the ground is steep, and when the distances are large, as at 6, 7, 8, we know that the ground falls gently. This is plainly seen both on plan and profile. Having now the topographical sketch, figure 15, we may easily deduce therefrom at any point a profile. If we would have a profile of capital G, capital E on plan, upon an indefinite line, capital G, capital E, figure 19, we set off capital G, 1, 1, 2, 2, 3, 3, 4, etc., equal to the same distances on the plan. From these points, draw verticals intersecting the horizontals AA, BB, CC, and lastly, through the intersections, draw the broken line, surface line, or profile A, B, C, D, D, C, B, A. Thus, we see how complete a knowledge of the ground a correct topographical sketch gives. 43. Field sketches for railroad work are generally made by the eye, the field book being ruled in squares representing 100 feet each. When we need a more accurate sketch than this method gives, we may cross-section the ground either by rods or with the level. By making a very detailed map of a survey and filling in with sketches of this kind, the location may be made upon paper and afterwards transferred to the ground. So far, we have dealt with but one summit, but the mode of proceeding is precisely the same when applied to a group or range of hills, or indeed to any piece of ground. 44. As a general thing, the intersection of the horizontal planes with the natural surface, contour lines, are concave to the lower land in depressions, and convex to the lower land on spurs and elevations. Thus, at capital B, capital B, capital B, BB, figure 20, upon the spurs, we have the lines convex to the stream, and in the hollows, C, 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 the lines are concave to the bottom. 45. Having by reconnaissance found approximately the place for the road, we proceed to run a trial line by compass. In doing this, we choose the apparent best place, stake out the center line, make a profile of it, and sketch in the topography right and left. Suppose that by doing so, we have obtained the plan and profile shown in figures 21 and 22, where capital A, capital B is the profile of capital A, capital C, capital D, capital B on the plan. The lowest line of the valley, though quite moderately inclined at first, from capital A to capital C, rises quite fast from capital C to the summit, and as the inclination becomes greater, the contour lines become nearer to each other. Now that the line may ascend uniformly from capital A to the summit, the horizontal distances between the contour lines must be equal. This equality is effected by causing the surveyed line to cut the contours square at 1, 2, 3, 4, and obliquely at 5, 8, 10. Thus we obtain the profile, capital A, 5, 5, capital B. 46. Having given the plan and profile, figures 23 and 24, where capital A, capital C, capital D, capital B represents the bed of the stream in profile, if it were required to put the uniformly inclined line, capital A, M, capital B, upon the plan, we should proceed as follows. Take the horizontal distance, capital A, M, from the profile, and with capital A on plan as a center, describe the arc 1, 3. The point M on the profile is evidently 3/4 of a division above the bed of the stream. So on the plan, we must trace the arc 1, 3, until we come to A, which is 3/4 of BC from B. Again, M' is 9 1/2 divisions above M. From A, with a radius MN on profile, describe the arc 4, 5, 6. Now, as on the profile, in going from M to M prime, we cross 9 contour lines and come upon the 10th at M prime. So on the plan, we must cross 9 contour lines and come upon the 10th, and at the same time upon the arc 4, 5, 6. Proceeding in this way, we find capital A, B, capital B on the plan as corresponding to capital A, M, M prime, capital B on the profile. To establish in this manner any particular grade, we have first to place it upon the profile and next to transfer it to the plan. 47. It may be remembered as a general thing that the steepest line is that which cuts the contour line at right angles. The contour line itself is level, and as we vary between these limits, we vary the incline. General establishment of grades. 48. Considerable has been written upon the relation which ought to exist between the maximum grade and the direction of the traffic. Some have given formulae for obtaining the rate and direction of inclines as depending upon the capacity of power. This seems going quite too far, as the nature of the ground and of the traffic generally fix these in advance. 49. Between two places which are at the same absolute elevation, there should be as little rise and fall as possible. 50. Between points at different elevations, we should, if possible, have no rise while descending, and consequently no fall while on the ascent. 51. Some engineers express themselves very much in favor of long levels and short but steep inclines. There are cases where the momentum acquired upon one grade or upon a level assists the train up the next incline. The distance on the rise during which momentum lasts is not very great. A train in descending a plane does not receive a constant increase of available momentum, but arrives at a certain speed, where by increased resistance and by added effect of gravity, the motion becomes nearly regular. Up to this point, the momentum acquired is useful, but not beyond. Any road being divided into locomotive sections, the section given to any one engine should be such as to require a constant expenditure of power as nearly as possible, i.e., one section, or the run of one engine, should not embrace long levels and steep grades. If an engine can carry a load over a 60 feet grade, it will be too heavy to work the same load upon a level economically. It is best to group all of the necessarily steep grades in one place, and also the easy portions of the road. Then, by properly adapting the locomotives, the cost of power may be reduced to a minimum. As to long levels and short inclines, the same power is required to overcome a given rise, but quite a difference may be made in the means used to surmount that ascent. 52. Suppose we have the profiles AED and ABD, figure 25. The resistance from A to D by the continuous 20 feet grade is the same as the whole resistance from A to B and from B to D. The reason for preferring AED is that an engine to take a given load from B to D would be unnecessarily heavy for the section AB, while the same power must be exerted at each point of AED. Also, the return by AED is made by a small and constant expenditure of power, being all of the way aided by gravity, while in descending by B, we have more aid from gravity than we require from D to B, after which we have none. When the distances A, B, B, C are 60 and 20 miles in place of 6 and 2, we may consider the grades grouped at BD and use a heavier engine at that point, as we should hardly find 80 miles admitting of a continuous and uniform grade. Equating for grades. 53. In comparing the relative advantages of several lines having different systems of grades, it is customary to reduce them all to the level line involving an equal expenditure of power. The question is to find the vertical rise, consuming an amount of power equal to that expended upon the horizontal unit of length. This has been estimated by engineers all the way from 20 to 70 feet. For simple comparison, it does not matter much what number is used if it is the same in all cases. But to find the equivalent horizontal length to any location, regard must be had to the nature of the expected traffic. The elements of the problem are the length, the inclination or the total rise and fall, and the resistance to the motion of the train upon a level, which latter depends upon the speed and the state of the rails and machinery. End of Section 4. Section 5 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from the Lathe and Its Uses, or Instruction in the Art of Turning Wood and Metal, including a description of the most modern appliances for the ornamentation of plane and curved surfaces, by James Lucan, with an appendix in which is described an entirely novel form of lathe for eccentric and rose engine turning, a lathe and planing machine combined, and other valuable matter relating to the art. Copiously illustrated. New York. John Wiley & Son, Publishers. No. 2, Clinton Place, 1868. Preface. Although the title of this work is sufficient to declare its contents, a few prefatory remarks may not be superfluous as to its design and the manner in which that design has been carried out. It has ever been to the writer a matter of surprise and regret that although the art of turning has been so long and so successfully pursued in this country, both by artisans and amateurs, no work has appeared in the English language treating upon the subject, except 1 or 2 sketches and imperfect treatises. Some years since Mr. Holtzapfel advertised a forthcoming series of 7 volumes, intended to supply this manifest deficiency in our scientific and mechanical literature, and the subject would have been handled by him in a thoroughly exhaustive and masterly manner. The untimely death of that gentleman occurred after the publication of the first 3 volumes, which are indeed complete in themselves and of immeasurable value to the mechanic and amateur, but which are unfortunately only introductory, simple turning by hand tools being the special subject of the proposed 4th volume. The present proprietors of the firm of Holtzapfel and Company having, in their catalogue, even up to the time of the most recent edition, continued to advertise the 7 volumes, amateurs especially have anxiously hoped for the publication of some part at least of the remainder of the series. That expectation is, it is to be feared, little likely to be rewarded, and not until that fact had been ascertained with something bordering upon certainty did the author of the present work venture to take up the pen and endeavor to set forth the principles and practice of an art which, like so many others, he has found so absorbing and attractive, and withal so delightful a source of recreation to mind and body. Several things, however, contributed to make the writer hesitate to undertake such a work. In the first place, he was aware that a number of possible readers would probably be more competent than himself for such a task, especially those whose means might have enabled them to procure a large amount of the most modern and approved apparatus connected with the lathe, and whose occupations might allow of more leisure for their extensive use than falls to the lot of the writer. In the next place, the risk of publication was such as he felt himself hardly justified in encountering. Just at this time, however, chance placed in his hand 2 or 3 numbers of the English Mechanic, in which someone else had begun, but speedily resigned, a series of papers on the lathe and its uses, compiled from American journals. The author of the present work at once put himself in communication with the editor and proprietor of the above periodical, with the result now well known to the readers. The following pages are not, strictly speaking, a mere reprint from the English Mechanic. The papers have been carefully revised and rearranged. Some statements, the correctness of which appeared doubtful, modified or wholly withdrawn, while in 1 or 2 instances whole chapters have been rewritten, and the suggestions and inventions relating to the lathe, furnished by other correspondents, embodied, when they appeared of real value, in the work. But in addition, a valuable appendix is now published, containing matter of great importance, contributed by 1 or 2 gentlemen who most kindly placed their papers at the service of the author. Foremost among them stands a paper on the angles of tools by Dodsworth Hayden, Esquire, of Guildford. A clever arrangement of lathe for rose engine work, by the aid of the eccentric chuck without rosettes, is also added from the pen of Mr. Elias Taylor, of Brighton, and 1 or 2 matters, which did not appear so fully treated as they deserved in the body of the work, have been resumed and more fully discussed in the appendix. The author gratefully acknowledges the suggestions of various correspondents, amateurs, and working men, from whom, as a rule, he has not failed to obtain any required assistance. That the work, in its present form, is entirely satisfactory or complete, the writer cannot pretend. That many errors have crept in is highly probable, but, if it is acknowledged to be the best work yet produced on the lathe, and should prove in any degree serviceable to amateur or artisan in the pursuit of this most delightful art, aye, if it should stir up some abler pen to write a better and more complete series, it will afford real pleasure and lasting gratification to the author. The Lathe and Its Uses. The lathe has now for many years been steadily making its way from the workshops of our leading artisans to those of the amateur and lesser stars of the mechanical world. This is but the natural result of the various additions and improvements which have been introduced into its construction from time to time. The unworkmanlike and clumsy tool of olden days has long since been superseded by one of admirable finish and perfect aptitude for its designed uses. And now that its construction is no longer dependent upon the skill of the workman alone, but upon machinery moving with the precision of clockwork, the fitting of the various parts is accomplished with the greatest ease and certainty. The sale being thus extended, the price has considerably diminished. The monopoly enjoyed by 1 or 2 makers no longer exists, and there are few of a mechanical turn of mind who cannot now provide themselves with a lathe suited to their requirements. Nevertheless, the adepts in the art of turning are by no means so numerous as might be expected, and among amateurs especially, it is rare to find work executed in first-rate style by simple hand tools, requiring skill and practice in their use, so that it not unfrequently happens that a workman who can turn out exquisite specimens of ivory carving and ornamental lathe work is but a fourth-rate hand with the gouge and chisel. But however beautifully executed such ornamental work may be, the credit is rather due to the tool than the workman, and a well-turned box with accurately fitting cover may bespeak more skill in handiwork than the above elaborately designed specimen. Moreover, the one requires lathe fittings, which are not always to be had unless the purse is well filled, whereas the general mechanic, amateur or professional, can provide the tools needed for the other. Hence, we propose first of all to give some practical hints on plain hand-turning of wood and metal. The ordinary form of foot lathe is well known and requires no special description. It is represented in the frontispiece of this volume. There are, however, certain points of detail in its construction to which it is necessary to direct the reader's attention. First and foremost comes the mandrel, of which there are several patterns, according to the special purpose for which the lathe may be intended. Now, of whatever form it may be made, this is the essential part of the lathe, and must run with the utmost truth in its bearings. Imperfection here will be imparted to all work executed upon it, and accuracy in this part alone will make up for any slight defects that may occur in less important parts of the machine. For ordinary work in wood alone or in brass, the best form is represented in Figure 1. The part AB should be cylindrical, with a feather let in to fit a slot in the pulley shown in Figure 2. This pulley, whether of hard wood or metal, is thus slipped on the mandrel as far as the collar DD and a nut E, screwed up tightly at the back of it, fixes it securely in its place, from which it may be moved if requisite, and replaced without fear of being out of truth. This cannot be done if the mandrel is squared at AB, and the pulley driven on with a hammer, as commonly done by inferior workmen. The part C is made conical, to fit a hardened steel collar of similar shape. The angle of this conical part is of some importance, as if it is too small, the mandrel is apt to jam and stick tight in its bearings. 35 degrees will be found to work well. With regard to the length of this conical part, opinions differ considerably, but it must be remembered that friction is independent of the extent of the bearing surfaces and depends on the force with which they are pressed together. In the present case, it depends on the tension of the lathe cord and the weight of the material to be turned, so that a tolerably wide margin may be allowed in this matter. Practically, the question is decided by the thickness of the casting of the poppet head, which is regulated by the required strength and size of the lathe. The collar is sometimes of hardened steel, sometimes of brass. The latter would theoretically cause less friction than the former, but practically nothing can beat a well-finished collar of hard steel. Collars of this material made by the original Holzapfel 2 generations back are now as good as ever, perhaps even better. The center, which screws up against the left-hand end of the mandrel, should be of the form shown in Figure 3. A plain cylinder with a screw cut at each end to receive clamping nuts. The central part is rather larger than the screwed parts, and passes truly through the poppet head. This form is much better than a simple screw with points, as the latter is not likely to keep the line of centers in being screwed up into its place. It will be found of great convenience to have the screw on the nose of the mandrel, and indeed all screws about the lathe, of standard Whitworth pitch, as taps for the chucks are thus readily obtained, and nuts and screws of the various sizes may be also procured to remedy breakages and losses. Upon this subject, however, we shall have occasion to treat more fully when we pass from the description of the lathe itself to the work that is to be accomplished by its aid. The only form of back poppet that need be particularized is that made with cylinder and leading screw. The simple pointed screw passing through the lathe head, tapped to receive it, not only requires no special description, but it is only calculated for lathes of the commonest design, as it is seldom that the line of centers is accurately maintained by the point at every part of the revolution of the screw. Moreover, the latter soon works loose in the poppet, and for anything like accurate work becomes speedily useless. The cylinder and pushing screw is indeed far superior to the form just alluded to, and where cheapness is an object, it has its advantages over the first named and best form. It is represented in Figure 4. The cylindrical part is shown at B, and many have at one end the usual point, and at the other a small conical hole or hollow center. It may then be reversed in its bearings at pleasure, or other cylinders with different shaped ends can be substituted, as may be found convenient. Of course, the pushing screw A is for the purpose of advancing the cylinder, which is clamped by the small screw at C. The cylinder and leading screw are shown in detail in Figure 5, which is the poppet head bored throughout to receive the spindle or cylinder A. At the right hand, this bore is enlarged to form a recess, B, to receive the head of the leading screw, C. This screw is generally made with a left-handed thread, so as to withdraw the back center when turned from right to left. The spindle A is bored, and a left-handed female thread is cut from end to end. This, however, is turned off at the place destined to receive the movable point or center, and a hole slightly tapering is cut, or if preferred, a cylindrical hole is made and tapped for the same purpose. The spindle has also a slot cut from end to end, into which a screw enters from the poppet, preventing the spindle from turning round, while the internal screw is revolving by means of the small wheel and handle fixed to its right-hand end. The spindle is now put in its place, the screw inserted and turned till the head or flange, C, rests in the recess before mentioned. A flat plate, F, is then attached to the back of the poppet by 3 or 4 screws, the head of the leading screw passing through its center. The small wheel is then attached, and the whole is complete. It is evident that by turning the wheel, the internal screw is put in revolution, and as it is prevented by its flange from assuming any motion in the direction of its length, the movable cylinder will instead be withdrawn or thrust forward. This form of poppet is the best that can be adopted, and is of general use in all first-class lathes. In addition to the movable point G, a flange similar to H should be fitted. This will be found of great use when the lathe is used for drilling, the piece of work resting against it, while the pressure is regulated by the leading screw. There are, in addition to the flange and pointed center, other pieces of apparatus that can be substituted, as occasion may require, and these will be hereafter described in this series. With regard to the common rest for hand turning, a lengthened description is unnecessary. The letter T, or word T, T-E-E, should for wood turning be of the form shown in Figure 6 at A. It is often made as B, which is a very inconvenient pattern, as the cross-piece on which the tool rests cannot be advanced sufficiently close to the work if the latter exceeds a diameter of 2 or 3 inches. For metal turning, the top of the rest should be flat and about 1 inch broad, as the heel of the hook tools used for turning iron must be able to take a firm bearing upon its surface. Sometimes a plate of brass is riveted on the flat top, as the tool takes a firmer hold on this metal, and when the latter becomes defaced and channeled, it can be renewed without the cost of a new casting in iron. The turner should be provided with 2 or 3 teeth for metal and for wood. One may be long enough to have 2 legs and require 2 sockets, as shown at C. This is convenient in turning long pieces of wood. A very short T, not more than 1 inch in length, should also be provided, and if one T is specially kept with a very level and smooth edge, it will be found of great advantage in chasing screws. Indeed, the latter work can hardly be managed at all if the top of the rest is damaged and uneven. The next part requiring description is the boring collar, without which even a hand-turning lathe can hardly be considered complete. This boring collar is intended so to support one end of the work, instead of its being held by the back center, as to enable the workman to get at the end of it for the purpose of drilling it. Suppose, for instance, the work in hand is a tool handle, and that it is so far finished as only to require the hole for the reception of the tang of the tool. If this is bored by hand with a gimlet, it is seldom that the hole will be truly in the axis of the piece, but when this is done in the lathe, by the help of the boring collar, the bore will be truly central, and the tool, when in place, will fall in the same line with the handle. This will conduce to the correctness of the work in hand, more than the amateur or other workman might suppose, and a row of tools thus truly handled and in good condition generally bespeaks an efficient and careful artisan. There are several plans for boring collar of nearly equal efficiency, and we shall describe 1 or 2 of the most common, and also one invented by the author, and which, if carefully made, is of great service. Figure 7 represents a poppet head, B, which is but half the height of the other poppets of the lathe. A side view of this is shown at B, figure 8. Near the top of this poppet is a hole through which passes a bolt, C, by which and its nut, the circular plate A, can be securely clamped in any desired position, as it revolves freely on the bolt as a center pin. This plate is bored with a series of conical holes, which are so arranged that their respective centers will be in a line with the centers of the mandrel when any one of them is brought into a position corresponding with the line C, C. The hole thus brought into position for use, having been selected according to the size of the work to be bored, takes the place of the back center. The end of the work rests in the cone, which is greased or soaped to reduce friction, and the rest being fixed at the other side of the boring collar, the drill can be readily used, and the bore afterwards enlarged, if necessary, with any convenient tool. This boring collar is generally made of iron, but a substitute of hard wood will frequently serve the purpose, and can be made by the amateur, who may be unable to attain one of a more durable material. If made of wood, the best unguent will be soap or black lead, such as is used for grates, or a mixture of the two. This black lead, or plumbago, it has no lead in its composition, will always be found serviceable where wood works upon wood, and also to give a smooth surface to wooden patterns for casting. Where cost is an object, a simple substitute for the boring collar is frequently made by the ordinary workman by a piece of board 1 inch thick, shaped like figure 9, with a single hole of the size most generally required, and the work is then fitted to the boring collar instead of the latter to the work. In turning tool handles, for instance, where a few dozen are required, all of the same size, or nearly so, a device of this kind, which can be made in a few minutes, is sufficiently effective. This form has been modified in 2 ways, and either will be found convenient. In the first, The conical hole is made of the largest size likely to be required. A set of boxwood plugs are then turned to fit this hole and are themselves bored in a similar way to suit various sizes of work. The form of these plugs is shown in Figure 10, which is a side sectional view, and at B, where the same is shown in perspective. Two small screws or pins, B, C, Figure 10, fitting into the holes AA, Figure 9, prevent these flange-shaped plugs from turning round in the board as the work revolves. The pattern of A, Figure 9, may be varied, and is better made of hard wood and of a form which will afford a good bearing upon the lathe bed. The second modification is more difficult to make, but equally effective. It is shown complete in Figure 11. This form, arranged by the writer, has many advantages over the two last named, and is very serviceable. A is the poppet, of the full height of the ordinary lathe heads, or a couple of inches higher. B, the slide forming the support of the piece to be bored. The form of the poppet without this attachment is shown in Figure 12. If for nice work, it should be made of metal and the face of it planed, but for general purposes, hard wood will suffice. BB, Figure 11, are two pieces of brass forming a groove or guide in which a slide, capital B, with dovetailed edges is fitted to work. This slide is bored, like the ordinary collar, with conical holes of different sizes, and should be made of metal and planed on back and edges. Over each hole is a mark, and this is to be brought to a similar mark on the face of the poppet. The plate is then clamped in position by a screw at the back of the poppet. One or more of such slides may be fitted at pleasure, and in case of wear or damage, these are the only parts requiring to be renewed. It is a good plan to arrange a socket and T of a rest, as BC, Figure 13, at the back of this boring collar, especially as the position of the tool will always be the same, so that the rest may be a permanent part of the poppet. There is sometimes a difficulty with the ordinary form of boring collar in advancing the rest T sufficiently near the work, the foot of the poppet and that of the rest preventing it by coming in contact. There is another modification of boring collar, forming at the same time a guide for the drill, which in slender work, where the tool is long and fine, becomes almost a matter of necessity. This consists in making such a guide cone as mentioned and shown in Figure 10, B, but with a continuation containing a smaller hole for the drill, as Figure 14. Both this and the other shorter cones above mentioned may be made to screw into the poppet A, Figure 9, instead of being kept in place by the pins at AA of that figure. In that case, however, the hole in the poppet must be cylindrical and only used as a support for the cones themselves. In addition to the use of these boring collars already alluded to, they serve for the purpose of turning up the points of screws like those of lathe centers. These are first formed between centers with carrier chuck. The back poppet is then removed, and the extreme point fitted through one of the holes of the boring collar, and the marks of the center turned off. Another useful adjunct to the lathe is the back rest for supporting long and slender articles, which would otherwise bend under the pressure of the tool. The ordinary and simplest form is shown in Figure 15, and this is of general use with brush handle makers and others whose work is confined to a few sizes and shapes only. A better form is shown in Figure 16. A support of wood or metal shaped like A is clamped to the lathe bed. Through the upper part, the slide B passes and is wedged up so as to support the work, or the socket of a lathe rest may be arranged to take the upper part A, which must then be rounded, as shown at C. A modification of the latter, communicated to the English mechanic, is shown in Figure 16A. Its construction and mode of application is sufficiently evident without a detailed description. Figure 16B is another form made in metal. It consists of two similar plates with a triangular opening A, through which the work is passed, and which has an oval slot D, by which the apparatus is secured to the short poppet of the boring collar. Between the two plates slides a third, partly visible at C, which can be clamped by a screw at B, this screw also serving as a stud by which the plate may be moved. The work is allowed to take up its own bearing in the triangular opening as it revolves in the lathe. The clamping screw of the poppet is then secured, and the centering thus made certain. The plate C is then made to descend so as to touch the work, and clamped in that position. This is a very good central support for long, slender articles. There is a plan practiced by German turners, by which the back rest is in a measure superseded, and which may be mentioned here. It is simply the peculiar method of using the left hand. This is placed on the piece to be turned, so that the fingers partly encircle the work, while the thumb rests in the hollow of the gouge or upon the end of the tool. The fingers thus form a back rest and keep the work pressed against the cutting edge, which is further steadied by the thumb. As the tool traverses the work, the left hand accompanies it, and with a little practice, a ramrod or similar long and slender article may be readily and accurately turned. This position is shown in Figure 17, and though the novice will find it difficult to work thus, it is well worth the trouble of mastering, as the method once acquired will be found of very great service. We have now described more or less in detail the principal parts of the lathe as adapted for hand turning. Before we dismiss this part of the subject, however, it will be necessary to say a few words respecting the bed and lower fittings, the flywheel, treadle, and their adjuncts. Beyond question, the iron bed, planed as it now is at a moderate price by machinery, is the best that can be adopted, especially if it is intended eventually to fit up the simple tool with slide rest and superior apparatus. Nevertheless, the pocket must in this case also frequently decide the question of material. If wood is preferred by necessity or otherwise, it should be hard wood, beech, or Spanish mahogany, unless it is proposed to plate the surface with iron. This latter plan costs little, and besides stiffening the bed, it prevents the wear and tear caused by the constant shifting of the back poppet and rest. A flat strip of iron, 1 inch or 1.5 inches wide, can be picked out from the stores of any village blacksmith, straight and level as it came from the rolls of the manufacturer. Selecting a piece of the required length and breadth, the 1/8 of an inch thick, or rather more, the purchaser will have holes drilled and countersunk at intervals of 9 or 10 inches to receive 3/4 inch screws. These strips will have to be laid upon the top of the bed at its inner edges. They need not be let in flush with the surface unless appearance is studied. They must then be screwed down firmly, and by means of a file worked by both hands up and down their length, not across them, a good surface may be readily obtained. If the iron is let into the bed, this filing will abrade the woodwork, which is the reason why we prefer screwing it on the surface. This method produces a very excellent and durable lathe bed, and it will be free from much of the tremor which is so disagreeable while working upon a lathe entirely of cast iron, unless the bed of the latter and the standards are more substantial than is usual with small lathes. The standards supporting the axle of the flywheel and bed may in like manner be of wood or iron. Even when the bed is of iron, these may be of hard wood, although it is customary to make them of the same material as the bed. If of beech, oak, or mahogany, as in some of Holtzapfel's best lathes with iron beds, the tremor before alluded to will be considerably lessened. Iron is nevertheless very neat, and is quite the fashion with the majority of makers, but is too often faulty in respect of solidity. The standards as a rule are too slight, an elegant pattern being studied to the sacrifice of substance and weight. The bed and stand of a lathe cannot be too strong and stiff. Respecting this matter of stiffness and solidity, we seldom find it sufficiently considered, and even with practical workmen, a defect in this particular is more frequently acknowledged and put up with than remedied, and although the comfort of a steady lathe is beyond question, to say nothing of its superiority when good workmanship is studied, as it always should be, the old French lathes made in the form of a thick table with 4 stout legs, forming the bed and backboard, are by no means to be despised as patterns, and instead of the usual method of making but one standard at end of the bed, there can be no question that 2 additional ones add considerably to the stability of the machine. The flywheel should be sufficiently heavy and have 3 speed grooves on the rim, and 2 additional ones to produce a slow motion, which is required for turning metal. The latter may be worked with ease in this way when the article to be turned is small, but if heavy work is likely to be encountered, the back-geared lathe, to be hereafter described, must be substituted, and the slide rest will then also replace the hand tools. The crank axle is generally supported by 2 center screws, the points being hardened, and also the ends of the axles, which are accordingly made of steel, and the holes for the center screws neatly drilled and countersunk. This is, however, not the most perfect method, and as we are speaking of better class lathes, as well as those of more common and cheaper make, we must by no means omit to speak of a very superior way of fitting the crank axle. The latter must be turned at both ends, the wheel bored and slipped on, and keyed in its place. 2 wheels of brass about 2 inches diameter must then take the place of the center screws. These are called friction wheels, and they must be placed sufficiently near each other to support the end of the axle between them, as shown in Figure 17b, A, and B. A pair of these must be thus fitted to each standard, and after the axle is placed in position, a third may be placed above it, to prevent the lathe cord from lifting the axle out of place by its tension. The axle and friction wheels will thus work together with an exquisitely smooth rolling motion. There will be no tendency to thrust the lathe standards apart, as must result from tightening the ordinary center screws, and the friction of the axle on its bearings will be reduced to a minimum. Any person acquainted with the use of the lathe may readily fit up these friction wheels, and the time and trouble so expended will be amply repaid by the superior ease with which the lathe can be used. We may say the same of the chain and eccentric, which can replace with similar advantage the crank and hook in ordinary use. For the latter, the following arrangements are necessary. A is the eccentric keyed to the crank axle, and may be either in the middle of the same or, as in Weir's patent lathes, at one end outside the standard. Around it passes the endless flat chain B, known as crank chain. This also passes round a roller in the treadle shown at C. This chain does not act as a mere link, but when the lathe is in action, it moves round and over the eccentric and treadle roller. The motion of the whole is smooth and regular, and what is almost as important, noiseless. In Weir's and other lathes, the crank chain is used without the eccentric being applied to the crank instead. Perhaps there is not much to choose between the two, but no one who has studied the eccentric and observed its exquisitely gentle and smooth motion in an ordinary engine can have failed to be struck by these valuable qualities. It must, however, be remembered that its throw is half that of a crank of the same eccentricity, and the latter will have the advantage in power size for size. In whatever position the lathe may be set up, let the rise of the treadle be moderate. It is exceedingly disagreeable to work at a lathe where the rise of the footboard is so great as to bring the knee into contact with the lathe bed, a consummation not infrequent in country-made ones. This is only to be escaped by giving up a certain portion of power. Let AB, figure 19, be the line of the treadle when at rest, C, the crank. To gain power, we should let part A, E, be longer than E, B, as in the sketch. But let this arrangement be made, and when the crank is at its highest point, the line GB will show the position of the treadle and footboard. Hence, this kind of leverage is not practicably available to any extent, and the length taken from footboard to link may with advantage be even less than that from link to the axle on which the treadle works. In lathes of all machine tools, it is essential that the workman should be able to stand easily, that the movements of the leg and body should not be communicated to the tool, the play of the treadle, and such items of detail being of more consequence than might at first sight appear, and any method tending to diminish friction, vibration, and noise is well worth consideration in planning this machine. We may now suppose the reader the happy possessor of a well-made foot lathe, long or short in bed, high or low in poppet, according to his need, but, of whatever size, carefully made and firmly fixed in a well-lighted place, and if possible on the basement floor. An upstairs workshop is objectionable owing to the certain vibration of a boarded floor. He will now require certain chucks and tools, many of the former of which he will have to make for himself. Chucks. No lathe can be considered well fitted until it is supplied with a large number of chucks, by which strange term are signified the various appliances for fixing to the mandrel the article to be turned. When it is considered how varied are the forms which present themselves to the turner, it may readily be conceived that much ingenuity has to be exercised in contriving methods for mounting his work in the lathe, and when in addition to variety of form, variety of size has to be taken into consideration, it is plain that a large assortment of chucks is a necessary item in the workshop of the turner. A vast number of these chucks are of necessity made of wood, as required, and such wooden ones are altered from time to time to suit different sized work, till they eventually become so completely used up as to be only fit for the fire. In addition, however, to these, there are certain chucks of metal, chiefly brass or gunmetal, which should always be ordered with a lathe, or fitted to it before any work, even the making of wooden chucks, can be satisfactorily accomplished. The first of these is represented in Figure 20, the part A, screws to the mandrel, while the work is attached to the taper screw B. The use of this chuck is to hold short pieces or flat discs, which allow of a hole in the center and require to be turned on the face. It is only used for woodwork. This is the chuck to be selected when it is desired to make a wooden chuck. A piece of sound wood being chosen of the requisite size, and roughly rounded by the axe or chisel, a hole is made in one face by a gimlet rather smaller than the tapering screw. The piece is then firmly screwed to the latter, the opposite end dressed with gouge and chisel, and the rest being placed across the end, a hand drill for wood is brought to bear upon the piece. The hole thus made in the center is then enlarged by any convenient tool until its diameter is only a little less than that of the screw cut on the lathe mandrel. An inside screw tool is then made use of to cut a thread of the same pitch as that of the mandrel, or a tab of similar size and pitch screwed into it. The former is the best, but most difficult method to a novice. The piece detached from the taper screw chuck, which is removed, and the wood attached to the nose of the mandrel on which it may now be accurately fitted and finished to the requisite form and hollowed out or otherwise as may be necessary. Numberless articles may be in a similar manner turned upon the above chuck, such as the bottoms of candlesticks, ring or other stands, bread platters, small wheels, and so forth. It may therefore stand as number 1 of these adjuncts to the lathe. Figure 21 is the faceplate, another most serviceable chuck of almost universal application in such work as surface turning and boring, and where a hole in the center is inadmissible. To this belong various dogs or cramps, a few forms of which are shown at A, B, C, D. These hold the work firmly down to the surface of the plate, being tightened from behind by screw nuts. It will be seen that there are 4 slots and numbers of holes in the faceplate, some of the latter being tapped for screws. These slots and holes may be increased in number, and some of the latter may be square instead of round, and the cramps may be of all shapes and sizes, because sometimes it may be required to hold down a flat piece of brass the 1/8 of an inch thick only, and the next job may be to hollow an irregular block of wood of 3 or 4 inches in thickness, or it may be necessary to bore out the boss of a wheel, or to turn the rim, all of which, and 100 others, are cases in which the aid of the faceplate will be in requisition. Figure 22 is the chuck specially used for turning rods of metal. It consists of 2 parts, the body A, which screws to the mandrel, and the piece B, which passes through a slot and is clamped by a small screw at one side, C. To these must be added the carrier, which is of such forms as A1, B1, C1. Above is shown a rod of metal to be turned with this chuck in position for use. Of this we shall have to speak again when we arrive at the subject of metal turning. There should be several sizes of carriers kept in stock, from 1/4 inch in the largest part of the ring to 2 inches or 3 inches, or even much larger for heavy work. The amateur will, however, scarcely need these larger ones. The usual method of making the wood-holding chuck for work that is to be also supported by the back center is to have a socket cast like figure 23, C, with a central hole to take the fork, A, which is held in place by a set screw. This socket is useful for other purposes, as it will hold short pieces of iron to be turned, but the fork is far inferior for general work to the piece B. This is made of iron, and the end of the cross, against which the wood to be turned comes, is sharpened, but must not be too sharp. The end of the piece of wood has then 2 saw cuts made at right angles to each other, into which the sharpened edges of the cross fall, figure 23D, and the whole will turn together without any chance of slipping. It often happens, when the ordinary fork is used, that if the tool chances to hitch in the work, the latter is either thrown quite out of the lathe, or the center of the fork retains its place, while the other 2 points slip and score the work. This can never happen with the form B, which is the most reliable pattern that can be devised for work of this nature. Figure 24 is to some extent self-centering. A piece of wood hollowed out conically has 3 nails or 3 square saw files so placed within the cone as to present 3 sharp edges inwards. Any piece of wood, if not too hard, will, if placed with one end in the chuck, while the back center is screwed against the other, center itself in some part of this cone, and being at the same time held by the 3 sharp edges, will necessarily revolve in the chuck. There are many cases in which even in this rough form such a chuck will prove useful, but if it were cast in metal, and the 3 edges formed by slips of steel, and the whole accurately turned, it would be a very efficient and good self-centering chuck. In its more common form, it is largely used by the turners of mop and broom handles, who work rapidly and cannot afford to waste time in chucking their work. With the above, the lathe, if worked by steam or water power, is not even stopped. The screw of the back center has a quick thread, so that a single turn to or fro fixes or releases the work, and thus, one handle being finished, another piece takes its place in the chuck, is fixed by a half turn of the back screw, and being set in rapid motion, is turned and completed by a practiced hand in a couple of minutes or less. Figure 25 represents another useful chuck, generally of boxwood, called the barrel stave chuck. It is turned conical, the largest part being towards the mandrel. It is then wholly or partially drilled through, after which saw cuts are made longitudinally, as in the drawing. These allow a certain degree of expansion when a piece of work is fitted into it, and it is tightened round the latter by driving on a ring of iron or brass. This ring is sometimes cut with a coarse thread inside, and a similar thread being chased on the outside of the chuck, it is screwed upon the cone instead of requiring to be driven by blows of a hammer. One important use of this chuck is to remount in the lathe for ornamentation by the eccentric cutter or other apparatus, any finished work that could not be readily chucked in any other manner, or to hold rings requiring, like curtain rings, to be turned on the inside. Such articles will, from the nature of this chuck, be truly centered at once, and their exterior parts will not be liable to injury, as they would be by being driven into an ordinary chuck hollowed out to receive them. Another useful chuck for turning short pieces of metal, such as bolts and binding screws, and which is in a great measure self-centering, is made of cast iron, and is usually called the dog-nose chuck, represented in Figure 26. This is made with movable jaw hinged, as more plainly seen in B. The screw clamps these jaws firmly together, and any small piece of work is thus securely held. The centering, however, is not accurate, though sufficiently so for many purposes. The die chuck, Figure 27, is accurately self-centering, and although somewhat expensive, is a valuable addition to the lathe. This chuck consists, first of all, of a socket for screw to fit the mandrel, and round flat plate of brass cast in one piece, as in Figure 28. This must be carefully turned and faced in the lathe. 2 pieces of iron or brass are then screwed to the face, as B, B, 28A, leaving a space between, the sides of which are to be truly parallel. These pieces may either be chamfered to form V pieces, or may be rectangular on their inner edges. At C, C, a part of each is cut away, and the outer or back plate is also filed down to receive the small plates DD. E shows a groove in which a screw lies, half of which has a right and half a left-handed thread. This is shown in Figure 29. It will be evident that if this screw is placed in the groove of the bottom plate, and its ends pass through the pieces DD, which are screwed to the plates, it can revolve in its bearings, but will have no endwise motion. The collar F resting in a recess under the top plate D. This screw passes through a projection in the back of the pair of dies, which projection also goes into the same slot in the back plate in which the screw works when turned by the key. Figure 27, B. The above being nicely fitted, the dies moving evenly but stiffly in their places, the plain top is screwed on, keeping all firmly together. This plate has a long opening or slot, figure 27, through which the jaws of the dies and part of the screw are visible. The ends of the screw should not project, as any such projection is calculated to bring to grief the knuckles of the turner, a consideration worth attention in every form of chuck. The squared ends of the screw lie in a recess in the small plates, as shown in the section of one of these plates, figure 28X. Into this recess, the key fits over the screw end, and by turning this, the dies are simultaneously moved asunder or closer together so as to grasp centrally, as in the jaws of a vise, any small article, such as a screw or short rod of metal placed between them. A similarly contrived chuck is often used under the name of a universal chuck for holding pieces of large diameter, and is very useful for taking pieces of ivory which have to be hollowed or otherwise worked, as will hereafter be detailed. In this case, the jaws may be semicircular in form, as figure 30. It is, however, evident that these two chucks have a rather limited range. The first can only be used for small work, and the only case in which the latter can take firm hold all round the work is when the jaws are just so far apart as that they form portions of the circumference of one and the same circle. Practically, they will hold the work tightly under an extended range of sizes, and they are thus of great use to the turner. The following is, however, more perfect in operation, from the fact that it has 4 jaws instead of 2 which meet concentrically. This may be made either with 2 long screws at right angles to each other, with right and left-handed threads to each, as in the die chucks, or more simply and, in some respects, more satisfactorily, with 4 distinct screws, all of the same pitch, and all with squared ends of equal size, to allow of the same key being used to turn them. It is possible to use such a chuck as an eccentric chuck if desired, which is certainly a recommendation in its favor over those which work always concentrically. The face of this chuck is shown in figure 31. The ends of the 4 screws have a bearing in the small center plate B, whilst the collars or flanges rest in a recess under the several plates C. The face of this chuck is graduated by each die, so that it is easy to set the jaws concentrically, or to place one or more eccentrically to take in work of other shape than round or square. The jaws of this form of chuck are used for 2 purposes, either to hold work inside them like a vise, or externally. A ring, for instance, requiring to be chased on the outside is slipped over the jaws, which are then caused to recede from the center so as to hold the work securely. If the latter does not run truly, one or more of the screws can be slackened and the opposite ones tightened, or if the eccentricity appears to be in an intermediate part, 2 adjacent screws will have to be thus slackened and the others tightened. On the whole, this is the most useful pattern of chuck. The following is a very excellent self-centering chuck, now coming into extensive use. It has been noticed in more than one periodical. The description annexed is extracted from the pages of the English Mechanic. Quote, "The chuck hereby illustrated seems to be a very convenient form, easily adjusted and holding the drill securely. It is also well adapted for holding wire to be threaded. Every piece of which it is composed is of cast steel well hardened. It can be furnished with a shank to fit the hole for the center, screwed on the spindle, or slipped on the center. No wrench is necessary, the gripe of the fingers being sufficient to secure the shank of any drill. The inventor claims that he has used a 1-inch drill and tenacious wrought iron in one of them, receiving a shank of only 3/8 of an inch diameter without using a wrench. End quote. Figure 31A represents the shell of the chuck with milled bosses for the fingers. The core, B, is threaded and receives a steel wire spring which is inserted into the rear of each jaw, so that when relieved from pressure, the jaw opens automatically. With this brief explanation, the operation of the chuck can be easily comprehended. These chucks are made of 2 sizes, one with the opening of 3/8 of an inch and the other of 3/16 of an inch, and they can be made of larger sizes. Patented by L. H. Olmsted, Stamford, Connecticut, United States, America. End of Section 5. Section 6 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Monthly Bulletin of the State College of Washington, Pullman, Washington. Volume 4, Number 7, December 1921. The Use of Ropes and Tackle. By H. J. Dana, Specialist in Experimental Engineering, and W. A. Pearl, Instructor in Mechanical Engineering. Engineering Bulletin Number 8. Engineering Experiment Station, H. V. Carpenter, Director, 1922. Entered as second-class matter, September 5th, 1919, at the Post Office at Pullman, Washington, under Act of August 24th, 1912. Introduction. Each year, old industries keep expanding, and new ones are created. In many of these, the use of hoists, tackle, rope transmissions, etc., is ever increasing in extent and importance. Information on the selection and use of ropes and tackles and the tying of knots is very scattering and incomplete. The purpose of this bulletin is to collect information from all the different sources possible and assemble it under one cover, in the hope that it may be valuable to people in many different fields of activity. It is not meant to be an advanced treatise for those who consider themselves already proficient in the use of rope and tackle, but is designed as an aid and reference to those less skilled in the art. A variety of knots and splices are shown with occasional suggestions as to their use and application. Some knots tie easily and are very secure, but are not so easy to untie. Others are easily and quickly tied, are secure, and yet are not difficult to untie. Some knots are suitable for small cords only, and others are adapted to large ships' hawsers. For these and other reasons, it is desirable to select the right knot for the job in hand. Nearly every individual, at some time or other, has gone camping. If he chanced to select a remote or inaccessible mountainside for a vacation trip, he probably had one or more pack animals to take in the supplies and camp outfit. How many could use the famous diamond hitch to fasten the pack on the horse's back so that it will not shift or fall off in transit? The desirability of correct selection with reference to the work to be done is also true of tackle sets. One type of tackle will give great mechanical advantage, but requires an excessive amount of rope, or requires frequent overhauling to complete the job, while another type, using the same equipment, will not give such great mechanical advantage, but does not require overhauling so often during the progress of the load. Rope is coming more and more into favor for the transmission of power, replacing gears and heavy leather belts. It is important that the proper sized sheave wheel be used with a rope of given diameter in order to secure the longest service from the transmission. It is also important that speed be considered in the calculation for necessary strength to transmit a certain amount of power. It is evident from these two instances alone that it is desirable that the selection of a rope transmission should be governed by the use of complete sets of data on the subject. Some of the knots, splices, etc., shown in this bulletin were found to have more than one name, or were called by different names by different authors. In such case, only the most commonly used term was selected. Knots. A knowledge of knots has saved many a life in storm and wreck, and if everyone knew how to tie a knot quickly and securely, there would be fewer casualties in hotel and similar fires where a false knot in the fire escape rope has slipped at the critical moment and plunged the victim to the ground. Many an accident has occurred through a knot or splice being improperly formed. Even in tying or roping a trunk, few people tie a knot that is secure and quickly made, and yet readily undone. How many can tie a tow rope to a car so it will be secure, and yet is easily untied after the car has been hauled out of the mud? Or suppose a rope was under strain, holding a large timber in midair, and a strand in the derrick guy rope shows signs of parting. How many could attach a rope each side of the weak spot to take the strain? The principle of a knot is that no two parts which lie adjacent shall travel in the same direction if the knot should slip. Knots are employed for several purposes, such as to attach two rope ends together, to form an enlarged end on a rope, to shorten a rope without cutting it, or to attach a rope to another rope or object. Desirable features of knots are that they may be quickly tied, easily untied, and will not slip under a strain. In a number of cases, a toggle is used either to aid in making the knot or make it easier to untie after a strain has been applied. A number of terms are commonly used in tying knots. The standing part is the principal portion or longest part of the rope. The bight is the part curved, looped, or bent while working or handling the rope in making a knot, and the end is that part used in forming the knot or hitch. The loose or free end of a rope should be knotted or whipped to prevent it from raveling while in use. Strength of knots. If a knot or hitch of any kind is tied in a rope, its failure under stress is sure to occur at that place. Each fiber in the straight part of the rope takes its proper share of the load, but in all knots the rope is cramped or has a short bend, which throws an overload on those fibers that are on the outside of the bend, and one fiber after another breaks until the rope is torn apart. The shorter the bend in the standing rope, the weaker the knot. The approximate strength of several types of knots in percent of full strength of a rope is given in the table below as an average of 4 tests. 1. Full strength of dry rope, 100%. 2. Eye splice over an iron thimble, 90%. 3. Short splice in rope, 80%. 4. Timber hitch, round turn and half hitch, 65%. 5. Bowline, slip knot, clove hitch, 60%. 6. Square knot, weaver's knot, sheet bend, 50%. 7. Flemish loop, overhand knot, 45%. Fastening knots. Figure 1. The overhand knot is the simplest of all knots to make. It is made by passing the loose end of the rope over the standing part and back through the loop. Figure 2. The double knot is made by passing the free end of the rope through the loop twice instead of but once, as in making an overhand knot. This is used for shortening or for a stop on a rope and is more easily untied than the overhand knot. It is also known as a blood knot from its use on whiplashes by slave drivers, etc. Figure 3. The figure 8 knot is similar to the overhand knot, except that the loose end of the rope is passed through the loop from the opposite side. It is commonly used to prevent a rope running through an eye or ring or tackle block. It is also used as the basis for ornamental knots, etc. Figure 4. The double figure 8 knot is made by forming a regular figure 8 and then following around with the end of the other rope, as shown. Figure 5. The square knot is probably the commonest and most useful of all knots. It is strong and does not become jammed when being strained. Take the ends of the two ropes and pass the left end over and under the right end, then the right end over and under the left. Beware of the granny knot, which is often mistaken for the square knot, but is sure to slip under strain. Figure 6. The reef knot is a slight modification of the square knot. It consists merely of using the bight of the left or right end instead of the end itself, and is tied exactly as is the square knot. This makes the knot easy to untie by pulling the free end of the bight or loop. Figure 7. If the square or reef knot is used to join two ropes of unequal diameter, the knot is apt to slip unless the ends of the rope are whipped as shown. Figure 8. A square knot joining two ropes of unequal size is apt to slip with a result similar to that shown. Figure 9. The open hand knot is made by tying an overhand knot with two rope ends lying parallel. It is better than a square knot for joining two ropes of unequal diameter. Grain binders use this knot. Figure 10. The granny knot is often mistaken for a square knot, and its use should by all means be avoided, as it is almost sure to slip when a strain is applied, unless the ends are whipped. For large rope, a granny knot with ends whipped will hold securely and is easy to untie. Figure 11. The fisherman's knot is a simple type of knot formed by two simple overhand knots slipped over the standing parts of the two ropes and drawn tight. It is valuable for anglers as the two lines may be drawn apart by merely pulling on the loose ends of the rope. Figure 12. The ordinary knot is used for fastening two heavy ropes together and is made by forming a simple knot with the end of one rope and then interlacing the other rope around it, as shown. Figure 13. Whipping the two ends of an ordinary knot makes it more secure. Figure 14. The weaver's knot is used to join small lines or threads and is made by forming a bight in one rope, passing the end of the second rope around the bight, back over itself, and through the bight. Weavers use this knot in tying broken threads. When pulled tight, both ends point backward and do not catch when pulled through the loom. Figure 15. The hawser knot or sheet bend is used for joining stiff or heavy ropes and is not to be confused with the weaver's knot. It resembles the bow line and is easily untied. Figure 16. The double sheet bend is similar to the hawser knot and is useful for the same purposes. Figure 17. The Garrick bend is commonly used for joining two heavy hawsers which are too stiff to bend easily. Figure 18. Another method of joining stiff hawsers is to use the half hitch and whipping. This is a satisfactory method of making a joint to be used for a considerable time. Figure 19. The slip knot as shown is a knot with many uses. Figure 20. The bowline knot is useful for forming a loop on the end of a rope. It is used frequently by stockmen to tie a horse or cow so that they will not choke themselves. It is always secure and easily untied. Use this knot in tying a tow rope to a car. Figure 21. The running bowline is used for the same purposes as the slip knot in Figure 19, but is much more secure. It will always run freely on the standing part of the rope and is easily untied. Figure 22. A loop knot is useful for making fast to the middle of a rope where the ends are not free. It will pull tight under strain and is not easily untied. Figure 23. The tomfool knot is formed in the middle of a rope and may be used for the same purpose as the loop knot, except in this case, either standing part of the rope may be strained without the knot failing or slipping. It can be used for holding hogs. Place one loop over the hog's snout and hold on to one rope. Release by pulling other rope. Can also be used from the ground for releasing hoisting tackle which has been used on a flagpole or other tall object. Figure 24. The boat knot is formed by the aid of a toggle on a rope whose ends are not free and is used for shortening or for stopping a ring on a taut line. Figure 25. The surgeon's knot is a modified form of the square knot, and if used with smooth cord, as in tying bundles, it holds very securely. The object of the double twist is to make the knot easy to tie without holding with the end of the finger. Figure 26. Bowline on the bight is easily made on the looped part of a rope which is double. It is used where a loop is desired which will not pull tight or choke and is easily untied. May be used for casting harness for horses. Figure 27. The Spanish bowline is a knot which may be made in the middle of a long rope or in a bight at the end, and gives two single loops that may be thrown over two separate posts or both thrown over one. Either loop will hold without slipping and is easily untied. Figure 28. The Flemish loop is similar to the fisherman's knot, Figure 11, except that it is used for forming a loop on the end of a rope instead of joining two ropes. The loop or eye will not close up when strained. Figure 29. The hawser knot with toggle is formed exactly the same as the regular hawser knot, except that the toggle is inserted for the purpose of making it easy to loosen the knot after a strain has been applied. Ending knots. A group of knots somewhat different from those already described are those used for ending ropes. Ending knots not only serve the purpose of giving a large end on the rope, but also take the place of whipping, in that they prevent the rope from unraveling. Sometimes an ending knot is also used for its ornamental value. Figure 30. A whipping applied as shown is employed for keeping loose ends from fraying or unraveling, where the use to which the rope is to be put will not permit of a knot on the end. Strong cord is used for whipping. In splicing ropes, the whipping is removed before the splice may be considered complete. Figure 31. The single crown, tucked, makes the rope end but slightly larger than the standing part, and serves to prevent the strands from unraveling. This gives a neat appearing end. To make this type of knot, leave the ends long enough so they can be brought down and tucked under the strands of the standing part. After tucking them under the first strand as shown, halve each strand and tuck it again under the next strand of the standing part, and continue this until the ends are completely tucked the whole length, thus giving a gradual taper to the end of the rope, and also giving a knot that will stand by itself. The single crown not tucked is not a good ending for a rope. Figure 32. The wall knot is frequently used as an ending knot to prevent unraveling. It is very satisfactory where the rope does not need to pass through a block or hole which is but slightly larger than itself. The wall knot may be tucked similar to the crown and makes a very secure ending for a rope. For small ropes, unlay the strands back, each 3 inches, and on larger ropes in proportion. Hold the rope in the left hand with the loose strands upward. With the right hand, take the end of strand number 1 and bring it across the loose end in position with the thumb of the left hand. Then take the rope, forming a loop and allowing the end to hang free. Hold strand number 2 and pass it under strand number 1, and hold it against the rope with the thumb of the left hand. Again with the right hand, take strand number 3 and pass it under strand number 2 and up through the first loop formed. Then draw each of the strands gradually until the knot is tightened. Figure 33. The Matthew Walker knot, or stopper knot, is similar to the wall knot, except the ends are inserted through 2 loops instead of 1 as in the wall knot. It can readily be made by loosely constructing the wall knot as explained before, and continuing as follows. Pass the end number 1 through the loop with 2, then end number 2 through the loop with 3, and number 3 through the loop with 1. Then gradually tighten the knot by drawing in a little at a time on each strand. Figure 34. The double wall or crown knot is made exactly the same as the single crown or wall knot, but instead of trimming off or tucking the ends in, they are carried around a second time, following the lay of the first as shown, and then the knot is pulled tight. When completed, the ends may be tucked in as was done in the single crown, or they may be trimmed off. Figure 35. The stevedore knot is similar to the overhand knot shown in Figure 1, except that the end of the rope is served around the standing part 2.5 times before it is tucked through the bight. It is used where a knot is desired to keep the rope from running through a block or hole. Shortening knots. A third type of knots are those which are used where a rope is too long, and where it is awkward to have the free ends hanging loose, or where the ends are in use and the slack must be taken up in the middle of the rope. These are known as shortening knots. They are also sometimes used merely for ornament. Figure 36. The chain knot is frequently used for shortening and is made by forming a running loop, then drawing a bight of the rope through the loop, and a second bight through the first, and so on, until the rope has been shortened sufficiently. The free end should then be fastened by passing a toggle or the end of the rope through this last loop. To undo this shortening is very simple, as all that is necessary is to either remove the toggle from the last loop, or remove the end of the rope if it were used, and then pull on the free end until the knot is completely unraveled. Figure 37. The whipped shortening, or bend shortening, is one of the most easily made and is well adapted to heavy ropes where a shortening must be made quickly and where it is not to withstand a heavy strain. Figure 38. Three-fold shortening is started by making an overhand knot and continuing to tuck the end through the loop 3 more times and drawing tight. Figure 39. The sheep shank, or dog shank as it is sometimes called, is one of the most widely used of all shortenings. It is made in several forms, but the first form shown, while adaptable to fairly stiff ropes, will not withstand much strain. It is used for shortening electric light cords. Figure 40. Sheep shank for free end rope is similar to the plain sheep shank, except the free end of the rope is passed through the loop. This makes a secure shortening, but it cannot be used where the ends of the rope are not free. Figure 41. A sheep shank with toggle is a plain sheep shank with the toggle inserted as shown, and makes the shortening as secure as that shown in Figure 38. It is also easily untied. Figure 42. Sheep shank with ends whipped is the same as in a plain sheep shank, except the loop is whipped to the standing part of the rope. This makes the shortening as secure as those shown in Figure 38 and Figure 39. Figure 43. Bow shortening is an ordinary knot in the middle of a rope in which a double bend has previously been made. It is not adapted to heavy ropes, nor will it stand a heavy strain successfully. Splices. In the use of ropes, occasion arises many times where it is necessary to join 2 ends together in such a way that the union is as strong as the rest of the rope, and still not too large or irregular to pass through a hole or a pulley block. Knots are unsuitable in that they will not pass through a block. They are unsightly, and usually are not as strong as the rest of the rope. The method of joining ropes to meet the above requirements is called splicing. There are 2 general types of rope splices, known as the short splice and the long splice. Other applications of the former are made in the eye splice and the cut splice. The long splice is almost always used in splicing wire rope, which runs through a block or over a sheave. Figure 44. The short splice is made as follows. The 2 ends to be joined are untwisted for a few inches, and the rope is whipped temporarily to prevent further unwinding. The end of each strand is also whipped temporarily to prevent unraveling. The strands may then be waxed if desired. The 2 rope ends are then locked together or married so that the strands from one end pass alternately between those from the other end. The strands from opposite sides are now in pairs. Take 2 strands from opposite sides as strands A and 1. Tie a simple overhand knot in its right-hand form. Similarly, with a right-hand knot, tie together the strands forming each of the pairs B and 2 and C and 3. Draw the knots tight, then pass each strand of the rope over the strand adjacent to it and under the next, coming out between 2 strands as at first. Repeat until the ends of the strands have been reached, leaving from 1/2 inch to 1.5 inches of ends hanging free, so that when the rope is put under repeated strain for the first few days, the stretching of the splice will not pull the ends from under the last strand under which they were tucked. After a few days' service, The free ends may be safely trimmed even with the face of the rope. After the splice has been completed by tucking the ends as above, remove whipping on strands and lay the splice on the floor and roll it under the foot, or in the case of a large rope, pound it with a mallet to make it round and smooth. The appearance of the splice is improved if the strands are divided in half just before the last tuck is made, and one half is cut off while the other half is used to complete the splice. This splice may also be made by simply laying the ropes together and then tucking them as above without first tying the simple overhand knots. A skilled workman frequently dispenses with the whipping in making a splice. Figure 45. An eye splice is so much smaller and neater than a knotted eye in the end of a rope that it is much to be preferred to the latter. The eye splice is made similar to the short splice, except that the strands on the end of the rope are unlaid for the full length of the splice. The ends are tucked under, over, and under, etc., the strands of the standing part of the rope. Stretch well and cut off the loose ends of the strands. Figure 46. Long splice. If it is desired to unite two rope ends so that the splices will pass through a pulley as readily and smoothly as the rope itself, what is known as a long splice is used. This is best suited as it does not cause an enlargement in the rope at the point where the splice is made. To make it, unlay the ends of two ropes to the length of at least 5.5 times the circumference of the rope. Interlace the strands as for the short splice. Unlay one strand and fill up the vacant space which it leaves with the strand next to it from the other rope end. Then turn the rope over and lay hold of the two next strands that will come opposite their respective lays. Unlay one, filling up the vacant space as before with the other. Take 1/3 out of each strand, knot the opposite 1/3s together, and heave them well in place. Tuck all 6 ends, once under adjacent strands, and having stretched the splice well, cut off the ends. The ending of successive pairs should occur at intervals in the splice as shown, and not at the two ends as in the short splice. Figure 47. A chain splice is used for splicing a rope into a chain end, which is required to travel through a block or small opening. It is also sometimes used for making an ordinary eye in the end of a rope. 4 or 6 strand rope lends itself more readily to this type of splice than does a 3-strand rope. To make a chain splice, unlay the strands more than for an eye splice, then unlay a little further 1 strand in a 3-strand rope and 2 strands in a 4-strand rope. Bend the two parts together and tie an overhand knot so that the divided strands will lay together again. Continue to lay the ends in by passing them through the eye. When the eye has been completely laid up, the remaining ends should be tucked in the standing part of the rope as in a very short splice. This makes an eye which will not pull out, even if the ends of the strands are only whipped without first tucking. It is especially valuable in forming smooth eyes in steel cable without the use of clamps. In this case, however, the eye must be made considerably longer than in the case of hemp rope. Figure 48. The cut splice is formed similar to the eye splice, except that the two rope ends are extended past each other and joined into the standing part of the ropes. This type of splice is frequently used to hold the rings in rope ladders. It can also be used where it is desired to attach a spar or rod to the middle of a line, hitches. The knots so far described are used mainly for fastening rope ends together or for ending a rope. A quite different class of knots is that used for fastening a rope to a stationary or solid object. This type of knots is known as hitches. Hitches, as well as other types of knots, should be easily made, should not slip under strains, and should be easily untied. If all ropes were the same size and stiffness, it would be possible to select 2 or 3 knots which would meet all requirements. But, since this is not true, and since a knot suitable for a silken fish line will not be satisfactory for a ship's hawser, we find a great variety of knots, each of which is designed to meet some special requirements of service. The following illustrations show a variety of the most typical and useful knots used on fiber or manila rope. Figure 49. The half hitch is good only for temporary fastenings where pull is continuous. It is usually used as part of a more elaborate hitch. Figure 50. The timber hitch is very similar to the half hitch, but is much more permanent and secure. Instead of the end being passed under the standing part once, it is wound around the standing part 3 or 4 times as shown. Figure 51. The clove or builder's hitch is more secure than either of the above hitches. It will hold fast on a smooth timber and is used extensively by builders for fastening the staging to upright posts. It will hold without slipping on wet timber. It is also used to make the scaffold hitch. Figure 52. The rolling hitch is made by wrapping the rope 3 or 4 times around the object to which it is to be fastened, and then making 2 half hitches around the standing part of the rope. It is then drawn tight. This hitch is easily and quickly made and is very secure. Figure 53. This illustrates another type of rolling hitch, very similar to the above, but which is not as secure under a heavy strain. Figure 54. The snubbing hitch is made by passing the rope around the object to which it is desired to fasten it, and then making what is known as a taut line hitch, figure 68, about the standing part of the rope. Figure 55. Timber hitch and half hitch is a combination of the 2 separate hitches shown in figure 49 and figure 50. It is more secure than either used alone. Figure 56. The chain hitch is a combination of the above hitch and 2 or more half hitches. It is used for hauling in a larger rope or cable with a tow line, etc. Figure 57. The twist hitch is more secure than the half hitch, and it is suitable only where the strain is continuous. Figure 58. Twist and bow hitch is similar to the simple twist hitch, but is easier to untie. Figure 59. The blackwall hitch is widely used as illustrated. The greater the strain, the more securely it holds, but it is unreliable if the rope is slack. This hitch can be used with chain as well as rope. Figure 60. The lark's head with toggle is easily made and is used as a rule where it is desired to have a type of hitch which is easily and quickly released. Figure 61. Round turn and half hitch is suitable for a more or less permanent method of attaching a rope to a ring. Whipping the end to the standing part of the rope makes it quite permanent. Figure 62. The fisherman's hitch is used for fastening large ropes or lines to rings and is very similar to the hitch shown in figure 61. It is improved by whipping the free end to the standing part. Figure 63. The cat's paw hitch is suitable for attaching a hook to the middle part of a rope where the ends are not free. Strain may be taken on either or both ends. It is easily released. Figure 64. The slippery hitch is easily made, but has the objection that it draws very tight under strain, making it hard to untie. Figure 65. The double black wall is similar to the single black wall and is used for the same purpose. Figure 66. The slip knot and half hitch constitute a combination that is used for the same purpose as the Flemish loop. It is made by first tying a slip knot so that it will run on the short end of the rope, then complete by tying a half hitch with the short end as shown. Figure 67. The fisherman's bend is similar to the fisherman's hitch, except that the half hitches are replaced with whipping. Figure 68. A taut line hitch is used for attaching a rope to another rope already under strain, where no slack is available for making any other hitch. It is not secure unless pulled very tight. A few threads of hemp or marlin served about the taut line for the knot to pull against will improve the hitch. Figure 69. The jam hitch is used in tying up light packages, such as bundles of lath, small boxes, rolls of paper, and the like. It is a hitch that will slide along a cord in one direction, but will jam and hold against moving the other way, and will be found exceedingly convenient. The jam hitch will answer the requirements, provided the cord is large enough and of not too hard a body, nor too smooth a surface. Figure 70. The scaffold hitch is very useful for slinging a scaffold so that it will not turn in the sling. It is started by making a clove hitch with the two free ends of the rope below the scaffold. Then draw each rope back on itself and up over opposite sides of the board, where the short end is joined to the other with a bowline. Plenty of slack in the clove will make it possible to draw the bight of each end out to the edge of the scaffold, as shown in the left of the figure. The two illustrations at the right of the figure show another method of making a scaffold hitch. Wrap the rope around the scaffold plank so that it crosses the top of the plank 3 times. Pull the middle loop as shown by the arrow and fold it down over the end of the plank, resulting, as shown in the illustration, immediately to the left of the arrow. This is completed by attaching the free end to the standing part with a bowline. Both hitches are equally good. Figure 71. The studding sail bend is frequently employed on shipboard for attaching a rope or line to a spar. Figure 72. The midshipman's hitch is somewhat similar to the snubbing hitch shown in Figure 54, but is perhaps a little easier to make if the rope is under strain while being tied. Figure 73. A bale sling, as shown, is useful where it is necessary to hoist an object to which it is difficult to attach the hoisting tackle. It may be used on bales, sacks, kegs, etc. Figure 74. The hamburger hitch is useful in connection with a bale sling which is too long for the object it is carrying. It is also used to balance the load where 2 slings are used. The sling is placed around the load as in Figure 73. Then, with the loop end of the sling, form a second loop as shown. Where the 2 ropes cross, start to tie a square or reef knot. Draw up the loops as shown, resulting in the hamburger hitch. This may be adjusted by running the knot up or down the rope while slack, but it will not slip under strain. Figure 75. Sling for a cask, head up, is very useful where it is desired to hoist an open barrel of water or lime or other material. Tie an ordinary knot over the barrel lengthwise. Then separate the 2 ropes in the middle of the twisted part and drop them over the head of the cask or barrel. Fasten the 2 rope ends together above the barrel as shown with a bowline. Figure 76. A well pipe hitch is used in hoisting pipe, where no special clamp is available for attaching the hoisting tackle to the pipe. The hitch shown will pull tighter the harder the strain, and is also easy to untie. Pull up all slack possible in the coils when forming the hitch, in order to prevent slipping when the strain is first applied. Figure 77. The hackamore hitch is commonly known and used as an emergency rope bridle or halter in the western part of the United States. Among sailors, it is known as a running Turk's head, and it may be used in carrying a jug or other vessel of similar shape. When used for a halter, about 20 feet will be required. The knot is started by forming a bight in the center of the rope. Proceed as indicated in the successive illustrations shown. The result will be a running Turk's head. Draw together the two center ropes, forming a bridle complete with bit, nose piece, head piece, and reins. Such a bridle is not suitable for continuous use, to be sure, but it will be found useful in an emergency. Figure 78. The halter tie is a knot preferred by some persons for use in hitching or in tying the halter rope in the stall. If properly set, it is secure and may be used in some cases in place of the underhand bowline knot. The halter tie should never be used around a horse's neck, because if the tie is not set up correctly, it forms a slip knot, and its use might result in strangulation of the animal. In completing the tie, draw the end through and set the knot by pulling first on the short end. This is important. If the long rope is pulled first and the kinks in it are straightened out, the tie forms a slip knot, being simply two half hitches around the rope. Figure 79. Horse hitch or tie is commonly used by farmers and stockmen to tie a horse or cow with a rope so it will not choke itself. Tie an overhand knot in the standing part of the rope and leave open. Tie another overhand knot or a stevedore knot in the end of the rope. Loop the rope around the animal's neck and insert the knotted end through the open overhand knot. This hitch will not slip and choke the animal. Figure 80. The manger tie is used for tying a horse or other animal to a manger or stanchion or hitching rack. The end of the halter rope is first passed through the hole in the manger. With a bight or loop on the free end of the rope, tie a slip knot on the standing part. Stick the free end of the rope through the loop or bow as shown. This knot is easily and quickly tied, but under great strain will pull tight, making it hard to untie. Figure 81. The figure 8 manger tie is superior to the ordinary manger tie in that it will not pull tight under heavy strain, such as would occur if the animal became frightened and attempted to break away. Pass the free end of the rope through the hole in the manger or around the hitching rack. Form a bight or loop with the free end of the rope and hold the loop along the standing part. With the free end, form another loop and serve around both the first loop and the standing part. Complete the tie by inserting the second loop through the first loop and secure by inserting the free end of the rope through the second loop as shown. This is easily untied by first withdrawing the free end from the loop and then pulling on same until knot is untied. Figure 82. The harness hitch is employed for forming a loop on a rope in such a way that strain may be applied to both ends and to the loop without slipping. Start to tie an overhand knot as shown. Reach through between the two twisted parts and draw the opposite side of the loop through, following the arrow. The completed harness hitch appears as shown. Figure 83. The strap hitch or line knot is used to join the free ends of two leather driving lines on a team. It may be employed as an emergency tie for a broken line or strap, but is not to be recommended as a permanent repair. Figure 84. The clevis hitch is used for forming a loop on the end of a rope, which is both secure under strain and easily untied. The diamond hitch. The present age of high-speed transportation, both on land and water, and in the air as well, has served to crowd pack animal transportation back into the hills and into those few regions where rail and sail have not yet penetrated. As a consequence, pack trains are fast becoming unknown, and the skill of the packer is fast being forgotten. The skill of the experienced packer is little short of marvelous, where he can catch a more or less wild pack animal and attach from 100 to 400 or 500 pounds of stuff to his back so securely that it will ride all day without coming off. Different types of freighting, of course, gave rise to different methods of binding on the load, but the more widely used was, no doubt, some form of the famous diamond hitch. The early trappers of the Hudson's Bay Company are credited with introducing the diamond hitch among the Northwest Indians, and old trappers of the period of 1849, engaged in freighting to California, claim that the Mexicans used it at that time. Different packers have modified and used the diamond hitch to suit their needs. As an example, in rough country where there is frequent trouble with pack animals falling with their load, some packers tie the diamond hitch so that the final knot is on top of the animal's back, where it can be easily reached and loosened with the animal down. Under more favorable conditions, other packers use a diamond hitch in which the final tie is made on the side of the animal near the cinch hook. In fact, out of a group of old packers from different localities, the probability is that no two would tie the diamond hitch alike in every particular. The following illustrations of the diamond hitch are shown only as types actually in use by different men in the packing business. Other packers may have different methods of tying it more suited to the type of load they are handling. The cuts shown represent the appearance of the diamond hitch if the cinch were cut under the animal's belly and the pack were flattened out and laid on the floor with the ropes undisturbed. This method clearly shows in one picture all the different parts of the hitch, so that those interested may follow it in making the hitch for themselves. The government uses a Spanish pack saddle, or what is known as an aparejo, pronounced aparejo, but civilian packers often use the cross-tree saddle. It consists of a padded board resting on each side of the animal's backbone. These two padded boards are usually fastened together, with two cross trees resembling a sawbuck. There are different methods of placing the load on the saddle preparatory to lashing it fast with the diamond hitch. No attempt will be made to give complete instructions in packing. The hitches shown are given with the hope they will serve the prospective camper on his vacation to a retreat in the hills, or perhaps satisfy the interest of those who have heard of the diamond hitch but have never seen it tied. End of Section 6. Section 7 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Concrete Construction, Methods and Cost, by Halbert P. Gillette. Member, American Society of Chemical Engineers. Member, American Institute of Mechanical Engineers. Managing Editor, Engineering Contracting. And Charles S. Hill, Chemical Engineer. Associate Editor, Engineering Contracting. New York and Chicago. The Myron C. Clark Publishing Company, 1908. Preface. How best to perform construction work and what it will cost for materials, labor, plant, and general expenses are matters of vital interest to engineers and contractors. This book is a treatise on the methods and cost of concrete construction. No attempt has been made to present the subject of cement testing, which is already covered by Mr. W. Purvis Taylor's excellent book, nor to discuss the physical properties of cements and concrete, as they are discussed by Falk and by Sabin, nor to consider reinforced concrete design, as do Tourneur and Maurer, or Buell and Hill, nor to present a general treatise on cements, mortars, and concrete construction, like that of Reed or of Taylor and Thompson. On the contrary, the authors have handled the subject of concrete construction solely from the viewpoint of the builder of concrete structures. By doing this, they have been able to crowd a great amount of detailed information on methods and costs of concrete construction into a volume of moderate size. Though the special information contained in the book is of most particular assistance to the contractor or engineer engaged in the actual work of making and placing concrete, it is believed that it will also prove highly useful to the designing engineer and to the architect. It seems plain that no designer of concrete structures can be a really good designer without having a profound knowledge of methods of construction and of detailed costs. This book, it is believed, gives these methods and cost data in greater number and more thoroughly analyzed than they can be found elsewhere in engineering literature. The costs and other facts contained in the book have been collected from a multitude of sources, from the engineering journals, from the transactions of the engineering societies, from government reports, and from the personal records of the authors and of other engineers and contractors. It is but fair to say that the great bulk of the matter contained in the book, though portions of it have appeared previously in other forms in the author's contributions to the technical press, was collected and worked up originally by the authors. Where this has not been the case, the original data have been added to and reanalyzed by the authors. Under these circumstances, it has been impracticable to give specific credit in the pages of the book to every source from which the authors have drawn aid. They wish here to acknowledge, therefore, the help secured from many engineers and contractors, from the volumes of Engineering News, Engineering Record, and Engineering Contracting, and from the transactions of the American Society of Civil Engineers, and the proceedings and papers of various other civil engineering societies and organizations of concrete workers. The work done by these journals and societies in gathering and publishing information on concrete construction is of great and enduring value and deserves full acknowledgement. In answer to any possible inquiry as to the relative parts of the work done by the two authors in preparing this book, they will answer that it has been truly the labor of both in every part. HPG CSH, Chicago, Illinois, April 15th, 1908. Chapter 1. Methods and cost of selecting and preparing materials for concrete. Concrete is an artificial stone produced by mixing cement mortar with broken stone, gravel, broken slag, cinders, or other similar fragmentary materials. The component parts are therefore hydraulic cement, sand, and the broken stone or other coarse material commonly designated as the aggregate. Cement. At least a score of varieties of hydraulic cement are listed in the classifications of cement technologists. The constructing engineer and contractor recognize only 3 varieties: Portland cement, natural cement, and slag or puzzle cement. All concrete used in engineering work is made of either Portland, natural, or slag cement, and the great bulk of all concrete is made of Portland cement. Only these 3 varieties of cement are, therefore, considered here, and they only in their aspects having relation to the economics of construction work. For a full discussion of the chemical and physical properties of hydraulic cements, and for the methods of determining these properties by tests, the reader is referred to Practical Cement Testing by W. Purvis Taylor. Portland cement. Portland cement is the best of the hydraulic cements, being made from a rigidly controlled artificial mixture of lime, silica, and alumina. The product of the best mills is a remarkably strong, uniform, and stable material. It is suitable for all classes of concrete work and is the only variety of hydraulic cement allowable for reinforced concrete or for plain concrete having to endure hard wear or to be used where strength, density, and durability of high degree are demanded. Natural cement. Natural cement differs from Portland cement in degree only. It is made by calcining and grinding a limestone rock containing naturally enough clayey matter, silica, and alumina to make a cement that will harden under water. Owing to the imperfection and irregularity of the natural rock mixture, natural cement is weaker and less uniform than Portland cement. Natural cement concrete is suitable for work in which great unit strength or uniformity of quality is not essential. It is never used for reinforced work. Slag cement. Slag cement has a strength approaching very closely that of Portland cement, but as it will not stand exposure to the air, slag cement concrete is suitable for use only under water. Slag cement is made by grinding together slaked lime and granulated blast furnace or slag. Size and weight of barrels of cement. The commercial unit of measurement of cement is the barrel. The unit of shipment is the bag. A barrel of Portland cement contains 380 pounds of cement, and the barrel itself weighs 20 pounds. There are 4 bags, cloth or paper sacks, of cement to the barrel, and the regulation cloth sack weighs 1.5 pounds. The size of cement barrels varies due to the differences in weight of cement and to differences in compacting the cement into the barrel. A light burned Portland cement weighs 100 pounds per struck bushel. A heavy burned Portland cement weighs 118 to 125 pounds per struck bushel. The number of cubic feet of packed Portland cement in a barrel ranges from 3 to 3.5. Natural cements are lighter than Portland cement. A barrel of Louisville, Akron, Utica, or other Western natural cement contains 265 pounds of cement and weighs 15 pounds itself. A barrel of Rosendale or other Eastern cement contains 300 pounds of cement, and the barrel itself weighs 20 pounds. There are 3 3/4 cubic feet in a barrel of Louisville cement. Usually there are 3 bags to a barrel of natural cement. As stated above, the usual shipping unit for cement is the bag, but cement is often bought in barrels or, for large works, in bulk. When bought in cloth bags, a charge is made of 10 cents each for the bags, but on return of the bags, a credit of 8 to 10 cents each is allowed. Cement bought in barrels costs 10 cents more per barrel than in bulk, and cement ordered in paper bags costs 5 cents more per barrel than in bulk. Cement is usually bought in cloth sacks which are returned, but to get the advantage of this method of purchase, the user must have an accurate system for preserving, checking up, and shipping the bags. Where any considerable amount of cement is to be used, the contractor will find that it will pay to erect a small bag house or to close off a room at the mixing plant. Provide the enclosure with a locked door and with a small window into which the bags are required to be thrown as fast as emptied. One trustworthy man is given the key and the task of counting up the empty bags each day to see that they check with the bags of cement used. The following rule for packing and shipping is given by Gilbreth. Footnote: Field System, Frank B. Gilbreth, Myron C. Clark Publishing Company, New York and Chicago. End footnote. Quote, pack cement bags laid flat, one on top of the other in piles of 50. They can then be counted easily. Freight must be prepaid when cement bags are returned, and bills of lading must be obtained in duplicate, or credit cannot be obtained on shipment. End quote. The volumes given above are for cement compacted in the barrel. When the cement is emptied and shoveled into boxes, it measures from 20 to 30% more than when packed in the barrel. Mr. Clarence M. Foster is authority for the statement that Utica cement barrels measure 16¼ inches across at the heads, 19½ inches across the bilge, and 25¾ inches in length under heads, and contain 3.77 cubic feet. When 265 pounds of Utica natural hydraulic cement are packed in a barrel, it fills it within 2½ inches of the top and occupies 3.45 cubic feet, and this is therefore the volume of a barrel of Utica hydraulic cement packed tight. Specifications and testing. The great bulk of cement used in construction work is bought on specification. The various government bureaus, state and city works departments, railway companies, and most public service corporations have their own specifications. Standard specifications are also put forward by several of the national engineering societies, and one of these, or the personal specification of the engineer, is used for individual works. Buying cement to specification necessitates testing to determine that the material purchased meets the specified requirements. For a complete discussion of the methods of conducting such tests, the reader is referred to Practical Cement Testing by W. Purvis Taylor. According to this authority, a field testing laboratory will cost for equipment $250 to $350. Such a laboratory can be operated by 2 or 3 men at a salary charge of from $100 to $200 per month. 2 men will test on average 4 samples per day, and each additional man will test 4 more samples. The cost of testing will range from $3 to $5 per sample, which is roughly equivalent to 3 cents per barrel of cement, or from 3 to 5 cents per cubic yard of concrete. These figures are for field laboratory work reasonably well conducted under ordinarily favorable conditions. In large laboratories, the cost per sample will run somewhat lower. Sand. Sand constitutes from 1/3 to 1/2 of the volume of concrete. When a large amount of concrete is to be made, a contractor cannot, therefore, afford to guess at his source of sand supply. A long haul over poor roads can easily make the sand cost more than the stone per cubic yard of concrete. Properties of good sand. Engineers commonly specify that sand for concrete shall be clean and sharp, and siliceous in character. Neither sharpness nor excessive cleanliness is worth seeking after if it involves much expense. Tests show conclusively that sand with rounded grains makes quite as strong a mortar, other things being equal, as does sand with angular grains. The admixture with sand of a considerable percentage of loam or clay is also not the unmixed evil it has been supposed to be. Myron S. Falk records a number of elaborate experiments on this point. Footnote: Cements, Mortars, and Concretes by Myron S. Falk. Myron C. Clark Publishing Company, Chicago, Illinois. End footnote. These experiments demonstrate conclusively that loam and clay in sand, to the amount of 10 to 15%, result in no material reduction in the strength of mortars made with this sand as compared with mortars made with the same sand after washing. There can be no doubt but that for much concrete work, the expense entailed in washing sand is an unnecessary one. The only substitute for natural sand for concrete that need be considered practically is pulverized stone, either the dust and fine screenings produced in crushing rock, or an artificial sand made by reducing suitable rocks to powder. As a conclusion from the records of numerous tests, M.S. Falk says, quote, "It may be concluded that rock screenings may be substituted for sand, either in mortar or concrete, without any loss of strength resulting. This is important commercially, for it precludes the necessity of screening the dust from crushed rock, and avoids, at the same time, the cost of procuring a natural sand to take its place." End quote. The principal danger in using stone dust is failure to secure the proper balance of different size grains. This is also an important matter in the choice of natural sands. Sand composed of a mixture of grains ranging from fine to coarse gives uniformly stronger mortars than does sand with grains of nearly one size, and as between a coarse and a fine sand of one size of grains, the coarse sand gives the stronger mortar. Further data on the effect of size of grains on the utility of sand for concrete are given in Chapter 2, in the section on voids in sand, and for those who wish to study in detail the test data on this and the other matters referred to here, the authors recommend Cements, Mortars, and Concretes, Their Physical Properties by Myron S. Falk. Cost of sand. A very common price for sand in cities is $1 per cubic yard delivered at the work. It may be noted here that as sand is often sold by the load instead of the cubic yard, it is wise to have a written agreement defining the size of a load. Where the contractor gets his sand from the pit, its cost will be the cost of excavating and loading at the pit, the cost of hauling in wagons, the cost of freight and rehandling it if necessary, and the cost of washing added together. An energetic man working under a good foreman will load 20 cubic yards of sand into wagons per 10-hour day. With a poor foreman, or when laborers are scarce, it is not safe to count on more than 15 cubic yards per day. With wages at $1.50 per day, this will make the cost of loading 10 cents per cubic yard. The cost of hauling will include the cost of lost team time and dumping, which will average about 5 cents per cubic yard. With 1 cubic yard loads, wages of team 35 cents per hour, and speed of travel 2.5 miles per hour. The cost of hauling proper is 1/2 cent per 100 feet, or 27 cents per mile. Assuming a mile haul, the cost of sand delivered, based on the above figures, will be 10 cents plus 5 cents plus 1/2 cent per 100 feet equals 15 plus 27 cents equals 42 cents per cubic yard. Freight rates can always be secured, and it is usually safe to estimate the weight on a basis of 2,700 pounds per cubic yard. For a full discussion of the cost of excavating sand and other earths, the reader is referred to Earth Excavation and Embankments, Methods and Cost by Halbert P. Gillette and Daniel J. Hauer. Methods and Cost of Washing Sand. When the available sand carries considerable percentages of loam or clay, and the specifications require that clean sand shall be used, washing is necessary. The best and cheapest method of performing this task will depend upon the local conditions and the amount of sand to be washed. Washing with hose. When the quantity of sand to be washed does not exceed 15 to 30 cubic yards per day, the simplest method, perhaps, is to use a hose. Build a wooden tank or box 8 feet wide and 15 feet long, the bottom having a slope of 8 inches in the 15 feet. The sides should be about 8 inches high at the lower end and rise gradually to 3 feet in height at the upper end. Close the lower end of the tank with a board gate about 6 inches in height and sliding in grooves so that it can be removed. Dump about 3 cubic yards of sand into the upper end of the tank and play a 3/4 inch hose stream of water on it, the hose man standing at the lower end of the tank. The water and sand flow down the inclined bottom of the tank where the sand remains and the dirt flows over the gate and off with the water. It takes about an hour to wash a 3 cubic yard batch, and by building a pair of tanks so that the hose man can shift from one to the other, washing can proceed continuously, and one man will wash 30 cubic yards per 10-hour day at a cost, with wages at $1.50, of 5 cents per cubic yard. The sand, of course, has to be shoveled from the tank, and this will cost about 10 cents per cubic yard, making 15 cents per cubic yard for washing and shoveling, and to this must be added any extra hauling and, if the water is pumped, the cost of pumping, which may amount to 10 cents per cubic yard for coal and wages. Altogether, a cost of from 15 to 30 cents per cubic yard may be figured for washing sand with a hose. Washing with sand ejectors. When large quantities of sand are to be washed, use may be made of the sand ejector system, commonly employed in washing filter sand at large water filtration plants. Water under pressure is required. In this system, the dirty sand is delivered into a conical or pyramidal hopper, from the bottom of which it is drawn by an ejector and delivered mixed with water into a second similar hopper. Here the water and dirt overflow the top of the hopper, while the sand settles and is again ejected into a third hopper or to the stockpile or bins. The system may consist of anywhere from 2 to 6 hoppers. Figure 1 shows a 2-hopper layout, and Figure 2 shows a 4-hopper layout. In the first plant, the washed sand is delivered into bins so arranged, as will be seen, that the bins are virtually a third washing hopper. The clean sand is chuted from these bins directly into cars or wagons. In the second plant, the clean sand is ejected into a trough, which leads it into buckets handled by a derrick. The details of one of the washing hoppers for the plant shown by Figure 1 are illustrated by Figure 3. At filter plants, the dirty sand is delivered mixed with water to the first hopper by means of ejectors stationed in the filters and discharging through pipes to the washers. When, as would usually be the case in contract work, the sand is delivered comparatively dry to the first hopper, this hopper must be provided with a sprinkler pipe to wet the sand. In studying the ejector washing plants illustrated, it should be borne in mind that for concrete work, they would not need to be of such permanent construction as for filter plants. The washers would be mounted on timber frames, underground piping would be done away with, etc. At best, however, such plants are expensive and will be warranted only when the amount of sand to be washed is large. The usual assumption of waterworks engineers is that the volume of water required for washing filter sand is 15 times the volume of the sand washed. At the Albany, New York filters, the sand passes through 5 ejectors at the rate of 3 to 5 cubic yards per hour and takes 4,000 gallons of water per cubic yard. 1 man shovels sand into the washer and 2 take it away. Based on an output of 32 cubic yards in 10 hours, Mr. Allen Hazen estimates the cost of washing as follows. 3 men at $2 per day, $6. 110,000 gallons of water at 5 cents, $5.50. Total, 32 cubic yards at 36 cents, $11.50. Washing with tank washers. Figure 4 shows a sand washer used in constructing a concrete lock at Springdale, Pennsylvania, in United States government improvement work on the Allegheny River. The device consisted of a circular tank 9 feet in diameter and 7 feet high, provided with a sloping false bottom perforated with 1-inch holes, through which water was forced as indicated. A 7.5 by 5 by 6-inch pump with a 3-inch discharge pipe was used to force water into the tank, and the rotating paddles were operated by a 7-horsepower engine. This apparatus washed a batch of 14 cubic yards in from 1 to 2 hours at a cost of 7 cents per cubic yard. The sand contained much fine coal and silt. The above data are given by Mr. W. H. Roper. Another form of tank washer, designed by Mr. Allen Hazen for washing bank sand at Yonkers, New York, is shown by Figure 5. This apparatus consisted of a 10 by 2.5 by 2.5 foot wooden box with a 6-inch pipe entering one end at the bottom and there branching into 3 3-inch pipes, extending along the bottom and capped at the ends. The undersides of the 3-inch pipes were pierced with 1/2-inch holes 6 inches apart, through which water under pressure was discharged into the box. Sand was shoveled into the box at one end, and the upward currents of water raised the fine and dirty particles until they escaped through the waste troughs. When the box became filled with sand, a sliding door at one end was opened, and the batch discharged. The operation was continuous as long as sand was shoveled into the box. By manipulating the door, the sand could be made to run out with a very small percentage of water. Sand containing 7% of dirt was thus washed so that it contained only 0.6% dirt. The washer handled 200 cubic yards of sand in 10 hours. The above data are given by F. H. Stevenson. A somewhat more elaborate form of tank washer than either of these described is shown by Figure 6. This apparatus was used by Mr. George A. Soper for washing filter sand at Hudson, New York. The dirty sand was shoveled into a sort of hopper, from which it was fed by a hose stream into an inclined cylinder, along which it traveled and was discharged into a wooden trough provided with a screw conveyor and closed at both ends. The water overflowing the sides of the trough carried away the dirt, and the clean sand was delivered by the screw to the bucket elevator, which hoisted it to a platform, from which it was taken by barrows to the stockpile. A 4-horsepower engine with a 5-horsepower boiler operated the cylinder, screw, elevator, and pump. 4 men operated the washer and handled 32 cubic yards of sand per day. With wages at $1.50, the cost of washing was 20 cents per cubic yard. In constructing a concrete block dam at Lynchburg, Virginia, sand containing from 15 to 30% of loam, clay, and vegetable matter was washed to a cleanliness of 2 to 5% of such matter by the device shown by Figure 7. A small creek was diverted, as shown, into a wooden flume terminating in 2 sand tanks. By means of the swinging gate, the flow was passed through either tank as desired. The sand was hauled by wagon and shoveled into the upper end of the flume. The current carried it down into one of the tanks, washing the dirt loose and carrying it off with the overflow over the end of the tank, while the sand settled into the tank. When one tank was full, the flow was diverted into the other tank, and the sand in the first tank was shoveled out, loaded into wagons, and hauled to the stockpile. As built, this washer handled about 30 cubic yards of sand per 10-hour day, but the tanks were built too small for the flume, which could readily handle 75 cubic yards per day, with no larger working force. This force consisted of 3 men at $1.50 per day, making the cost for a 30 cubic yard output 15 cents per cubic yard for washing. None of the figures given above includes the cost of handling the sand to and from the washer. When this involves much extra loading and hauling, it amounts to a considerable expense, and in any plan for washing sand, the contractor should figure, with exceeding care, the extra handling due to the necessity of washing. Aggregates. The aggregates commonly used in making concrete are broken or crushed stone, gravel, slag, and cinders. Slag and cinders make a concrete that weighs considerably less than stone or gravel mixtures, and being the products of combustion, are commonly supposed to make especially fire-resisting concrete. Their use is, therefore, confined very closely to fireproof building work, and in fact, to floor construction for such buildings. Slag and cinder concretes are for this reason given minor consideration in this volume. Broken stone. Stone produced by crushing any of the harder and tougher varieties of rock is suitable for concrete. Perhaps the best stone is produced by crushing trap rock. Crushed trap, besides being hard and tough, is angular and has an excellent fracture surface for holding cement. It also withstands heat better than most stone. Next to trap, the hard, tough, crystalline limestones make perhaps the best all-around concrete material. Cement adheres to limestone better than to any other rock. Limestone, however, calcines when subjected to fire, and is therefore objected to by many engineers for building construction. The harder and denser sandstones, mica schists, granites, and syenites make good stone for concrete, and occasionally shale and slate may be used. Gravel. Gravel makes one of the best possible aggregates for concrete. The conditions under which gravel is produced by nature make it reasonably certain that only the tougher and harder rocks enter into its composition. The rounded shapes of the component particles permit gravel to be more closely tamped than broken stone and give less danger of voids from bridging. The mixture is also generally a fairly well-balanced composition of fine and coarse particles. The surfaces of the particles, being generally smooth, give perhaps a poorer bond with the cement than most broken stone. In the matter of strength, the most recent tests show that there is very little choice between gravel and broken stone concrete, slag and cinders. The slag used for concrete aggregate is iron blast furnace slag, crushed to its proper size. Cinders for aggregate are steam boiler cinders. They are best with the fine ashes screened out and should not contain more than 15% of unburned coal. Balanced aggregate. With the aggregate, as with the sand for concrete, the best results, other things being equal, will be secured by using a well-balanced mixture of coarse and fine particles. Usually, the product of a rock crusher is fairly well balanced, except for the very fine material. There is nearly always a deficiency of this, which, as explained in a succeeding section, has to be supplied by adding sand. Usually, also, the engineer accepts the crusher product, coarser than screenings, as being well enough balanced for concrete work, but this is not always the case. Engineers occasionally demand an artificial mixture of varying proportions of different sized stones, and may even go so far as to require gravel to be screened and reproportioned. This artificial grading of the aggregate adds to the cost of the concrete in some proportion, which must be determined for each individual case. Size of aggregate. The size of aggregate to be used depends upon the massiveness of the structure, its purpose, and whether or not it is reinforced. It is seldom that aggregate larger than will pass a 3-inch ring is used, and this only in very massive work. The more usual size is 2.5 inches. For reinforced concrete, 1 1/4 inches is about the maximum size allowed, and in building work, 1-inch aggregate is most commonly used. Some constructors use no aggregate larger than 3/4 inch in reinforced building work, and others require that for that portion of the concrete coming directly in contact with the reinforcement, the aggregate shall not exceed 1/4 to 1/2 inch. The great bulk of concrete work is done with aggregate smaller than 2 inches, and as a general thing, where the massiveness of the structure will allow of much larger sizes, it will be more economic to use rubble concrete. See Chapter 6. Cost of aggregate. The locality in which the work is done determines the cost of the aggregate. Concerns producing broken stone or screened and washed gravel for concrete are to be found within shipping distance in most sections of the country, so that these materials may be purchased in any amount desired. The cost will then be the market price of the material freight on board cars at plant, plus the freight rates and the cost of unloading and haulage to the stockpiles. If the contractor uses a local stone or gravel, the aggregate cost will be, for stone, the costs of quarrying and crushing and transportation, and for gravel, the cost of excavation, screening, washing, and transportation. screened or crusher-run stone for concrete. Formerly, engineers almost universally demanded that broken stone for concrete should have all the finer particles screened out. This practice has been modified to some considerable extent in recent years by using all the crusher product, both coarse and fine, or, as it is commonly expressed, by using run-of-crusher stone. The comparative merits of screened and crusher-run stone for concrete work are questions of comparative economy and convenience. The fine stone dust and chips produced in crushing stone are not, as was once thought, deleterious. They simply take the place of so much of the sand which would, were the stone screened, be required to balance the sand and stone mixture. It is seldom that the proportion of chips and dust produced in crushing stone is large enough to replace the sand constituent entirely. Some sand is nearly always to be added to run-of-crusher stone, and it is in determining the amount of this addition that uncertainty lies. The proportions of dust and chips in crushed stone vary with the kind of stone and with the kind of crusher used. Furthermore, when run-of-crusher stone is chuted from the crusher into a bin or pile, the screenings and the coarse stones segregate. Examination of a crusher-run stone pile will show a cone-shaped heart of fine material enclosed by a shell of coarser stone. Consequently, when this pile of stone is taken from to make concrete, a uniform mixture of fine and coarse particles is not secured. The material taken from the outside of the pile will be mostly coarse, and that from the inside mostly fine. This segregation, combined with the natural variation in the crusher product, makes the task of adding sand and producing a balanced sand and stone mixture one of extreme uncertainty and some difficulty, unless considerable expenditure is made in testing and reproportioning. When the product of the crusher is screened, the task of proportioning the sand to the stone is a straightforward operation, and the screened-out chips and dust can be used as a portion of the sand if desired. The only saving, then, in using crusher-run stone direct is the very small one of not having to screen out the fine material. The conclusion must be that the economy of unscreened stone for concrete is a very doubtful quantity, and that the risk of irregularity in unscreened stone mixtures is a serious one. The engineer's specifications will generally determine for the contractor whether he is to use screened or crusher-run stone, but these same specifications will not guarantee the regularity of the resulting concrete mixture. This will be the contractor's burden, and if the engineer's inspection is rigid and the crusher-run product runs uneven for the reasons given above, it will be a burden of considerable expense. The contractor will do well to know his product, or to know his man, before bidding less or even as little on crusher-run as on screened stone concrete. Cost of quarrying and crushing stone. The following examples of the cost of quarrying and crushing stone are fairly representative of the conditions which would prevail on ordinary contract work. In quarrying and crushing New Jersey trap rock with gyratory crushers, the following was the cost of producing 200 cubic yards per day: $106.50 per day, 53.3 cents per cubic yard. The quarry face worked was 12 to 18 feet, and the stone was crushed to 2-inch size. Owing to the seamy character of the rock, it was broken by blasting into comparatively small pieces, requiring very little sledging. The stone was loaded into one-horse dump carts, the driver taking one cart to the crusher while the other was being loaded. The haul was 100 feet, The carts were dumped into an inclined chute leading to a number 5 gates crusher. The stone was elevated by a bucket elevator and screened. All stone larger than 2 inches was returned through a chute to a number 3 gates crusher for recrushing. The cost given above does not include interest, depreciation, and repairs. These items would add about $8 to $10 more per day, or 4 to 5 cents per cubic yard. In quarrying limestone, where the face of the quarry was only 5 to 6 feet high, and where the amount of stripping was small, 1 steam drill was used. This drill received its steam from the same boiler that supplied the crusher engine. The drill averaged 60 feet of hole drilled per 10-hour day, but was poorly handled and frequently laid off for repairs. The 4 men quarrying barred out and sledged the stone to sizes that would enter a 9 by 16-inch jaw crusher. The 6 men wheeling delivered the stone in wheelbarrows to the crusher platform, the run plank being never longer than 150 feet. 2 men fed the stone into the crusher, and a bin man helped load the wagons from the bin and kept tally of the loads. The stone was measured loose in the wagons, and it was found that the average load was 1.5 cubic yards, weighing 2,400 pounds per cubic yard. There were 40 wagon loads, or 60 cubic yards, crushed per 10-hour day, although on some days as high as 75 cubic yards were crushed. The stone was screened through a rotary screen, 9 feet long, having 3 sizes of openings, 1/2 inch, 1 1/4 inch, and 2 1/4 inch. The output was 16% of the smallest size, 24% of the middle size, and 60% of the larger size. All tailings over 2.5 inches in size were recrushed. It will be noticed that the interest on the plant is quite an important item. This is due to the fact that year in and year out, a quarrying and crushing plant seldom averages more than 100 days actually worked per year, and the total charge for interest must be distributed over these 100 days, and not over 300 days, as is so commonly and erroneously done. The cost of stripping the earth off the rock is often considerably in excess of the above given cost, and each case must be estimated separately. Quarry rental or royalty is usually not in excess of 5 cents per cubic yard, and frequently much less. The dynamite used was 40%, and the cost of electric exploders is included in the cost given. Where a higher quarry face is used, the cost of drilling and the cost of explosives per cubic yard is less. Exclusive of quarry rent and heavy stripping costs, a contractor should be able to quarry and crush limestone or sandstone for not more than 75 cents per cubic yard, or 62 cents per ton of 2,000 pounds, wages and conditions being as above given. The labor cost of erecting bins and installing a 9 by 16 jaw crusher, elevator, etc. averages about $75, including hauling the plant 2 or 3 miles and dismantling the plant when work is finished. For a full discussion of quarrying and crushing methods and costs, and for descriptions of crushing machinery and plants, the readers referred to Rock Excavation, Methods and Cost by Halbert P. Gillette. Screening and washing gravel. Handwork is resorted to in screening gravel only when the amount to be screened is small and when it is simply required to separate the fine sand without sorting the coarser material into sizes. The gravel is shoveled against a portable inclined screen through which the sand drops, while the pebbles slide down and accumulate at the bottom. The cost of screening by hand is the cost of shoveling the gravel against the screen divided by the number of cubic yards of saved material. In screening gravel for sand, the richer the gravel is in fine material, the cheaper will be the cost per cubic yard for screening. On the contrary, in screening gravel for the pebbles, the less sand there is in the gravel, the cheaper will be the cost per cubic yard for screening. The cost of shoveling divided by the number of cubic yards shoveled is the cost of screening only when both the sand and the coarser material are saved. Tests made in the pit will enable the contractor to estimate how many cubic yards of gravel must be shoveled to get a cubic yard of sand or pebbles. An energetic man will shovel about 25 cubic yards of gravel against a screen per 10-hour day and keep the screened material cleared away, providing no carrying is necessary. A mechanical arrangement capable of handling a considerably larger yardage of material is shown by Figure 8. 2 men and a team are required. The team is attached to the scraper by means of the rope passing through the pulley at the top of the incline. The scraper is loaded in the usual manner, hauled up the incline until its wheels are stopped by blocks, and then the team is backed up to slacken the rope and permit the scraper to tip and dump its load. The trip holding the scraper while dumping is operated from the ground. The scraper load falls onto an inclined screen, which takes out the sand and delivers the pebbles into the wagon. By erecting bins to catch the sand and pebbles, this same arrangement could be made continuous in operation. In commercial gravel mining, the gravel is usually sorted into several sizes, and generally it is washed as well as screened. Where the pebbles run into larger sizes, a crushing plant is also usually installed to reduce the larger stones. Works producing several hundred cubic yards of screened and washed gravel per day require a plant of larger size and greater cost than even a very large piece of concrete work will warrant, so that only general mention will be made here of such plants. The commercial sizes of gravel are usually 2 inches, 1 inches, 1/2 inch, and 1/4 inch, down to sand. No very detailed costs of producing gravel by these commercial plants are available. At the plant of the Lake Shore and Michigan Southern Railway, where gravel is screened and washed for ballast, the gravel is passed over a 2 inch, a 3/4 inch, a 1/4 inch, and a 1/8 inch screen in turn, and the fine sand is saved. About 2,000 tons are handled per day. The washed gravel, 2 inches to 1/8 inch sizes, represents from 40 to 65% of the raw gravel and costs from 23 to 30 cents per cubic yard for excavation, screening, and washing. The drawings of Figure 9 show a gravel washing plant having a capacity of 120 to 130 cubic yards per hour, operated by the Stewart Peck Sand Company of Kansas City, Missouri. Where washing alone is necessary, a plant of 1 or 2 washer units like those here shown could be installed without excessive cost by a contractor at any point where water is available. Each washer unit consists of 2 hexagonal troughs 18 inches in diameter and 18 feet long. A shaft carrying blade set spirally is rotated in each trough to agitate the gravel and force it along. Each trough also has a fall of 6 inches toward its receiving end. The 2 troughs are enclosed in a tank or box, and above and between them is a 5-inch pipe having 3/4 inch holes 3 inches apart, so arranged that the streams are directed into the troughs. The water and dirt pass off at the lower end of the troughs, while the gravel is fed by the screws into a chute discharging into a bucket elevator, which in turn feeds into a storage bin. The gravel to be washed runs from 2 inches to 1/8 inch in size. It is excavated by steam shovel and loaded into 1.5 cubic yard dump cars, 3 of which are hauled by a mule to the washers, where the load is dumped into the troughs. The plant, having a capacity of 120 to 130 cubic yards per hour, cost $25,000, including pump and an 8-inch pipeline a mile long. A 100-horsepower engine operates the plant, and 20 men are needed for all purposes. This plant produces washed gravel at a profit for 50 cents per cubic yard. End of Section 7. Section 8 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Petroleum by Albert Lidgett, editor of the Petroleum Times, late editor of the Petroleum Review. London, Sir Isaac Pitman and Sons, Limited, 1 Amen Corner, EC4, Bath, Melbourne, and New York. Chapter 3. How Petroleum is Produced. Time was when the engineering aspect of the production of petroleum was practically non-existent. The ancients, and even those of the last century, were content to resort to the most primitive means for winning petroleum from the earth. Shallow wells were sunk or dug by hand, the eventual securing of the oil being carried out by lowering primitive receptacles, generally leather bottles, into the hole. It was a period long before the advent of the oil age, and the methods employed were clearly in keeping with the mode of life of that day. In practically every oil-producing field of the world, though in this respect the United States is almost an exception, the history records the fact that for many years the extraction of oil from the ground was confined to the use of the primitive methods which held sway in those days, those associated with the operations of the hand-dug wells. In the Far East, notably in Japan, we find the first serious attempts to obtain and utilize petroleum, for as far back as AD 615, there were shallow wells in existence, from which the burning water, as it was called, was collected. In Romania and Russia, too, the earlier attempts to create a petroleum industry were confined to these methods. It was only when the demand for petroleum became large and consistently increased with the opening up of new fields that we find other and more practical methods were introduced for winning larger quantities of the oil from the earth. Today, in every branch of the industry associated with petroleum, whether it be in producing the crude oil, in transporting it, or in refining nature's product into those numerous commodities which are part and parcel of everyday life, the engineering aspect is one of very great importance. In fact, throughout the petroleum industry, engineering science is the alpha and omega. By its means, we are now able to carefully study the nature of the ground at depths of 6,000 feet, and to extract from the deep-lying strata a wealth of minerals. We are able, too, to transport thousands of tons of crude oil daily across thousands of miles of continent, while is it not the direct result of engineering science which allows over 15,000 tons of petroleum products to be carried across the oceans of the world in one vessel with the same ease that one would take a rowing boat from one side of a lake to another? Great, however, as have been the degrees of progress recorded in connection with drilling for petroleum, the old methods, generally speaking, and which date back to the days of early China, are still largely copied in all pole and percussion systems of drilling. And though steam has replaced manual labor, and electricity now bids fair to replace steam, the operating principles today are the same as then. The only exception, of course, is the advent and growing popularity of the rotary method of drilling, to which interesting phase of the subject I will briefly refer later. The old Eastern method of drilling has obviously been the forerunner of the Canadian, Standard, and other systems of today, the wire rope replacing the use of poles. In oil field work, the principal types of percussion drills used are known: 1. As the Pennsylvanian cable, 2. The Canadian pole, and 3. The Russian free-fall system. And though from time to time many attempts have been made to introduce modifications of these, the vast majority have been unsuccessful in their operation. The Pennsylvanian cable system was used for drilling the earliest oil wells in the United States, and doubtless took its name from the fact that it was so largely used in that oil region. As may also be gathered from the name, the principal feature in this system is the cable by which the tools are suspended and connected to the walking beam. There is no doubt that this system of drilling, which has been so universally used in the oil fields, gives most satisfactory results. When first introduced in Pennsylvania, the cable system of drilling was particularly simple and did remarkably good work, for the reason that the strata usually encountered was of such a nature that it did not cave, and, as a result, the well pipe was only lowered when the full depth of that string had been drilled. The drilling bits were seldom more than 4 inches thick. In order to give a rotary motion to the bit, the continuous twisting of the cable to and fro was necessary, but when in other fields, where deeper strata had to be explored, the cable system was introduced. The semi-sandy nature of the strata called for wells of larger diameter, with correspondingly larger drilling bits. As a consequence of the additional weight of the drilling bit, it was found that the swing of the tools was sufficient to give them a rotating movement for the drilling of a circular hole. In regions where caving in of the walls of the wells was liable to occur, the string of pipe had to closely follow the tools, which, with the old Pennsylvanian type of rig, meant frequent winding of the cable from the bull wheel, so as to allow of the well pipes being handled. In order to prevent the waste of time which these operations occasioned, the calf wheel was added, by means of which the pipe could be lowered into the hole without the removal of the drilling cable. This cable almost invariably was of the manila character, and in many instances this rope is retained today, though wire ropes have been introduced frequently. The Canadian pole system, which is largely in use in oil field operations, is, like the first mentioned method of drilling, of the percussion type, the chief essential difference being that, instead of a cable connecting the tools to the surface, poles are used. In former times, these poles were of ash wood, but with the extended use of the system, iron rods took their place. The introduction of these iron rods was a distinct advantage, for they could be welded to whatever lengths are required, whereas the wooden poles, which were seldom more than 20 feet long, had to be spliced for practical work. The rig used with the Canadian system is not so powerful as that for the Pennsylvanian method, but the one great advantage of the Canadian system is that, for the drilling of shallow oil wells, it could be operated by men of less experience. The success which has attended the operation of the pole system lies in the fact that although drilling by its means is very slow, for seldom is 250 feet per month exceeded, it is one of the best methods of drilling through complicated strata, and, in the hands of conscientious men, does highly satisfactory work. It might be of interest to very briefly refer to the operations of the system when a well is being drilled. The rig, that is, the superstructure above ground, is quite a simple framing, 70 or more feet high, with a base of about 20 feet. The power is usually derived from a steam engine, with the usual means for operating the gear from the derrick. Fuel found locally, natural gas, or other form of heating agent used. One shaft and 2 spools running in bearings transmit the various motions desired, the drive being taken up by a pulley attached to the main shaft. On this shaft are keyed 2 band pulleys, which communicate by belting with 2 spools running immediately overhead in the upper part of the framework. Fastened to one extremity of the main shaft is a disc crank, which, through the medium of a connecting rod, transmits an oscillating movement to an overhead pivoted walking beam. In all systems of percussion drilling, the drilling bit is raised and then dropped a distance of several feet, the result being that the strata to be drilled are steadily pounded away. As the ground is pulverized by the percussion tools, the debris has to be cleared away so as to enable the drill to fall freely and to deliver clean blows to the unbroken strata, and this work is performed by appliances known as balers and sand pumps. There is no need for me to go into the numerous technical details regarding this or any other system of drilling, for my only desire is to give a general impression as to the usual methods adopted for the winning of petroleum. I will therefore pass on to deal briefly with the Russian free-fall system so much in vogue in the Russian fields. Incidentally, I may here say that when drilling for oil in Russia, one has to recollect several features which are not common to the development of other oil fields. Bearing in mind the great depth to which wells have to be sunk to reach the prolific oil horizons in the majority of the fields in Russia, which necessitates starting the well with a very large diameter, frequently 30 inches, it will be easily appreciated that the loss of a hole in the course of drilling is a very expensive affair. The Russian free-fall system of boring necessitates patient and hard manual labor. It is, as its name implies, of the percussion type, and is, in fact, a modified pole tool system which well suits the local conditions. The clumsy drilling tools have a practically free drop, being picked up when the walking beam is at its lowest point, and released at the top of the stroke. When released, the tools naturally force their way downwards in the strata, and are released only with difficulty, although in a measure this difficulty is minimized on account of the fact that the under-reaming, slightly enlarging the diameter of the hole, is done simultaneously with the drilling. After a Russian well has been started by means of a slip hook suspended from a haulage rope, and a depth of some 30 feet obtained, the free fall is added to the string of tools. This free fall is composed of 2 separate parts, the rod and the body, and these are held together by means of a wedge working in vertical slots cut in the sides of the body. In operating the free fall, the handles, fixed to the temper screw, are held by the driller. On the downward stroke, these are pushed forward from right to left, but as soon as the downward stroke is completed, they are quickly pulled backwards. The steel wedge enters the recess, and the tools are carried to the top of the stroke, where, by a quick forward jerk, the wedge is thrown clear of the recess, and the tools drop freely, the momentum of the string of tools driving the drilling bit deeper into the hole. After several feet of the hole are drilled, the tools have to be withdrawn in order to allow the pulverized mass of debris to be cleared away, while, owing to the caving nature of the strata, it is necessary to case the well as drilling proceeds. As I have said, the system is very cumbersome, but in the hands of experienced men, it does its work well, if but slowly. There are many cases on record where, when the well has assumed a considerable depth, it has been completely spoiled by the carelessness of the operators. But, more often than not, this has been deliberate, for the Caucasian oil field worker has many grievances, admittedly more or less imaginary. During recent years, the rotary method of drilling has been successfully adopted, and it is in regard to this revolutionary method of speedy drilling that I will now touch upon. The rotary method of drilling made its debut in Texas some 14 years ago, and since then it is not any exaggeration to say that nearly 20,000 wells for oil have been drilled with the system, which has found popularity in all the oil fields of the world. Its main operation is simplicity itself. A rigid stem of heavy pipe rotates a fishtail drilling bit at the bottom of the hole, cutting and stirring up the formation to be drilled. It cuts its way through the underground formations, much in the same way as a screw, when rotated, forces its way through wood. It is the essence of speed in drilling, for, unlike the necessary principles to be adopted in the percussion methods of drilling, the rotary drill does not have to be lifted from the hole for the purposes of clearing. The pulverized strata are continuously washed from the hole by a stream of water reaching the bottom of the drill. Very frequently, a pressure-fed mud is used, and this serves the double purpose, for in its return to the surface, it tends to plaster the walls of the well. The mud emerges in streams of high velocity from the two apertures in the drilling bit, for in its downward course it is carried through the drilling pipe or stem, but naturally loses this velocity considerably in its return to the surface. It is, however, very easy to detect the kind of stratum being drilled through from the returned cuttings, these reaching the surface but a few minutes after the drilling bit has entered the formation. From time to time, various grievances have been ventilated against this improved system of boring for petroleum, but today its adoption is worldwide, and by its use, wells which, with the old-fashioned method of drilling, would take many months, if not 2 or 3 years, are now got down to the producing horizons in but a few weeks. It is, in fact, solely due to the ever-increasing use of the rotary drill that the universally increased demands for petroleum products have been met by an ever-increasing production of the crude oil. Leaving the question of drilling methods, I cannot fail to mention the interesting fact that in oil field operations, progress is now being recorded in another direction, and that is by the increasing utilization of electrical power in the place of steam. At the time of writing, it is safe to say that fully 60% of the power requirements on the oil field is provided for by steam plants with their attendant waste. Oil and gas engines, with their greater efficiency, may claim to be operated to an extent of 35%, while not more than 5% of the requirements are satisfied by the use of electric motors. There is no doubt that prejudice has had a deal to do with the very minimized use of electrical power on the oil fields in the past, but this is being gradually swept aside, and, in the next few years, I have no doubt that both electrical manufacturers and the petroleum industry generally will materially benefit from the use of this cheap and very economical form of power. In the past, many disastrous oil field conflagrations have been due solely to the use of open-fired engines in close proximity to the wells, but with the use of electrical energy, this fire danger will be rapidly removed. Before closing this chapter, I would say a word or two with respect to the bringing into the producing stage of the oil wells when once they have been drilled. In the early history of oil-held developments, it was not infrequent to find the crude oil ejected from the well by natural pressure. But today it is the exception to find those oil fountains which have made the early history of the Russian oil fields so famous. In many of the fields, explosives are used to promote the flow of oil, and when the well comes into production, the ordinary methods of bailing or pumping are resorted to. Compressed air is also used for bringing about and sustaining production. The quantity of air and the periods of admission naturally vary with the diameters of the wells, the amount of gas present, the level of the liquid, etc., which latter also determines the pressure of air necessary. The natural exhaustion of oil wells can obviously have no remedy, but areas conveying that impression can often be revived by methods, the study of which is being carefully continued. As I write, I find that the officials of the United States Bureau of Mines, who have been studying this question of exhaustion, have arrived at the conclusion that from 20 to as much as 90% of the crude oil remains in the strata tapped by the well, even when it is abandoned as no longer capable of profitable production. This conclusion opens up what may prove someday to be a most interesting chapter in oil field history. Chapter 4. The Refining of Petroleum. Inasmuch as the aim of this little volume is to interest other than those who are directly associated with the petroleum industry, I shall endeavor in this chapter to refer to the refining of petroleum in a manner which shall be readily understood by the reader, and shall, wherever possible, refrain from entering into those highly technical matters which do not lend themselves to popular expression. The refining of crude oil as it is produced from the earth consists in the classification of its various hydrocarbons by means of fractional distillation into the various products which so largely enter into our commercial and domestic life of today. The refined products, in the order in which they are received by distillation, are motor spirit, illuminating oils, solar oils, lubricating oils, fuel oils, residuum, etc. The first mentioned being the lightest, and the last the heaviest in specific gravity. Almost simultaneously with the discovery of petroleum, there sprung up the first attempts to refine nature's product, and though these early experiments were of a most primitive character, they doubtless served their purpose admirably. In this respect, probably the most primitive oil refinery in the world was built near the Tigris, in Mesopotamia. Crude petroleum varies in its character, for while certain crudes are pale in color and almost transparent, others are almost black and viscid. Some indeed would appear to have undergone a course of refining by nature itself, for in some fields the crude oil will freely burn in lamps without any refining treatment. In the vast majority of cases, however, the crude oil, as withdrawn from the producing wells, represents a liquid somewhat like molten tar. The chemical composition of petroleum consists essentially of carbon and hydrogen, together with oxygen and varying amounts of nitrogen and sulfur. The crude from Pennsylvania, and this is the finest crude in the United States, consists chiefly of a large number of hydrocarbons of the paraffin series, whilst in the Russian petroleums, the predominant constituents are naphthenes or polymethyllenes. Then the crude petroleum of the Dutch Indies and Burma is of a different character from that found elsewhere, for in it aromatic hydrocarbons are largely present. The various series of hydrocarbons found in crude oils, the paraffins and naphthenes, readily lend themselves to conversion into other compounds of carbon and hydrogen by dissociation, and this conversion produces compounds of higher volatility, such as motor spirits, etc. When the compounds of hydrogen and carbon are submitted to distillation, certain chemical changes occur, as the result of which other series of hydrocarbons are formed. And though it is not my intention here to dive into this comparatively new realm of chemical investigation, it is interesting to mention that, by carrying the treatment of the compound still further, it is possible to obtain aromatic hydrocarbons, including trinitrotoluene, generally known as the explosive TNT, in addition to various dye products. In the earlier methods of refining, the stills usually consisted of a vertical cylinder in which the charge of crude oil was distilled almost to dryness. But this method was completely revolutionized many years ago, especially in the United States, by the introduction and immediate success of a principle known as the cracking process, and by the separation of the distillation into two portions, one for the removal of the more volatile constituents in the crude oil, such as motor spirit, and the other for the treatment of the heavier products. I will first deal with the method of refining known as the straight process, or the process which does not involve cracking. At one time, the refiner had to consider the salability of his refined products before he commenced to refine them, but today, with the perfect system which prevails for the handling of huge quantities of refined products and the transporting of them to the most distant markets, the one desire of the refiner is, naturally, to secure from his treatment of the crude oil as many refined products as possible, always keeping an eye on the production of the largest quantities of the higher-priced products than upon those which are of low value. The process of refining to be applied to any particular oil naturally depends upon its composition as shown by analysis. It may be that the crude oil to be treated, apart from containing a small percentage of distillates with a low boiling point, motor spirit, is principally made up of residues of little value except as fuel, or, on the other hand, it may be that the crude oil is of high quality and contains all possible products. In the former case, the process of distillation is brief, and the plant inexpensive, as compared with the lengthy process of full refining necessitated in the latter case. The refining operations consist of three distinct branches. 1. The distillation. 2. The extracting of paraffin and refining. And 3. The chemical treatment. When only a small percentage of the low boiling fractions has to be removed from the crude oil, the process is known as topping, and a convenient form of apparatus for the purpose is the tower still. This consists of a vertical cylinder fitted with perforated plates resting at intervals on pipes through which superheated steam travels. The pipes serve the double purpose of conveying the steam to its inlet and of heating the oil to be distilled. The steam, on entering the cylinder, ascends, meeting the crude oil, as it descends from plate to plate in a regulated stream, and carrying with it to the outlet the light fractions which the operation is intended to remove. A few years ago, a Californian chemist invented an improvement of the principles of maximum heating and evaporating surfaces. His name was Trumbull, and the process is known as the Trumbull process. The crude oil is heated to the desired temperature in pipes or retorts set in a primary furnace, the hot gases of combustion from which are utilized to heat the distillation chamber proper. Entering the vertical cylinder at the top, the oil is spread over and through perforated plates, falling on a cone-shaped plate to divert the continuous stream of oil to the sides of the still, down which it flows in a thin film. Other conical plates, arranged at intervals underneath, maintain the flow in the desired channel until it reaches the outlet at the bottom. When 60 or 70%, comprising the motor spirit series, the kerosenes, and perhaps the intermediate fractions, are to be removed, it is common practice to distill the crude oil in a series of stills, cylindrical in shape, connected continuously. The best-known system is that patented 35 years ago by Mr. Henderson of the Broxburn Oil Company Limited for the distillation of shale oil, and since adopted by many refiners of petroleum. In this system, the crude oil flows from a charging tank by gravity through a preheater heated by the passage from the second or other still of distillates of suitable temperature, and thence into the first still. Here it is raised to distillation temperature, and the specific gravity of the distillate therefrom fixed. The feed of the crude oil is constant, the residue formed in the still passing through a connection at the bottom into the second still in the series at the top, and led from back to front so that the inlet and outlet shall be as far apart as possible. It is here raised to a higher temperature, yielding a distillate of higher specific gravity, the residue passing on to the next still, and so on through the series of stills until it reaches the point where all the motor spirit, or benzene as it is called, kerosene, and the intermediate distillates are removed. The distillates obtained from the refining of the crude are usually purified by treatment successively with sulfuric acid and solution of caustic soda, this process of chemical treatment being necessary before the products are fit for the market. The cracking process of distillation briefly consists in distilling the oils at a temperature higher than the normal boiling points of the constituents it is desired to decompose, and in practice, the result is that the heavier oils are turned into lighter hydrocarbons of lower boiling points. Thus, the yield of the more valuable of the refined products is materially increased. The cracking process, which very largely obtains today, was quite accidentally discovered by a small refiner in America many years ago. The man in charge of the still left it with the intention of returning very shortly. He was, however, absent for several hours, and to his dismay found that, as the result of his neglect in attending to the still, a very light-colored distillate of much lower density than that which it was usual to obtain was issuing from the condenser. Upon investigation, it was found that a portion of the distillate had condensed upon the upper part of the still, which was cooler, and had dropped back into the still, where the temperature was sufficient to produce products of a lower boiling point, certainly a distinct improvement. As may be imagined, this cracking process does not commence until the lighter products of distillation have been removed, and is now so popular because by its use a greater yield can be obtained of those more valuable products for which there is an ever-increasing demand. It is unnecessary here to enter into those various improvements which have been introduced from time to time, all of which have as their aim the production of larger quantities of refined oils, and it would likewise be invidious to enumerate even the more popular scientists to whose energies much of the resulting progress has been due, for the simple reason that it has never been the aim of the petroleum chemist to turn his abilities in the direction indicated. As may be imagined, the industry of petroleum refining has had to adapt itself to the altered conditions of today. For instance, prior to the advent of the internal combustion engine, which now is responsible for such a wide application of motor spirit, the demand for this, the lightest product of petroleum distillation, was non-existent. Consequently, when such spirit was produced, there was no market for it, and its production represented sheer loss to the refiners. Both in the Far East and in Russia, we have examples of the enormous loss which accrued to the refiners by reason of there being no market for this highly inflammable product. In the Far Eastern fields in particular, this loss was very heavy, for in the earlier days of its operations, the Shell Company had to remove thousands of tons of this now valuable motor spirit from its refineries and burn it in the open fields. The successful introduction of the internal combustion engine, however, completely changed the aspect of petroleum refining, and the desire became general not to see how little motor spirit could be produced, but to perfect methods by which the yield of the benzene series of hydrocarbons should be as large as possible. Even today, progress is still being recorded in this direction, and each American refiner is vying with his neighbor as to how far that output of gasoline, as it is there called, can be increased. Many and varied are the means which have been resorted to for this purpose, but most of them have reference to improvements in the processes for refining the crude oil. One, however, is worthy of being mentioned in this little treatise, inasmuch as it deals with quite another aspect of the problem of increased motor spirit supply. As I have mentioned in another chapter, enormous quantities of natural gas exude from the oil wells, and this in the past has been for the most part allowed to go to waste in the air, causing an ever-present danger to oil field operations on account of its liability to ignite. Being heavier than the air itself, for it is impregnated with oil gases, it remains for long periods in the lower air strata, and consequently, not infrequently, has been the direct cause of great oil field fires. This gas, casing head gas as it is termed, comes from the oil wells between the casing and the tubing, and in the case of numerous wells, the flow is remarkable, some wells giving forth 300,000 cubic feet of gas every 24 hours, and the only useful purpose that this vapor has served until recent years has been to light several towns situated comparatively near to the oil-producing fields. The great volume of the gas, however, has been allowed to go to waste. But experiments have proved that the gas is capable of condensation into motor spirit, and the general yield of such spirit may be taken as fully 2 gallons per 1,000 cubic feet of natural gas treated. What wonderful possibilities lie in the direction of the conversion of this vapor into motor spirit! The oil producers in the United States have not been slow to appreciate this, and today there are hundreds of plants in the United States which have been erected solely to condense these oil well gas vapors. Some of these plants are dealing with as much as 3 million cubic feet of gas a day. The most recent official returns available from the United States show that the production of gasoline, motor spirit, from this process of oil gas condensation is approximately 150 million gallons per annum, and even this substantial figure is being steadily increased. There is also another phase of the oil refining industry which, during recent years, has materially altered. I refer to the production of solar oil during distillation. It is an apt saying that we can scarcely look to any section of our commercial or domestic life without being confronted with the fact that oil products play some part therein. There are few, however, who, without reflection, would agree that when they light their gas, they are dependent upon petroleum for much of the light the gas gives. It is nevertheless a fact, as I will proceed to show. Many years ago, the oil refiners in Baku were confronted with a problem which appeared for some time to be insurmountable. After the distillation of their kerosene, or illuminating oil, and before they could commence to take off the lubricating oil fractions, there was an intermediary product which, while being of no use for lamp oil, did not possess the necessary constituents of viscosity to make it acceptable as a lubricant. It was a fairly decent volume of something for which there was no market at the time. Experiments were made, and with these the name of Dr. Paul Dvorkovits will ever be associated, and it was found that by the passage of a current of gas over the surface of this intermediate product, the gas caught up, as it were, a richness which materially increased the lighting power of the gas. To cut a long but highly interesting story short, this solar or gas oil was subsequently introduced by Dr. Dvorkovits to England for gas enrichment purposes, and the extent of its employment today may be judged from the fact that the United Kingdom regularly imports between 60 million and 70 million gallons per annum for the enrichment of the coal gas, which finds useful employment in practically every home throughout the land. As is known, the gas companies have to produce gas of a certain lighting quality, and it is in the upholding of the lighting strength of the gas that solar oil today plays so important a part. At first, the oil came almost exclusively from Russia, but now the competition from the United States has secured for our American friends the vast bulk of the trade, which, as I have shown, has reached enormous proportions. Solar oil is also largely utilized for the production of refined perfumery oils, which are quite colorless and inodorous, while the finest quality is used in pharmacy and known as paraffinum liquidum, and is in much demand, but in this connection it is the Russian petroleums that have gained distinction. It was held for many years that such tasteless and colorless oils could not be produced from the United States petroleums, but from the commencement of the European War and the consequent closure of Russia's export port, whereby all overseas trade in Russian petroleums was held up, much progress was made in the manufacture of tasteless medicinal petroleums in the United States, such articles having now become popular throughout the world. One of the most important discoveries made during recent years has been the finding of large quantities of toluol in petroleum. This article is necessary for the manufacture of high explosives. In Borneo heavy petroleum, toluol exists to a very large extent, and it was its discovery and consequent use by the Allies, thanks to the offer made to the governments by Sir Marcus Samuel, Bart, that almost unlimited quantities of high explosives were manufactured. Vaseline is another useful commodity which is derived from the refining of crude petroleum, and this article is turned out of the American refineries as well as those of Russia and Galicia in large quantities, but, beyond mentioning this fact, no useful purpose would here be served by relating the various processes employed. With reference to the methods generally adopted in the refining of the products from the distillation of the Scottish oil shales, these are briefly dealt with in the chapter devoted to the Scottish oil industry. It is safe to say that the past 2 or 3 decades have witnessed marked progress in perfecting the methods by which crude petroleums are refined into the innumerable common commodities of commerce, and it is doubtful whether in any branch of chemical research there has been such concerted energy shown as in regard to the refining of mineral oils. Signs, however, are not wanting to show that the zenith of this project has by no means been reached. Chapter 5. Transport by Land and Sea. The remarkably perfect methods by which petroleum and its products are transported by land and sea before they reach the consumer may not at first sight appear to be anything but commonplace, but a moment's reflection will be sufficient to suggest that a vast and complete organization must be required in order that petroleum may be brought from practically the ends of the earth to the consumer in the most remote village in the British Isles. But it is the demands of necessity that have been responsible for the building up of this vast organization of transportation, which represents, in the United States alone, the investment of many millions of pounds sterling. Taking first the methods of oil transportation by land, in no other oil-producing country do we find such an elaborate system for dealing with enormous quantities of petroleum as in America, for it is safe to say that at least 500,000 barrels of crude oil have to be dealt with daily at the present time. Going back to the time when petroleum first became a commercial commodity, when the first wells in Oil Creek commenced to open up a period of new prosperity for the United States, these wells were situated so close to the water that their product could easily be loaded into canoes and barges and floated down the Allegheny River. In the dry season, the flow was insufficient to float the craft, and then some hundreds of the boats, carrying each from 50 to 1,000 barrels, would be assembled in a mill pond near the wells, and the water impounded while the loading was in progress. Then the gates would be opened, and the fleet, carried on the flood of rushing water, would be hurried down the river in charge of pilots. The fleet of creek and river boats engaged in this novel work at one time numbered 2,000. But as the production of oil increased and new districts were successfully tapped, it became obvious that some different method of handling the crude oil would have to be adopted. The inland wells could not get rid of their production, and it is not surprising to find that at one time, about 1862, crude oil prices at the well fell to 10 cents per barrel. A system of horse haulage was initiated, and in time thousands of animals were required to haul the oil from the inland wells to shipping points. The wagon train of the oil country in the pre-pipeline days at its maximum consisted of 6,000 two-horse teams and wagons, and a traveler in the oil region in those early 60s could not lose sight of an endless train of wagons, each laden with from 5 to 7 barrels. The roads were almost bottomless, and the teamsters tore down fences and drove where they liked. These men, always of the roving, picturesque type, would earn anything from $10 to $25 per day, spending the most part in revelry on the Saturday night. It was at this time that a bill was introduced into the state's legislature authorizing the construction of a pipeline from Oil Creek to a spot known as Katanning, but the opposition of 4,000 teamsters defeated the bill and the first effort to organize an oil pipeline company. The modest beginning of the present-day system of oil transportation on land by pipeline was due to the enterprise of a Jerseyman named Hutchings, who laid a 2-inch pipe from some wells to the Humboldt refinery. The teamsters, foreseeing the possibilities of this innovation, proceeded to tear up the line and warn the oil producers not to adopt these new methods of oil transportation. But Hutchings was undismayed, for he laid a second line, this being composed of cast iron joints caulked with lead. Although this was impracticable, the teamsters again wrought vengeance on the proposition and completely destroyed it. Hutchings still persisted in his efforts, but died, disappointed and penniless, a genius living a little before his time. At the end of 1865, a Henry Harley commenced the laying of a pipeline to the terminus of the Oil Creek Railroad, but teamsters cut the pipes, burned the collecting tanks, and retarded the work in every possible way. Armed guards eventually came on the scene. The mob was quelled and dispersed, and the line completed. It was of 2-inch diameter and laid to handle 800 barrels of oil daily. This was the first successful and profitable pipeline on record for the handling of oil. From this time, the number of pipelines have multiplied until today there are thousands of them scattered throughout every oil-producing field of America. The first long main transportation line for oil was laid in 1880 from Butler County to Cleveland, a distance of over 100 miles, and immediately after its completion, trunk lines were commenced from the Bradford oil region to the Atlantic seaboard. The popularity of this new method of oil transportation may be judged from the fact that within 3 years from the completion of these first propositions, the National Transit Company possessed over 3,000 miles of oil pipelines and had iron tank storage for 35 million barrels of crude oil. Then a few masterminds came to the front, and loyally supported by Mr. John D. Rockefeller of Standard Oil fame, they undertook the Herculean task of practically girdling the states with a system of oil pipelines that has no parallel anywhere. They eliminated the jaded horses, oil boats, wooden tankage, and slow freights, tedious methods, and questionable practices of handling petroleum, and substituted therefore the stem pump, the iron conduit, the steel tank storage, and systematic and businesslike methods which soon commanded the confidence and respect of all oil producers. They extended their pipelines to practically every producing well and established a transportation system which serves the industry today as no other on earth is served. The advantages of the modern pipeline to the oil producer are obvious. A pipeline connection to a producer's tank ensures prompt service and a cash market for his product at all times. The small line connected with his tank conveys the crude oil therefrom, either by gravity or by means of a pump, into a receiving tank of the gathering or field lines of the pipeline system, from which it is pumped into the main trunk pipelines to the refineries. The system by which the producer can have payment for his oil at any time, for he is credited with its value when it once enters the pipeline, is the perfection of simplicity, accuracy, and efficiency. The pipeline of which the gathering or field lines are composed varies in diameter from 2 to 8 inches, the joints of which are screw-threaded. The main trunk lines are from 6 to 10 inches in diameter, and pumping stations, supplied with powerful plant driven by steam or internal combustion engines of the diesel type, are located at suitable points of the line. According to the nature of the crude oils to be passed through the pipeline, must the erection of pumping houses be governed. For instance, in handling the heavy Californian or Mexican crudes, the pumping stations have to be much nearer each other than when a lighter crude oil is transported. Some of the heavier oils have, in fact, to be heated before they enter the pipes at all. As already mentioned, the total oil transported today by the American pipeline system exceeds 500,000 barrels daily. The lines themselves, all laid, of course, below ground, are so unobtrusive and do their work so quietly and unseen that they attract no attention, and yet they are vastly important to not only the business of the states, but to those myriads of consumers abroad. It is, in fact, impossible to overstate the importance of this up-to-date system of oil transportation in the United States as it exists today. To show the impossibility of conducting the present-day American petroleum industry without the use of pipelines, let me give a few facts. The large oil tank cars, which are not unusual sights on our railways, hold at the maximum about 25 tons of oil. Excluding California altogether from these illustrations, the 500,000 barrels of oil which are transported daily in the States by pipelines would fill over 2,500 tank cars. Taking 25 cars to make up a freight train, it would require fully 100 trains daily to transport the oil that now goes by pipeline, and inasmuch as it is estimated that the oil on the average is transported over land, or rather under land, 1,000 miles, it would require approximately 200,000 railroad tank cars to do the daily work in connection with the transport of oil in the United States east of the Rocky Mountains, for the average movement of tank cars is 30 miles daily, and all empty cars must be returned. No less than 8,000 railroad engines would be required to do this work, which, on the face of it, is a railway impossibility. I am afraid I have devoted more space to the question of pipeline transport in the States than the confines of this little work warrants, but the subject is one of great interest to all who would know the magnitude of the organization which is comprised in the limits of the petroleum industry. The United States, however, is but one of the large oil-producing countries where the pipeline system for the land transport of oil has become the backbone of transport. In Russia, for instance, the fields of production are situated hundreds of miles from the exporting ports, and, following upon the principles which obtain in the United States, the pipeline system had, perforce, to be adopted. In this respect, however, Russia has still a great deal to learn from our Western friends, and the conservative policy which permeated the Russian Empire as a whole has precluded the making of much headway. The Russian oil fields, those of Baku and Grozny, are situated at great distance from the coast, and the necessity of connecting both fields with the export port of Batum on the Black Sea has frequently been put forward as a project offering the one solution of the difficulties attending the retention of a large export oil trade. The Grozny pipeline is still a scheme for future solution, but that affecting Baku has been solved by the laying of a pipeline from Baku to Batum. This line, which is approximately 650 miles long, runs direct between the two oil centers and, assuming it operates 24 hours in the day, has a capacity of transporting over 3,000 tons of oil daily. Inasmuch as the Russian oil refineries are at Baku, the line is used solely for the transportation of the refined products. The line itself is laid alongside the railway line of the Transcaucasian Railway at a depth of 4 feet, but many strange stories are related as to the tapping of it at various points and a lucrative trade being done in the oil so caught. When normal conditions return to Russia and the petroleum industry rights itself, Russian petroleum products will again come on the international markets, and in this respect, the Grozny oil will be able to secure an outlet via Novorossiysk. Romania can also boast of a main trunk pipeline for refined products from the inland refineries direct to the port of Constanța. This important project, which has been carried out practically by the government itself, was just about ready for service when the European War broke out. It has, therefore, had little time in which to display its practical use to the petroleum industry at large. When one recollects that Romania's future, so far as the petroleum industry is concerned, lies in the direction of the building up of its already established export trade in petroleum products, the necessity for such a trunk pipeline to the seaboard has been obvious for many years. Unlike the case of the United States, there are no interesting events to recall which delayed the advent of this new form of land oil transportation. There is only one oil pipeline of any considerable length in the United Kingdom, and this runs across Scotland from Old Kilpatrick on the west to Grangemouth on the east coast, its terminal being in close proximity to the naval base at Rosyth. The line, which is 36 miles long, was laid to circumvent the activity of enemy submarines, but was only completed in November 1918, after the conclusion of the European hostilities. The one other important oil pipeline which calls for mention is that connecting the oil fields of Persia with the coast. In this scheme, the British government is heavily interested, and though there has been much criticism of its action, there is no doubt that, in due time, the Persian fields will play an important part in the supply of petroleum products to England, and in that connection, the Persian pipeline must naturally prominently figure, since without it, there would be numerous difficulties to be contended with in getting the oil to the coast. End of Section 8. Section 9 of the Insomnia Collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from the Draftsman's Handbook of Plan and Map Drawing, including instructions for the preparation of engineering, architectural, and mechanical drawings, with numerous illustrations and colored examples, by George G. Andre, C.E., M.S.E., London, E. and F. N. Spahn, 48 Charing Cross, New York, 446 Broome Street, 1874. Preface. The main purpose of the present work is to be a handy book of reference for draftsmen engaged chiefly in topographical drawings, but to have limited its use to one class of draftsmen, and especially to the skilled members of that class, would have necessitated the discovery of more cogent reasons for its publication than its author has yet been able to adduce. Works of such a character exist already, and though their imperfections are numerous, they fulfill their purpose in a fairly satisfactory manner. But had the field been clear in this direction, it is so restricted in extent that to have entered upon it would have been to undertake a labor that promised little fruit, for such a work could be only of small utility even to those for whom it was specially intended. It was therefore determined to make the present handbook generally useful by giving it a much wider scope, and hence, if the intention has been efficiently carried out, it may claim a place in every drawing office, be it that of the topographer, the hydrographer, the surveyor, the military, civil, or mechanical engineer, or the architect. Whether or not this degree of success has been achieved is not for the author to judge, but should he have failed to reach the high mark at which he has aimed, he hopes, with some degree of confidence, that he has at least succeeded in producing a book which the experienced draftsman will find valuable as a book of reference, and which the pupil may constantly consult with profit. A want has long been felt by draftsmen for some work of this kind, to which they might refer their pupils in the office, and it may not be presumptive to suppose that the present work has supplied that want. To render it convenient for this twofold purpose, it has been divided into two parts. In the first part, the principles and practices of the art have been clearly but briefly explained and illustrated, while in the second part, the application of the principles previously learned has been treated of, and such information given as relates directly to the duties of the practitioner. Of course, in a work of the present character, originality in the matter is neither to be expected nor desired. Enough if the manner show some novelty, and is such as to add value to the matter. Although the preparation of maps and plans has received the chief share of attention, Engineering, architectural, and mechanical drawings have been largely treated of. Projection, orthographic, isometric, and perspective has been altogether omitted as beyond the scope of the work. But coloring and shading have been fully considered and profusely illustrated. The plates appended as examples for reference are numerous and varied in character. They have been specially prepared by B. Alexander, to whom the author offers his warmest thanks for the truly admirable manner in which he has executed the work entrusted to him. 16 Craven Street, Charing Cross, September 7th, 1874. Part 1. The Essential Elements. Section 1. The Drawing Office and its Furnishings. There are few occupations so dependent for their correct performance upon minute matters of detail as that of the draftsman. Things apparently the most trivial are sufficient to render inaccurate or to mar the appearance of the otherwise most carefully and skillfully executed design, and as the value of a drawing depends wholly upon its accuracy and its appearance, it is obvious that such matters of detail, however trivial they may be in themselves, demand careful attention. We have, therefore, deemed it desirable to preface our remarks on plan and map drawing with a brief description of the instruments and materials required, and of the mode of using them which experience has shown to be the best. The Drawing Office. The first essentials of a room for drawing in are that it shall be quite free from damp and be well lighted. The position of the windows is a matter of some importance, and though persons have largely to accommodate themselves to circumstances in this respect, it is desirable to know what are the most suitable conditions in order that they may be complied with as far as circumstances permit. Skylights are unsuitable, because the light entering from above is liable to be intercepted by the body, and especially by the hands of the draftsman, besides which, the light from a skylight is seldom sufficient. For the same reasons, a window placed very high in the room is objectionable. When possible, a western aspect is to be preferred, as the light from this direction is less variable and lasts later in the day than from other directions. Blinds of some kind are necessary to modify the light when the sun shines directly upon the window. Gas lights should be situate about 3 feet above the drawing table, and there should be 2 burners, placed not less than 2 feet apart, as otherwise the hands and the instruments will cast shadows which will prevent fine lines and points from being seen. The drawing table should be placed under the window. It should have a breadth of about 2 feet 6 inches, and its height should be 3 feet 8 inches at the back and 3 feet 6 inches at the front. The front edge should be rounded over. Dusters and means for washing the hands must also be provided, as it is requisite to frequently dust the paper in the instruments and to keep the hands perfectly clean. Instruments. All drawing instruments should be of the best workmanship, for it is impossible to obtain accuracy with imperfect tools, and they must be kept in order by careful handling. For all kinds of drawing, compasses of 3 sizes are required: the ordinary compass, the bows, and the spring bows. The best compasses are those which are sector jointed. The points should be kept sufficiently sharp not to slip on the paper, but not so sharp as to readily penetrate it. It is also important that the points be thin and round, as otherwise, when several arcs have to be struck from the same center, the compass leg is apt to make a large hole which is utterly destructive of accuracy. The pencil leg should be kept exactly equal in length to the steel leg, for true circles cannot be drawn when one leg is shorter than the other. In removing the movable leg, care should be taken to draw it straight out, as nothing spoils the instrument so soon as wrenching the leg from side to side. In using the compasses, the instrument should be held lightly between the thumb and the forefinger only. It should not be pressed upon the paper, but it should rest equally upon both points. If the weight of the hand be thrown upon the instrument, the points will penetrate the paper. Care should also be taken to bend the joints so as to keep both legs perpendicular to the paper. If attention be not given to this matter, the steel leg will make a large hole in the paper, and the ink leg will make a ragged line, because only one of the nibs will touch. Next in importance to the compass, and of more frequent use, is the drawing pen. The draftsman should possess at least 2 of these instruments, one for fine and another for medium lines. When the proper opening of the nibs for fine lines has once been obtained, it is desirable not to change it. The pen can always be cleaned by passing a piece of drawing paper between the nibs. The cleaning of the pen should be carefully attended to. It should never be put away without having every particle of dried ink removed from it, and frequently, while in use, it should be wiped out to remove the dust, which is constantly settling in it, as well as the particles of lead that are taken up from the paper. The ink is supplied by breathing between the nibs and dipping them in the liquid, or by means of a camel's hair brush. When the latter method is adopted, care should be taken to protect the brush from the dust floating in the atmosphere of the room. After considerable wear, the drawing pen will require setting. The operation of setting requires some judgment and considerable practice, and is one of those mechanical niceties which it is difficult to describe. Generally, it will be found advantageous to have the pen set by an instrument maker. As, however, this resource is not always at hand, it is desirable that the draftsman should be able to set his own pen. The following description of the operation, given by W. Binns in his admirable work on projection, is the best we have seen. Quote, "The nibs must be precisely of the same length, rounded in 2 directions, and as sharp as it is possible to make them, without producing to the touch a sensation of cutting, and without scratching the surface of the paper when drawing a line, which is generally the case when one nib is longer than the other. This irregularity may be detected by placing alternately the sides of the pen at an acute angle with the forefinger, and slipping the edge of the nail over the point, when the difference in length will be at once perceived, and it may be reduced by drawing a few lines, as it were, on a turkey stone, with the pen applied to the edge of a set square in the same manner as if drawing lines upon paper, but with this difference that during the longitudinal motion of the pen, the handle must be turned over in a circular manner, so as to give a rounded form to the point of the pen. If the pen be now held with the point directed towards the eye, and gently moved about so as to catch the angle of reflection, a bright speck on one or both nibs will be observed, which must be reduced by rubbing the pen to and fro upon the stone, giving at the same time a slight rotary motion to the handle, which must be held at an angle of about 20 degrees with the face of the stone. The point of the pen being examined from time to time, and the process of reducing the bright specks continued until the point is as fine as can be used without cutting or scratching the paper. If at this stage the two nibs are of the same length, a perfectly solid and fine line can be drawn. The beginner, however, must not be disappointed if 60 minutes are thus expended before he can produce a satisfactory result, whereas 2 minutes in the hands of a practitioner would suffice. End quote. The instrument most frequently in the hands of the draftsman is the lead pencil. These are required of various degrees of hardness, but for lines that are to be ruled, an HH is the best. The most suitable qualities of lead are those which are the most easily rubbed out. These qualities are sometimes gritty, but this defect is more than compensated by the facility with which a line may be removed from the paper. There is some art in cutting a pencil properly. If the point is intended for sketching, it should be cut equally from all sides, so as to produce a perfectly acute cone. But for line drawing, a flat or chisel point should always be used. This point is much stronger and will last much longer than the cone point. To produce the chisel point, first cut the pencil from 2 sides only with a long slope, and afterwards cut the other sides away only just sufficiently to round the first edge a little. This side wood is needed both to afford a support to the lead and to show in what direction the point stands. To avoid breaking the lead, the knife should be held at an acute angle with it. A point cut in this manner may be kept in order for some time by rubbing it upon a fine file or upon a piece of glass paper or fine sandstone. Of the other instruments used in drawing, nothing need be said in this work, as their use presents no difficulties. It may, however, be well to remark that no straight edge employed for ruling lines should be less than 1/14 of an inch thick, for if the edge be very thin, it will be impossible to prevent the ink from escaping from the pen onto it. Materials. The drawing papers known as Whatmans are the best prepared of any obtainable, and they are almost universally employed. Of these there are 2 kinds, the smooth and the rough. The former is technically called knot paper and is the more suitable for mechanical and architectural drawings. The rough is more effective for perspectives and Gothic elevations. A third kind is shown as the hot pressed, but as it does not take color so well as the knot and the rough, it is not often used. The various sizes are indicated by their names, which are the following: Antiquarian, 53 by 31 inches. Atlas, 34 by 26 inches. Colombier, 34.5 by 23.5 inches. Demi, 20 by 15 inches. Double Elephant, 40 by 26 3/4 inches. Elephant, 28 by 23 inches. Emperor, 68 by 48 inches. Imperial, 30 by 22 inches. Medium, 22 3/4 by 17 inches. Royal, 24 by 19 1/4 inches. Super Royal, 27.5 by 19 1/4 inches. The sizes considered best and almost universally used for engineering and architectural drawings are the elephant, the double elephant, and the imperial. If smaller sizes are required, the half or quarter sheet is used. Antiquarian has generally a good surface to draw upon, and it is preferred by some architects. The Atlas is also a very good paper. Besides the foregoing, there is the machine-made or cartridge paper, which is very commonly employed for detailed drawings. It has not so good a surface as the other kinds, nor is it so white. Its chief advantage is found in its dimensions, it being made uniformly 53 inches wide and continuous. Hence, the exact length required may be obtained. For large plans and competition drawings, either cartridge or emperor paper is used. Paper that is to receive an elaborate drawing must be stretched and glued to the board. This operation is one requiring a little skill and some practice to perform successfully. The following is the best manner of proceeding. The sheet to be strained is laid face upward upon the board, and a wet sponge is passed rapidly along the margins, and then across the face, including the margins, until the whole surface is sufficiently and uniformly wetted. The object of wetting the margins first is to prevent cockling by allowing them a longer time to expand in than the middle of the paper. The sheet must now be left for about 10 minutes, or until the wet gloss has entirely disappeared. The process of gluing to the board is as follows. A straight edge is laid along one end of the sheet, and about 3/8 of an inch of the margin is turned up against it and glued by means of a brush. The margin is then turned down and rubbed quickly with a knife handle, or, still better, a paper knife. The opposite end of the sheet is next pulled outwards and glued in the same way, and the same method is afterwards applied to the top and bottom margins. Some draftsmen prefer to glue down the adjoining edges, but generally it will be found that laying down successfully opposite edges will give more satisfactory results. The contraction of the paper in drying should leave the face quite flat and solid. During the process of drying, it is important to keep the board in a perfectly horizontal position, as otherwise the water will gravitate towards the lower side and soften the glue, and as the sheet will dry unequally, the lower edge will break away. The thinner the glue used, the better, and for this reason, the best quality should be obtained, and care should be taken to keep the water supplied that is lost by evaporation. When it becomes necessary to replenish the glue pot, the cake should be soaked in cold water for at least 8 hours. The removal of a drawing from the board presents no difficulty. A pencil line is drawn along the margin at a sufficient distance from the edge to be clear of the glue, and a penknife is guided along this line by a straight edge not used for drawing. As duplicates of drawings, especially if they be working drawings, are usually tracings. Tracing paper is an important material in every drawing office. It is too well known to need a description. It is sold in various sizes and of various prices, but the most usual sizes are 30 by 20 inches and 40 by 30 inches, the price of the former being 3d and that of the latter 6d a sheet. It may also be purchased in continuous lengths of 24 yards, 42 inches wide, for about 8 shillings, or if extra stout, 16 shillings. A much less expensive mode of obtaining tracing paper is to make it oneself. Common silk or tissue paper may be purchased in quantities at less than a halfpenny a sheet of the ordinary size. This may be prepared by placing a single sheet at a time flat upon a board or other smooth horizontal surface, and applying a mixture of boiled linseed oil and turpentine. This mixture should be composed of 1 part of oil to 5 of turpentine, and it should be applied with a small sponge. 1 coating is sufficient, and it should not be put on too thickly. Each sheet, as prepared, should be hung over a string stretched across the room to dry, and when all the clear, oily marks have entirely disappeared, it will be ready for use. 5 gills of turpentine and 1 of oil is enough for 2 quires of double-crown tissue paper. That tracing paper is best which is toughest, most transparent, and most free from greasiness. The continuous papers are more economical than those in sheets, because just the quantity required can always be taken from the roll. For durability, tracing cloth is to be recommended. It is sold in continuous lengths of 24 yards, and it may be had from 18 inches to 41 inches in width. That known as Sager's vellum cloth is of excellent quality, both for transparency and strength. Some kinds of drawings, such as specification for letters patent, plans upon deeds, etc., have frequently to be made upon parchment. Special kinds of parchment can be obtained for these purposes. There is a kind made which is quite transparent, and which can be purchased cut to the Patent Office regulation size. As parchment has always a more or less greasy surface, before commencing to ink or to color, it should be pounced over with pouncet of finely powdered French chalk. Besides this precaution, it will be necessary to add a little ox gall to the ink or color. Blacklead and carbonic paper are used to transfer a drawing. The former is prepared by rubbing thin paper over with a soft block of Cumberland lead. The latter, by painting one side of the paper with lampblack ground to perfect fineness in slow-drying oil. Carbonic paper is used for coarser work than blacklead paper. Both may be purchased, properly prepared, at a trifling cost. The drawing to be copied is laid over the sheet of paper which is to receive the copy, with a sheet of the blacklead or carbonic paper interposed, and a tracer is passed with a light pressure over the lines. This method is mostly used to reproduce a drawing from a tracing, to obtain a finished copy from a rough draft that has become soiled and marked in designing, or to avoid errors or small alterations in the first drawing. A very convenient kind of paper for small working drawings or for sketching to scale is that known as sectional paper. This is paper ruled into small squares to a given scale with pale ink. The spaces in ordinary use are 1/10, 1/8, 1/6, 1/5, and 1/4 inch. Thicker lines are drawn either to mark off the inches or to count the spaces in tens. With this paper, the scale may be dispensed with, as the eye is capable of subdividing the spaces with sufficient accuracy for practical purposes. Sectional paper is much used for sections of railway cuttings and embankments, as it affords a ready means of calculating the contents. It is also made up into sketching books and architects' pocketbooks, for which purposes it is peculiarly convenient. Indian ink is used for all kinds of geometrical drawings. Being free from acid, it does not corrode the steel points of the instruments, and it preserves its color unchanged. It is difficult to get the genuine ink, but even that, as it is imported from China, varies considerably in quality. For line drawing, that is the best quality, which will wash up least when other colors are passed over it. This quality is ascertained in the trade, though not with absolute certainty, by breaking off a small portion. If it be of the right quality, it will show a very bright and almost prismatic colored fracture. The ink is prepared for use by rubbing it with water on a slab or in a saucer. The saucer should be quite smooth inside, so as not to abrade the ink. When mixed to the requisite thickness, which may be ascertained by drawing a line with a common pen, it should be covered to protect it from the particles of dust floating about the room. Ink should be rubbed up perfectly black, for pale ink makes the boldest drawing look weak. But after it has become black, any further mixing will only injure it by rendering it viscid. It is best to use it immediately after it is mixed, for if redissolved, it becomes cloudy and irregular in tone. The addition of a little ox gall will make it flow more freely from the pen. For erasing Cumberland lead pencil marks, native or bottle India rubber is sufficient. But for other kinds of pencils, fine vulcanized India rubber is better. This, besides being a more powerful eraser, possesses the important quality of keeping clean, as it frets away with the friction of rubbing, and thus presents a continually renewed surface. Vulcanized rubber is also very useful for cleaning off drawings. Precautions and remarks. It is essential to the good appearance of a drawing that the paper be preserved perfectly clean. The hands especially should be kept as much as possible from resting on it, as the perspiration makes it greasy, and when once it has acquired this defect, clear, sharp lines become impossible. A sheet of clean paper should be constantly interposed between the draftsman's hands and the drawing upon which he is working. Brown or printed paper is unfit for this purpose, as the former is either greasy or tarry, and the latter is apt to soil from the printed matter. White paper can be had of large size, or, if necessary, several sheets may be pasted together. To prevent risk of smearing the lines when inking in, it is well to begin at the top of the drawing and to work downwards, also from the right to the left for vertical lines. The ink slab or saucer should be kept on one side and never in front of the drawing. Should a drawing get a grease spot, it may be removed by the application of a hot smoothing iron to a piece of clean blotting paper laid over the spot, but not sufficiently to be colored over. Great care should be taken to correctly place the center lines of a drawing. These lines should be drawn very fine and distinct. In working drawings, the center lines are of great importance, as the dimensions are always measured from them. In such cases, it is customary to draw them in red or blue color. In all cases where a plane figure is symmetrical with respect to a given line, whether the line exists in the figure or may be considered as existing in it, that line should be drawn first, and such a line is known as the center line. The centers of all arcs should be marked for the ink compasses at the time the arc is struck by the pencil, by placing a small hand-drawn circle around it. It is also necessary to mark distinctly by short intersecting straight lines the exact points at which the arc begins and ends. When a number of concentric circles have to be struck, the smaller ones should be struck first, as it is more difficult when the hole in the paper becomes enlarged to draw a small circle than a large one. Whenever it is practicable, lines should be drawn from a given point rather than to it, and if there are several points in one of which two or more lines meet, the line should be drawn from that one to the others. Thus, for example, radii should be drawn from the center to the points in the circumference of a circle. When a point has to be determined by the intersection of circular arcs or straight lines, these should not meet at an angle less than 30 degrees. In dividing a line into a number of parts, instead of setting off the part repeatedly along the line, it is better to set off a convenient multiple of the given part and subdivide it. That is, to work from the whole to the parts, rather than from the parts to the whole. This is an important principle in surveying as well as in plan drawing, and in the construction of scales it ought always to be observed. Ink lines should never be erased with a knife, nor should an ink eraser be used, especially if the drawing is to be colored. A needlepoint will take out a short line in a way that leaves little trace of the error. A very good means of taking out a line is furnished by a piece of Oakey's No. 1 glass paper, folded several times until it presents a round edge. The application of this leaves the surface of the paper in a much better condition for drawing upon than it is left in by the knife. When the drawing is to be colored, it is best to wash out a wrong line with a small hard brush, and to slightly sponge over the place through a hole of the requisite size cut in a scrap of drawing paper, to save the other parts of the drawing. When a line has been drawn a little beyond the point at which it should terminate, it will generally be found better to avoid erasure by laying a little Chinese white over the line with a fine sable brush. Sometimes, when erasures are unavoidable upon a drawing that is to be colored, it will be found expedient to take the surface off the whole of the paper with glass paper. The color will then flow equally. In copying from a tracing, it is well to put a sheet of drawing paper underneath the tracing, for it not only shows up the lines more distinctly, but it prevents the dividers from tearing the drawing while taking off measurements. Before commencing a drawing, a cutting off line should be drawn all round the sheet, clear of the glued portion. The portions outside of this line are useful to try the drawing pen upon before drawing a line, or for trying a tint when coloring. Care should be taken not to leave too narrow a margin, for nothing detracts more from the appearance of a good drawing. For a drawing occupying a space of 1 foot or 15 inches square overall, there should be a margin of at least 5 inches all round, with the border line from 1½ to 2 inches from the cut-off line. Other sizes should be in proportion. This rule is given by Maxton in his engineering drawing, who also has the following remarks on cutting off and preserving drawings. Quote, "The opposite side should never be cut first, for if so cut, upon nearly completing the cutting of the third side, the paper undergoes contraction, and the fourth side pulling against it is apt to snap off the remaining inch or so, and generally in towards the sheet, seldom in the margin on the outside of the cutting off line. The sheet should be cut off all around, taking care, by applying the knife blade under the edge of the sheet, that it is free from the board before proceeding to cut off the side or end adjoining. When the sheet has been removed, the strips of drawing paper left on the board should be simply sponged over 2 or 3 times, and they will peel off easily. For preserving a rolled drawing, a common substitute for string, and one less likely to crease the drawing, is made as follows. Take a strip of drawing paper from 1½ to 2 inches wide and 1 inch longer than the circumference of the rolled drawing. About ½ an inch from each end, make incisions, at one end in the middle and 1/3 of the breadth across, and at the other end at the sides, each 1/3 of the breadth across. Fold in these sides so that they may pass through the incision in the opposite end of the strip. On being opened again after they have passed through, the whole will form a hoop which, when slipped over the drawing, will keep it secure. End quote. As cartridge paper is not always suitable, it sometimes becomes necessary to join the smaller sizes end to end. To do this neatly, the edges should be cut straight and a straight edge laid upon the paper, allowing 3/8 inch to project beneath it. This portion of the paper should then be rubbed down with sand or glass paper until the outer edge is quite thin. The edges of both sheets to be joined must be treated in this way and covered with a thin coating of gum. Having placed these edges in contact, a strip of paper 1½ or 2 inches wide should be laid upon the joint and well rubbed with the handle of a paper knife. If the paper thus joined has afterwards to be stretched on a board, it should be done while the joint is damp. In sponging the paper, care must be taken not to go over the joint. In joining sheets of tracing paper, the joint should never be made more than 1/4 inch broad. The gum used for this purpose should be very thin, and a strip of drawing paper should be placed upon each side of the joint until it is quite dry. It is a good plan to roll the joined sheet upon a roller with the joint in a line with the roller and the strips enfolded over the joint. When left to dry in this position, the joint will be perfectly smooth. Drawings have frequently to be mounted on stretchers, and the operation of mounting is one requiring some care and practice. Generally, it will be found more convenient to purchase the stretcher ready-made complete. But when this is not done, care must be taken to have the frame made of sufficient strength to resist the tension of the paper when dry. The sides and the ends of a stretcher, 8 or 9 feet long, should be 4 inches broad and not less than 7/8 inch thick, and for any length above 18 inches, there should be 1 or more bars across. A frame 6 feet long should have 2 crossbars dividing the length into 3 equal parts, and they should be of such a thickness as not to come up flush with the sides and ends by about 1/8 inch. The inner edges on the face of the latter should be rounded down to the level of the crossbars, and the same degree of rounding should be given to the edges of the crossbars themselves. This is necessary to prevent the edges from showing a soiled mark on the paper. When the frame has been thus prepared, the linen or calico should be spread out on some flat surface, and the frame laid upon it face downwards. The ends of the linen should then be pulled over and nailed to the back. Next, the middle of the sides should be pulled over and fixed in the same way. The intermediate spaces are afterwards tacked down by placing a tack alternately on opposite sides, care being taken to pull the linen tight and smooth before inserting the tack. It is a good plan to fold the edge, as the double thickness will hold the tacking better than if single. To mount the paper on the stretcher, it should be laid face downwards upon a clean, flat surface, which will be all the better if covered with a clean cloth and sponged with clean water. When the water has soaked in, apply with a flat brush some cold flour paste, and, if necessary, remove all knots or particles of gritty matter, as these would prevent the paper from lying close to the linen. The addition of a little alum to the paste improves its adhesive property, and also tends to make the drawing less stiff when dry. When a good coating of paste has been well distributed over the paper, place the stretcher upon the paper and rub the back of the linen well. Then turn the stretcher over and rub down the edges of the paper. Air bubbles between the linen and the paper may be got rid of by puncturing the spot with a fine needle and rubbing it down. Paper thus mounted may be drawn upon nearly as well as when stretched on a board. To give an edge for the T-square, a strip of wood with parallel edges may be temporarily nailed on. Some drawings, such as large plans of estates, have frequently to be varnished. This operation requires some skill and can be satisfactorily accomplished only by a practiced hand. The process generally adopted is to stretch the drawing upon a frame and to give it 3 or 4 coats of isinglass size with a flat, broad brush, taking care to well cover it each time and to allow it time to dry between each coat. The best varnish is Canada balsam diluted in oil of turpentine. This requires to be put on evenly in a flowing coat with a fine, flat brush, and to be left in a warm room, free from dust, until it is thoroughly dry. The drawing must be in a perfectly horizontal position, while the size and the varnish are being applied. In drawings to be varnished, thick lines, such as shade lines, and chalky colors should never be put on before sizing, as they are apt to blot during the process. Should a fur drawing board get accidentally dented, an application of water to the part will, within certain limits, bring it up to its proper level. Section 3. Lines, dots, and their combinations. All kinds of drawings are made up of lines and dots. These are the constituent parts, the materials which the draftsman has to employ. It is therefore essential that he should make himself acquainted with their various forms and uses, and familiar with those means of producing them which experience has shown to be the best, before commencing the study of the principles by which the representation of an object is delineated. And moreover, it is desirable that he should acquire a familiarity with the operations required in the delineation of isolated objects, previously to making any attempt to place them in combination for the purpose of producing a complete drawing. The student will, therefore, do well to study carefully and to practice diligently the forms and examples given in this section. Straight and curved lines. All straight lines, however short, should be ruled, whether they be drawn with the pencil or the pen. Pencil lines, which are intended to serve merely as guides to the pen, should be drawn lightly, as otherwise it will be difficult to rub them out without injuring the ink. They should also be drawn a little beyond the point at which the line is required to terminate, because the intersection of the lines at that point makes it more distinctly visible, and there is, consequently, less danger of passing beyond that point or of stopping short of it when inking in. It is very important not to stop short of the required length when ruling a straight line with a pen, for it is extremely difficult to lengthen the line subsequently without leaving the join visible. An accurate line cannot be drawn unless the point of the pencil or the pen be kept close up to the rule, and to do this, the top should be inclined a little outward. Before inking in a line that has been drawn in pencil, the India rubber should be passed lightly over it to remove the particles of lead adhering to the paper, for if these particles are allowed to remain, they get between the nibs of the pen and prevent the ink from flowing freely. The chief difficulties in ruling a straight line with the pen are to keep it of a regular thickness throughout, and, when numerous parallel lines have to be drawn, to keep them at equal distances apart. To draw an even line, a first requisite is that the pen be in good condition. Frequently, it will be found when drawing fine lines that the pen ceases to mark before the end of the line is reached, and as we have already said, it is very difficult to join a line without leaving visible traces of the operation. To remedy this defect, the pen must be reset as described in Section 1. If a very hard pencil has been used, or if the pencil has been pressed heavily upon the paper, the pencil line will lie in a groove in the paper, and as the nib of the pen will not touch the bottom of this groove, the line drawn will be ragged. Another cause of unevenness is unduly pressing the pen against the rule. This pressure closes the nibs, and besides producing an irregularity in the thickness of the line, is very apt to cause a blot by forcing out the ink, which adheres to the rule when brought into contact with it. To prevent this, care should be taken to press the pen very lightly against the edge of the rule. A pen is manufactured by Stanley of Holborn, London, which has the back nib much stiffer than the other, so that all danger of defect from this cause is removed by the construction of the instrument. To ensure a good line, the pen should rest lightly upon the paper, and the handle of the pen should make the same angle with the paper from the beginning to the end of the line. A considerable amount of practice is required to accomplish this, and to acquire the habit, the same attention should be given to the pencil as to the pen. The ability to draw a number of parallel lines at equal distances apart without measuring requires considerable training of the eye, and this training can be obtained from practice alone. This ability must be acquired before anything further is attempted, and the student who spends a good deal of time in its acquisition may have the satisfaction of knowing that while he is going through this somewhat monotonous practice, besides exercising himself in drawing accurate lines, he is acquiring a correctness of eye and a power of hand that will be of incalculable service to him later. The straight line, besides being used for the outlines of regular objects, is employed conventionally for various purposes. When it is required to show an object in section, the part in section is covered with straight and parallel lines drawn at an angle of 45 degrees and at equal distances apart, as in Figure 38. To represent standing water, as ponds and lakes, horizontal straight lines are drawn parallel to each other and at equal distances apart over the surface, as shown in Figure 39. Curved lines, when arcs of circles, are drawn by the compasses. Other curves are drawn by hand through points previously found. To draw the curve correctly through these points, unless they be very numerous, a knowledge of the nature of the curve is necessary, which the draftsman should in all cases endeavor to obtain. When the curved line is long, it is usually inked in with the drawing pen, with the aid of an instrument called the French curve, or cardboard molds cut for the purpose. But for short lines, an ordinary fine-pointed steel pen point, or better, a good quill, is used. In general, all lines drawn by hand should be drawn towards the body, as a better command of the pen can be obtained in that direction than in any other. In inking in curves by this means, the draftsman should proceed continuously along the pencil-drawn line by partly repeated touches with the pen point, so held that the divided points of the pen may follow partly in the same track. Each touch should be made about 1/30th of an inch in length, and it should begin and end fine. Each succeeding touch must begin half its length back, so that the line is advanced by 1/60th of an inch. In map drawing, all irregular lines are drawn in this way. Tracing maps will afford the student excellent practice in this mode of using the pen. Lines of uneven thickness. Though generally a line is required to be of even thickness throughout, cases sometimes occur in which a variation in the thickness may be made to express some feature or quality of the landscape. The usual application of this kind of line is to mark the outline of rivers, lakes, and ponds, as shown in Figure 40. The drawing of such a line presents no difficulty. The increased thickness is produced by going over those parts of the line again with the pen. Care must, however, be taken not to make a sudden increase in the breadth of the line, but to begin and end imperceptibly. The broken line. The broken line, shown in Figure 41, is of frequent occurrence in all kinds of drawings. In architectural and engineering drawings, it is usually employed in roofs, as in Figure 42, and for water in sections, as in Figure 43. It is also used in combination with other lines for various purposes. In drawing a succession of broken lines, care must be taken not to allow the break in one line to be immediately over that in another. The effect may be varied considerably by increasing or diminishing the extent of the break. As in section lining, the lines should be at regular intervals apart and be all of the same degree of fineness. Broken lines are sometimes used upon the face of stone buildings, instead of marking in the joints and etching or coloring. In such a case, the breaks are long and the lines widely spaced. The dotted line. Of still more frequent occurrence is the dotted line. There are two kinds of dotted lines, distinguished by the shape of the dot, and known as the long and the round dotted line. These are shown in Figure 44, as well as a combination of the two. The round dotted line is of very general application. In architectural and mechanical drawings, it is used to distinguish hidden parts, and to mark the path of a moving piece in a machine. In plans, it is used to show the position of proposed works, to denote the walks through pleasure grounds and gardens, to indicate lines chained over in surveying, and frequently for other purposes, at the pleasure of the draftsman. The long dotted line is employed to mark the boundaries of a township, the navigable channel of a river or creek, and in large-scale maps to show farm and bridle roads, footpaths, and the divisions of land among different tenants. The combination of the long and round dotted lines is used for the boundaries of a parish. Another combination of 2 round and 1 long dots, or sometimes of 3 round and 1 long, is used to denote proposed railways, canals, roads, and other similar works. To draw a good dotted line requires some care. The difficulty lies in keeping the dots at equal distances apart, and in making them equal in size. And unless both these conditions are fulfilled, the line will not present a pleasing appearance. To obviate this difficulty, an instrument is sold by mathematical instrument makers called the dotting or wheel pen. But it requires very great care in using, as otherwise it frequently happens that the ink escapes from it and spoils the drawing. For this reason, its use has been generally abandoned by draftsmen. But if the instrument were better constructed and carefully handled, it might be made to do good service. Combinations of straight, broken, and dotted lines. Combinations of the foregoing lines are used for various purposes. Some draftsmen employ alternate, full, and dotted lines to denote wood in section, as in figures 45 and 46. When wood is used in combination with iron or other metal, this is a very good way of distinguishing it. Wood graining, though not made up of straight, broken, or dotted lines, yet partakes somewhat of the nature of all 3 kinds, and may therefore be introduced here. Oak graining is shown in figure 47, and fir graining in figure 48. The former is executed with a drawing pen, and requires some care and practice. The latter is most readily done with a common pen or a crow quill, and wood is grained as shown in figure 49. The spring bows are very suitable for drawing in the circles, as a certain degree of turn to the nut will open the ink leg to the required distance after drawing each circle. A few broken wavy lines, called shakes, radiating from the center, produce a good effect. When several pieces of end wood come together, the centers in each should not be in the same relative position. End of section 9. Section 10 of the Insomnia collection, Volume 6. This LibriVox recording is in the public domain. Read by Verla Viera. Excerpts from Aviation Engines, Design, Construction, Operation, and Repair. A complete practical treatise outlining clearly the elements of internal combustion engineering, with special reference to the design, construction, operation, and repair of airplane power plants. Also, the auxiliary engine systems, such as lubrication, carburation, ignition, and cooling. It includes complete instructions for engine repairing and systematic location of troubles, tool equipment, and use of tools. Also outlines the latest mechanical processes. By First Lieutenant Victor W. Paget, ASSC, USR, Assistant Engineering Officer, Signal Corps Aviation School, Mineola, Long Island. Author of The Modern Gasoline Automobile, etc. Contains valuable instructions for all aviation students, mechanicians, squadron engineering officers, and all interested in the construction and upkeep of airplane power plants. New York, the Norman W. Henley Publishing Company, 2 West 45th Street, 1917. Preface. In presenting this treatise on aviation engines, the writer realizes that the rapidly developing art makes it difficult to outline all latest forms or describe all current engineering practice. This exposition has been prepared primarily for instruction purposes and is adapted for men in the aviation section, signal corps, and students who wish to become aviators or aviation mechanicians. Every effort has been made to have the engineering information accurate, but owing to the diversity of authorities consulted and use of data translated from foreign language periodicals, it is expected that some slight errors will be present. The writer wishes to acknowledge his indebtedness to such firms as the Curtiss Airplane and Motor Company, Hall Scott Company, Thomas Morse Aircraft Corporation, and General Vehicle Company for photographs and helpful descriptive matter. Special attention has been paid to instructions on tool equipment, use of tools, troubleshooting, and engine repairs, as it is on these points that the average aviation student is weakest. Only such theoretical consideration of thermodynamics as was deemed absolutely necessary to secure a proper understanding of engine action after consulting several instructors is included, the writer's efforts having been confined to the preparation of a practical series of instructions that would be of the greatest value to those who need a diversified knowledge of internal combustion engine operation and repair, and who must acquire it quickly. The engines described and illustrated are all practical forms that have been fitted to airplanes capable of making flights and may be considered fairly representative of the present state of the art. Victor W. Paget, First Lieutenant, ASSC, USR, Mineola, Long Island, October 1917. Chapter 1. Brief consideration of aircraft types. The conquest of the air is one of the most stupendous achievements of the ages. Human flight opens the sky to man as a new road, and because it is a road free of all obstructions and leads everywhere, affording the shortest distance to any place, it offers to man the prospect of unlimited freedom. The aircraft promises to span continents like railroads, to bridge seas like ships, to go over mountains and forests like birds, and to quicken and simplify the problems of transportation. While the actual conquest of the air is an accomplishment just being realized in our days, the idea and yearning to conquer the air are old, possibly as old as intellect itself. The myths of different races tell of winged gods and flying men, and show that for ages to fly was the highest conception of the sublime. No other agent is more responsible for sustained flight than the internal combustion motor, and it was only when this form of prime mover had been fully developed that it was possible for man to leave the ground and alight at will, not depending upon the caprices of the winds or lifting power of gases as with the balloon. It is safe to say that the solution of the problem of flight would have been attained many years ago if the proper source of power had been available, as all the essential elements of the modern airplane and dirigible balloon, other than the power plant, were known to early philosophers and scientists. Aeronautics is divided into two fundamentally different branches, aviatics and aerostatics. The first comprises all types of airplanes and heavier-than-air flying machines, such as the helicopters, kites, etc. The second includes dirigible balloons, passive balloons, and all craft which rise in the air by utilizing the lifting force of gases. Airplanes are the only practical form of heavier-than-air machines, as the helicopters, machines intended to be lifted directly into the air by propellers without the sustaining effect of planes, and ornithopters, or flapping wing types, have not been thoroughly developed, and in fact, there are so many serious mechanical problems to be solved before either of these types of aircraft will function properly, that experts express grave doubts regarding the practicability of either. Airplanes are divided into two main types: monoplanes, or single-surface forms, and biplanes, or machines having two sets of lifting surfaces, one suspended over the other. A third type, the triplane, is not very widely used. Dirigible balloons are divided into three classes: the rigid, the semi-rigid, and the non-rigid. The rigid has a frame or skeleton of either wood or metal inside of the bag to stiffen it. The semi-rigid is reinforced by a wire net and metal attachments, while the non-rigid is just a bag filled with gas. The airplane, more than the dirigible and balloon, stands as the emblem of the conquest of the air. Two reasons for this are that power flight is a real conquest of the air, a real victory over the battling elements. Secondly, because the airplane, or any flying machine that may follow, brings air travel within the reach of everybody. In practical development, the dirigible may be the steamship of the air, which will render invaluable services of a certain kind, and the airplane will be the automobile of the air, to be used by the multitude, perhaps for as many purposes as the automobile is now being used. Chapter 2: Operating Principles of 2- and 4-stroke cycle engines. Before discussing the construction of the various forms of internal combustion engines, it may be well to describe the operating cycle of the types most generally used. The 2-cycle engine is the simplest because there are no valves in connection with the cylinder, as the gas is introduced into that member and expelled from it through ports cored into the cylinder walls. These are covered by the piston at a certain portion of its travel, and uncovered at other parts of its stroke. In the 4-cycle engine, the explosive gas is admitted to the cylinder through a port at the head end closed by a valve, while the exhaust gas is expelled through another port controlled in a similar manner. These valves are operated by mechanism distinct from the piston. The action of the 4-cycle type may be easily understood if one refers to illustrations at figures 5 and 6. It is called the 4-stroke engine because the piston must make 4 strokes in the cylinder for each explosion or power impulse obtained. The principle of the gas engine of the internal combustion type is similar to that of a gun, i.e., power is obtained by the rapid combustion of some explosive or other quick-burning substance. The bullet is driven out of the gun barrel by the pressure of the gas evolved when the charge of powder is ignited. The piston or movable element of the gas engine is driven from the closed or head end to the crank end of the cylinder by a similar expansion of gases resulting from combustion. The first operation in firing a gun or securing an explosion in the cylinder of the gas engine is to fill the combustion space with combustible material, This is done by a downstroke of the piston, during which time the inlet valve opens to admit the gaseous charge to the cylinder interior. This operation is shown at Figure 5a. The second operation is to compress this gas, which is done by an upward stroke of the piston, as shown at Figure 5b. When the top of the compression stroke is reached, the gas is ignited and the piston is driven down toward the open end of the cylinder, as indicated at Figure 6c. The fourth operation, or exhaust stroke, is performed by the return upward movement of the piston, as shown at Figure 6d, during which time the exhaust valve is opened to permit the burnt gases to leave the cylinder. As soon as the piston reaches the top of its exhaust stroke, the energy stored in the flywheel rim during the power stroke causes that member to continue revolving, and as the piston again travels on its downstroke, the inlet valve opens and admits a charge of fresh gas, and the cycle of operations is repeated. The illustrations at Figure 7 show how the various cycle functions take place in an L-head type water-cooled cylinder engine. The sections at A and C are taken through the inlet valve. Those at B and D are taken through the exhaust valve. The two-cycle engine works on a different principle, as while only the combustion chamber end of the piston is employed to do useful work in the four-cycle engine, both upper and lower portions are called upon to perform the functions necessary to two-cycle engine operation. Instead of the gas being admitted into the cylinder, as is the case with the four-stroke engine, it is first drawn into the engine base, where it receives a preliminary compression prior to its transfer to the working end of the cylinder. The views at Figure 8 should indicate clearly the operation of the two-port, two-cycle engine. At A, the piston is seen reaching the top of its stroke, and the gas above the piston is being compressed, ready for ignition, while the suction in the engine base causes the automatic valve to open and admits mixture from the carburetor to the crankcase. When the piston reaches the top of its stroke, the compressed gas is ignited, and the piston is driven down on the power stroke, compressing the gas in the engine base. When the top of the piston uncovers the exhaust port, the flaming gas escapes because of its pressure. A downward movement of the piston uncovers the inlet port opposite the exhaust and permits the fresh gas to bypass through the transfer passage from the engine base to the cylinder. The conditions with the intake and exhaust port fully opened are clearly shown at Figure 8c. The deflector plate on the top of the piston directs the entering fresh gas to the top of the cylinder and prevents the main portion of the gas stream from flowing out through the open exhaust port. On the next upstroke of the piston, the gas in the cylinder is compressed and the inlet valve opened, as shown at A, to permit a fresh charge to enter the engine base. The operating principle of the three-port, two-cycle engine is practically the same as that previously described, with the exception that the gas is admitted to the crankcase through a third port in the cylinder wall, which is uncovered by the piston when that member reaches the end of its upstroke. The action of the three-port form can be readily ascertained by studying the diagrams given at Figure 9. Combination 2 and 3-port engines have been evolved and other modifications made to improve the action. Theory of the gas and gasoline engine. The laws controlling the elements that create a power by their expansion by heat due to combustion, when properly understood, become a matter of computation in regard to their value as an agent for generating power in the various kinds of explosive engines. The method of heating the elements of power in explosive engines greatly widens the limits of temperature as available in other types of heat engines. It disposes of many of the practical troubles of hot air, and even of steam engines, in the simplicity and directness of application of the elements of power. In the explosive engine, the difficulty of conveying heat for producing expansive effect by convection is displaced by the generation of the required heat within the expansive element and at the instant of its useful work. The low conductivity of heat to and from air has been the great obstacle in the practical development of the hot air engine, while, on the contrary, it has become the source of economy and practicability in the development of the internal combustion engine. The action of air, gas, and the vapors of gasoline and petroleum oil, whether singly or mixed, is affected by changes of temperature, practically in nearly the same ratio. But when the elements that produce combustion are interchanged in confined spaces, there is a marked difference of effect. The oxygen of the air, the hydrogen and carbon of a gas, or vapor of gasoline or petroleum oil, are the elements that by combustion produce heat to expand the nitrogen of the air, and the watery vapor produced by the union of the oxygen in the air and the hydrogen in the gas, as well as also the monoxide and carbonic acid gas that may be formed by the union of the carbon of gas or vapor with part of the oxygen of the air. The various mixtures as between air and gas, or air and vapor, with the proportion of the products of combustion left in the cylinder from a previous combustion, form the elements to be considered in estimating the amount of pressure that may be obtained by their combustion and expansive force. The isothermal law. The natural laws, long since promulgated by Boyle, Gay-Lussac, and others, on the subject of the expansion and compression of gases by force and by heat, and their variable pressures and temperatures when confined, are conceded to be practically true and applicable to all gases, whether single, mixed, or combined. The law formulated by Boyle only relates to the compression and expansion of gases without a change of temperature, and is stated in these words: if the temperature of a gas be kept constant, its pressure or elastic force will vary inversely as the volume it occupies. It is expressed in the formula P times V equals C, or pressure times volume equals constant. Hence, C divided by P equals V, and C divided by V equals P. Thus, the curve formed by increments of pressure during the expansion or compression of a given volume of gas without change of temperature is designated as the isothermal curve, in which the volume multiplied by the pressure is a constant value in expansion, and inversely, the pressure divided by the volume is a constant value in compressing a gas. But as compression and expansion of gases require force for their accomplishment mechanically, or by the application or abstraction of heat chemically, or by convection, a second condition becomes involved, which was formulated into a law of thermodynamics by Gay-Lussac under the following conditions. A given volume of gas under a free piston expands by heat and contracts by the loss of heat, its volume causing a proportional movement of a free piston equal to 1/273rd part of the cylinder volume for each degree centigrade difference in temperature, or 1/492nd part of its volume for each degree Fahrenheit. With a fixed piston, constant volume, the pressure is increased or decreased by an increase or decrease of heat in the same proportion of 1/273rd part of its pressure for each degree centigrade, or 1/492nd part of its pressure for each degree Fahrenheit change in temperature. This is the natural sequence of the law of mechanical equivalent, which is a necessary deduction from the principle that nothing in nature can be lost or wasted, for all the heat that is imparted to or abstracted from a gaseous body must be accounted for, either as heat or its equivalent transformed into some other form of energy. In the case of a piston moving in a cylinder by the expansive force of heat in a gaseous body, all the heat expended in expansion of the gas is turned into work. The balance must be accounted for in absorption by the cylinder or radiation. The adiabatic law. This theory is equally applicable to the cooling of gases by abstraction of heat, or by cooling due to expansion by the motion of a piston. The denominators of these heat fractions of expansion or contraction represent the absolute zero of cold below the freezing point of water, and read -273 degrees Celsius, or -492.66 degrees equals -460.66 degrees Fahrenheit below zero, and these are the starting points of reference in computing the heat expansion in gas engines. According to Boyle's law, called the first law of gases, there are but two characteristics of a gas and their variations to be considered, viz., volume and pressure, while by the law of Gay-Lussac, called the second law of gases, a third is added, consisting of the value of the absolute temperature, counting from absolute zero to the temperatures at which the operations take place. This is the adiabatic law. The ratio of the variation of the three conditions, volume, pressure, and heat, from the absolute zero temperature has a certain rate in which the volume multiplied by the pressure and the product divided by the absolute temperature equals the ratio of expansion for each degree. If a volume of air is contained in a cylinder having a piston and fitted with an indicator, the piston, if moved to and fro slowly, will alternately compress and expand the air, and the indicator pencil will trace a line or lines upon the card, which lines register the change of pressure and volume occurring in the cylinder. If the piston is perfectly free from leakage, and it be supposed that the temperature of the air is kept quite constant, then the line so traced is called an isothermal line, and the pressure at any point when multiplied by the volume is a constant, according to Boyle's law. P times V equals a constant. If, however, the piston is moved very rapidly, the air will not remain at constant temperature, but the temperature will increase because work has been done upon the air, and the heat has no time to escape by conduction. If no heat whatever is lost by any cause, the line will be traced over and over again by the indicator pencil, the cooling by expansion, doing work precisely equaling the heating by compression. This is the line of no transmission of heat, therefore known as adiabatic. The expansion of a gas 1/273rd of its volume for every degree centigrade added to its temperature is equal to the decimal 0.00366, the coefficient of expansion for centigrade units. To any given volume of a gas, its expansion may be computed by multiplying the coefficient by the number of degrees, and by reversing the process the degree of acquired heat may be obtained approximately. These methods are not strictly in conformity with the absolute mathematical formula, because there is a small increase in the increment of expansion of a dry gas, and there is also a slight difference in the increment of expansion due to moisture in the atmosphere and to the vapor of water formed by the union of the hydrogen and oxygen in the combustion chamber of explosive engines. Chapter 3. Efficiency of internal combustion engines. Efficiencies are worked out for a variety of theoretical and unknown conditions of combustion in the cylinder, ratios of clearance and cylinder volume, and the uncertain condition of the products of combustion left from the last impulse and the wall temperature. But they are of but little value, except as a mathematical inquiry as to possibilities. The real commercial efficiency of a gas or gasoline engine depends upon the volume of gas or liquid at some assigned cost, required per actual brake horsepower per hour, in which an indicator card should show that the mechanical action of the valve gear and ignition was as perfect as practicable, and that the ratio of clearance, space, and cylinder volume gave a satisfactory terminal pressure and compression, i.e., the difference between the power figured from the indicator card and the brake power being the friction loss of the engine. In four-cycle motors of the compression type, the efficiencies are greatly advanced by compression, producing a more complete infusion of the mixture of gas or vapor and air, quicker firing, and far greater pressure than is possible with the two-cycle type previously described. In the practical operation of the gas engine during the past 20 years, the gas consumption efficiencies per indicated horsepower have gradually risen from 17% to a maximum of 40% of the theoretical heat, and this has been done chiefly through a decreased combustion chamber and increased compression, the compression having gradually increased in practice from 30 pounds per square inch to above 100. But there seems to be a limit to compression as the efficiency ratio decreases with greater increase in compression. It has been shown that an ideal efficiency of 33% for 38 pounds, compression will increase to 40% for 66 pounds, and 43% for 88 pounds compression. On the other hand, greater compression means greater explosive pressure and greater strain on the engine structure, which will probably retain in future practice the compression between the limits of 40 and 90 pounds, except in supercompression engines intended for high-altitude work, where compression pressures as high as 125 pounds have been used. In experiments made by Dugald Clerk in England with a combustion chamber equal to 0.6 of the space swept by the piston with a compression of 38 pounds, the consumption of gas was 24 cubic feet per indicated horsepower per hour. With 0.4 compression space and 61 pounds compression, the consumption of gas was 20 cubic feet per indicated horsepower per hour, and with 0.34 compression space and 87 pounds compression, the consumption of gas fell to 14.8 cubic feet per indicated horsepower per hour, the actual efficiencies being respectively 17, 21, and 25%. This was with a Crossley 4-cycle engine. Various measures of efficiency. The efficiencies in regard to power in a heat engine may be divided into 4 kinds as follows. 1. The first is known as the maximum theoretical efficiency of a perfect engine, represented by the lines in the indicator diagram. It is expressed by the formula T sub 1 minus T sub 0 divided by T sub 1, and shows the work of a perfect cycle in an engine working between the received temperature plus absolute temperature, T sub 1, and the initial atmospheric temperature plus absolute temperature, T sub 0. 2. The second is the actual heat efficiency, or the ratio of the heat turned into work to the total heat received by the engine. It expresses the indicated horsepower. 3. The third is the ratio between the second, or actual heat efficiency, and the first, or maximum theoretical efficiency of a perfect cycle. It represents the greatest possible utilization of the power of heat in an internal combustion engine. 4. The fourth is the mechanical efficiency. This is the ratio between the actual horsepower delivered by the engine through a dynamometer, or measured by a brake horsepower, and the indicated horsepower. The difference between the two is the power lost by engine friction. In regard to the general heat efficiency of the materials of power in explosive engines, we find that with good illuminating gas, the practical efficiency varies from 25 to 40%. Kerosene motors, 20 to 30. Gasoline motors, 20 to 32. Acetylene, 25 to 35. Alcohol, 20 to 30% of their heat value. The great variation is no doubt due to the imperfect mixtures and variable conditions of the old and new charge in the cylinder, uncertainty as to leakage, and the perfection of combustion. In the diesel motors operating under high pressure, up to nearly 500 pounds, an efficiency of 36% is claimed. The graphic diagram at Figure 12 is of special value, as it shows clearly how the heat produced by charge combustion is expended in an engine of average design. On general principles, the greater difference between the heat of combustion and the heat at exhaust is the relative measure of the heat turned into work, which represents the degree of efficiency without loss during expansion. The mathematical formulas appertaining to the computation of the element of heat and its work in an explosive engine are in a large measure dependent upon assumed values, as the conditions of the heat of combustion are made uncertain by the mixing of the fresh charge with the products of a previous combustion, and by absorption, radiation, and leakage. The computation of the temperature from the observed pressure may be made as before explained, but for compression engines, the needed starting points for computation are very uncertain and can only be approximated from the exact measure and value of the elements of combustion in a cylinder charge. Chapter 4. Engine Parts and Functions. The principal elements of a gas engine are not difficult to understand, and their functions are easily defined. In place of the barrel of the gun, one has a smoothly machined cylinder in which a small cylindrical or barrel-shaped element fitting the bore closely may be likened to a bullet or cannonball. It differs in this important respect, however, as while the shot is discharged from the mouth of the cannon, the piston member sliding inside of the main cylinder cannot leave it, as its movements back and forth from the open to the closed end and back again are limited by simple mechanical connection or linkage which comprises crank and connection rod. It is by this means that the reciprocating movement of the piston is transformed into a rotary motion of the crankshaft. The flywheel is a heavy member attached to the crankshaft of an automobile engine which has energy stored in its rim as the member revolves, and the momentum of this revolving mass tends to equalize the intermittent pushes on the piston head produced by the explosion of the gas in the cylinder. In aviation engines, the weight of the propeller or that of rotating cylinders themselves performs the duty of a flywheel, so no separate member is needed. If some explosive is placed in the chamber formed by the piston and closed end of the cylinder and exploded, the piston would be the only part that would yield to the pressure which would produce a downward movement. As this is forced down, the crankshaft is turned by the connecting rod, and as this part is hinged at both ends, it is free to oscillate as the crank turns, and thus the piston may slide back and forth, while the crankshaft is rotating or describing a curvilinear path. In addition to the simple elements described, it is evident that a gasoline engine must have other parts. The most important of these are the valves, of which there are generally 2 to each cylinder. One closes the passage connecting to the gas supply and opens during one stroke of the piston in order to let the explosive gas into the combustion chamber. The other member, or exhaust valve, serves as a cover for the opening through which the burned gases can leave the cylinder after their work is done. The spark plug is a simple device which may be compared to the fuse or percussion cap of the cannon. It permits one to produce an electric spark in the cylinder when the piston is at the best point to utilize the pressure which obtains when the compressed gas is fired. The valves are open one at a time, the inlet valve being lifted from its seat while the cylinder is filling, and the exhaust valve is opened when the cylinder is being cleared. They are normally kept seated by means of compression springs. In the simple motor shown at Figure 5, the exhaust valve is operated by means of a pivoted bell crank rocked by a cam which turns at half the speed of the crankshaft. The inlet valve operates automatically, as will be explained in proper sequence. In order to obtain a perfectly tight combustion chamber, both intake and exhaust valves are closed before the gas is ignited, because all of the pressure produced by the exploding gas is to be directed against the top of the movable piston. When the piston reaches the bottom of its power stroke, the exhaust valve is lifted by means of the bell crank, which is rocked because of the point or lift on the cam. The camshaft is driven by positive gearing and revolves at half the engine speed. The exhaust valve remains open during the whole of the return stroke of the piston, and as this member moves toward the closed end of the cylinder, It forces out burned gases ahead of it through the passage controlled by the exhaust valve. The camshaft is revolved at half the engine speed because the exhaust valve is raised from its seat during only one stroke out of 4, or only once every 2 revolutions. Obviously, if the cam was turned at the same speed as the crankshaft, it would remain open once every revolution, whereas the burned gases are expelled from the individual cylinders only once in 2 turns of the crankshaft. Why multiple cylinder forms are best. Owing to the vibration which obtains from the heavy explosion in the large single-cylinder engines used for stationary power, other forms were evolved in which the cylinder was smaller and power obtained by running the engine faster, but these are suitable only for very low powers. When a single-cylinder engine is employed, a very heavy flywheel is needed to carry the moving parts through idle strokes necessary to obtain a power impulse. For this reason, automobile and aircraft designers must use more than one cylinder, and the tendency is to produce power by frequently occurring light impulses rather than by a smaller number of explosions having greater force. When a single-cylinder motor is employed, the construction is heavier than is needed with a multi-cylinder form. Using 2 or more cylinders conduces to steady power generation and a lessening of vibration. Most modern motor cars employ 4-cylinder engines because a power impulse may be secured twice every revolution of the crankshaft, or a total of 4 power strokes during 2 revolutions. The parts are so arranged that while the charge of gas in one cylinder is exploding, those which come next in firing order are compressing, discharging the inert gases, and drawing in a fresh charge, respectively. When the power stroke is completed in one cylinder, the piston in that member in which a charge of gas has just been compressed has reached the top of its stroke, and when the gas is exploded, the piston is reciprocated and keeps the crankshaft turning. When a multiple cylinder engine is used, the flywheel can be made much lighter than that of the simpler form and eliminated altogether in some designs. In fact, many modern multiple cylinder engines developing 300 horsepower weigh less than the early single and double cylinder forms, which developed but 1/10 or 1/20 that amount of energy. Describing sequence of operations. Referring to Figure 22A, the sequence of operation in a single-cylinder motor can be easily understood. Assuming that the crankshaft is turning in the direction of the arrow, it will be seen that the intake stroke comes first, then the compression, which is followed by the power impulse, and lastly, the exhaust stroke. If 2 cylinders are used, it is possible to balance the explosions in such a way that one will occur each revolution. This is true with either one of 2 forms of 4-cycle motors. At B, a 2-cylinder vertical engine using a crankshaft in which the crank pins are on the same plane is shown. The 2 pistons move up and down simultaneously. Referring to the diagram describing the strokes, and assuming that the outer circle represents the cycle of operations in one cylinder, while the inner circle represents the sequence of events in the other cylinder, while cylinder number 1 is taking in a fresh charge of gas, cylinder number 2 is exploding. When cylinder number 1 is compressing, cylinder number 2 is exhausting. during the time that the charge in cylinder number 1 is exploded, cylinder number 2 is being filled with fresh gas. While the exhaust gases are being discharged from cylinder number 1, cylinder number 2 is compressing the gas previously taken. The same condition obtains when the crank pins are arranged at 180 degrees and the cylinders are opposed, as shown at C. The reason that the two-cylinder opposed motor is more popular than that having two vertical cylinders is that it is difficult to balance the construction shown at B, so that the vibration will not be excessive. The two-cylinder opposed motor has much less vibration than the other form, and as the explosions occur evenly and the motor is a simple one to construct, it has been very popular in the past on light cars and has received a limited application on some early light airplanes. To demonstrate very clearly the advantages of multiple cylinder engines, the diagrams at Figure 23 have been prepared. At A, a three-cylinder motor having crank pins at 120 degrees, which means that they are spaced at thirds of the circle, we have a form of construction that gives a more even turning than that possible with a two-cylinder engine. Instead of one explosion per revolution of the crankshaft, one will obtain 3 explosions in 2 revolutions. The manner in which the explosion strokes occur and the manner they overlap strokes in the other cylinder is shown at A. Assuming that the cylinders fire in the following order: first, number 1, then number 2, and last, number 3, we will see that while cylinder number 1, represented by the outer circle, is on the power stroke, cylinder number 3 has completed the last 2/3 of its exhaust stroke and has started on its intake stroke. Cylinder number 2, represented by the middle circle, during the same period has completed its intake stroke and 2/3 of its compression stroke. A study of the diagram will show that there is an appreciable lapse of time between each explosion. Three-cylinder engines are not used on aircraft at the present time, though Blériot's flight across the British Channel was made with a three-cylinder Anzani motor. It was not a conventional form, however. The three-cylinder engine is practically obsolete at this time for any purpose except penguins or school machines that are incapable of flight and which are used in some French training schools for aviators. Radial cylinder arrangements. While the fixed cylinder forms of engines, having the cylinders in tandem in the 4- and 6-cylinder models, as shown at figures 33 to 35 inclusive, and the 8-cylinder V-types, as outlined at figures 36 and 37, have been generally used and are most in favor at the present time. Other forms of motors having unconventional cylinder arrangements have been devised, though most of these are practically obsolete. While many methods of decreasing weight and increasing mechanical efficiency of a motor are known to designers, one of the first to be applied to the construction of aeronautical power plants was an endeavor to group the components, which in themselves were not extremely light, into a form that would be considerably lighter than the conventional design. As an example, we may consider those multiple cylinder forms in which the cylinders are disposed around a short crankcase, either radiating from a common center, as at figure 38, or of the fan shape, shown at figure 39. This makes it possible to use a crankcase but slightly larger than that needed for 1 or 2 cylinders, and it also permits of a corresponding decrease in length of the crankshaft. The weight of the engine is lessened because of the reduction in crankshaft and crankcase weight, and the elimination of a number of intermediate bearings and their supporting webs, which would be necessary with the usual tandem construction. While there are 6 power impulses to every 2 revolutions of the crankshaft, in the 6-cylinder engine they are not evenly spaced as is possible with the conventional arrangement. In the Anzani form, which is shown at Figure 38, the crankcase is stationary, and a revolving crankshaft is employed as in conventional construction. The cylinders are 5 in number, and the engine develops 40 to 50 horsepower with a weight of 72 kilograms or 158.4 pounds. The cylinders are of the usual air-cooled form, having cooling flanges only part of the way down the cylinder. By using 5 cylinders, it is possible to have the power impulses come regularly, they coming 145-degree crankshaft travel apart, the crankshaft making 2 turns to every 5 explosions. The balance is good and power output regular. The valves are placed directly in the cylinder head and are operated by a common push rod. Attention is directed to the novel method of installing the carburetor, which supplies the mixture to the engine base, from which inlet pipes radiate to the various cylinders. This engine is used on French school machines. In the form shown at Figure 39, 6 cylinders are used, all being placed above the crankshaft center line. This engine is also of the air-cooled form and develops 50 horsepower and weighs 105 kilograms or 231 pounds. The carburetor is connected to a manifold casting attached to the engine base, from which the induction pipes radiate to the various cylinders. The propeller design and size relative to the engine is clearly shown in this view. While flights have been made with both of the engines described, this method of construction is not generally followed, and has been almost entirely displaced abroad by the revolving motors or by the more conventional 8-cylinder V engines. Both of the engines shown were designed about 8 years ago and would be entirely too small and weak for use in modern airplanes intended for active duty. Chapter 5. Properties of Liquid Fuels. There is no appliance that has more material value upon the efficiency of the internal combustion motor than the carburetor or vaporizer which supplies the explosive gas to the cylinders. It is only in recent years that engineers have realized the importance of using carburetors that are efficient and that are so strongly and simply made that there will be little liability of derangement. As the power obtained from the gas engine depends upon the combustion of fuel in the cylinders, it is evident that if the gas supplied does not have the proper proportions of elements to ensure rapid combustion, the efficiency of the engine will be low. When a gas engine is used as a stationary installation, it is possible to use ordinary illuminating or natural gas for fuel, but when this prime mover is applied to automobiles or airplanes, it is evident that considerable difficulty would be experienced in carrying enough compressed coal gas to supply the engine for even a very short trip. Fortunately, the development of the internal combustion motor was not delayed by the lack of suitable fuel. Engineers were familiar with the properties of certain liquids, which gave off vapors that could be mixed with air to form an explosive gas which burned very well in the engine cylinders. A very small quantity of such liquids would suffice for a very satisfactory period of operation. The problem to be solved before these liquids could be applied in a practical manner was to evolve suitable apparatus for vaporizing them without waste. Among the liquids that can be combined with air and burned, gasoline is the most volatile and is the fuel utilized by internal combustion engines. The widely increasing scope of usefulness of the internal combustion motor has made it imperative that other fuels be applied in some instances, because the supply of gasoline may in time become inadequate to supply the demand. In fact, abroad this fuel sells for 50 to 200% more than it does in America, because most of the gasoline used must be imported from this country or Russia. Because of this, foreign engineers have experimented widely with other substances, such as alcohol, benzol, and kerosene, but more to determine if they can be used to advantage in motor cars than in airplane engines. Principles of carburation outlined. The process of carburation is combining the volatile vapors which evaporate from the hydrocarbon liquids with certain proportions of air to form an inflammable gas. The quantities of air needed vary with different liquids, and some mixtures burn quicker than do other combinations of air and vapor. Combustion is simply burning, and it may be rapid, moderate, or slow. Mixtures of gasoline and air burn quickly. In fact, the combustion is so rapid that it is almost instantaneous, and we obtain what is commonly termed an explosion. Therefore, the explosion of gas in the automobile engine cylinder, which produces the power, is really a combination of chemical elements which produce heat and an increase in the volume of the gas because of the increase in temperature. If the gasoline mixture is not properly proportioned, the rate of burning will vary, and if the mixture is either too rich or too weak, the power of the explosion is reduced, and the amount of power applied to the piston is decreased proportionately. In determining the proper proportions of gasoline and air, one must take the chemical composition of gasoline into account. The ordinary liquid used for fuel is said to contain about 84% carbon and 16% hydrogen. Air is composed of oxygen and nitrogen, and the former has a great affinity, or combining power, with the two constituents of hydrocarbon liquids. Therefore, what we call an explosion is merely an indication that oxygen in the air has combined with the carbon and hydrogen of the gasoline. End of section 10. End of the Insomnia collection, volume 6.